complete view of how Australopithecines like Lucy are related to modern humans, and whilst the details are still debated and new evidence is continually updating the standard model of hominin evolution, it's now possible to tell the broad sweep of the story in some detail. The members of our human evolutionary family are referred to as hominins. The split between hominins and the ancestor of the chimpanzee occurred at some point before 5 million years ago in Africa, and by 4 million years ago, Australopithecus afarensis, Lucy, was present. Their brain size was approximately 500 cc, around the same as a chimpanzee, and less than 1/3 that of a modern human. Around 1.8 million years ago, there was a step change in both brain size and the number of hominin species in the East African Rift. Several species of our genus Homo appeared, including Homo habilis and Homo erectus. They lived for a time alongside other species, including several Australopithecines and a genus known as Paranthropus. There are anthropologists who prefer to classify Paranthropus as a different species of Australopithecus. I make this point not to be confusing, but to highlight an important fact. The study of hominin evolution is a difficult area, and it's not surprising that there are ongoing debates about the classification of 2-million-year-old fossils and DNA sequences. What's important for our story, however, and what nobody disputes, is that there seems to have been a jump in both brain size and the number of species of hominins in the Rift Valley region around 1.8 million years ago. By around 1.4 million years ago, only one of these species had survived, Homo erectus, with a brain size of 1,000 cc. The next milestone is the appearance of Homo heidelbergensis around 800,000 years ago. Homo heidelbergensis is generally accepted to be the ancestor of Homo sapiens and the Neanderthals who lived alongside us in Europe until around 45,000 years ago, and possibly later. Homo heidelbergensis represented another jump in brain size, up to around 1400 cc, which is close to that of modern humans. In the late 1960s and early 1970s, 2 hominin skulls were found near the Omo River in Ethiopia. Known as Omo 1 and Omo 2, argon dating of the volcanic sediments around the level they were found dates them at 195,000 plus or minus 5,000 years old. These are the earliest fossilized remains to have been identified as Homo sapiens. The interesting question is what caused these rapid increases in brain size, driving hominin intelligence from the chimpanzee-like capabilities of Australopithecus to modern humans in only a few million years. Again, this is a very active area of research, and there are differences of opinion amongst experts. This is the nature of science at the frontier of knowledge, and this is what makes science exciting and successful. The model we are focusing on is the most widely accepted theory of human evolution. It is known as the recent single origin hypothesis, or more colloquially, the out of Africa model, and the dates and locations we've described so far might be referred to as textbook. There is broad consensus, therefore, about the when and the where, but not why, and it is to why that we now turn. There's a trend towards larger brain size over the 4 million years since the emergence of Australopithecus, but the trend is not gradual. There's a large jump around 1.8 million years ago with the emergence of Homo erectus, and another jump just under 1 million years ago with Homo heidelbergensis. The final jump occurs when Homo sapiens emerges 200,000 years ago. The time period around 1.8 million years ago also corresponds to a leap in the number of hominin species present in the Rift Valley. There were at least 5 or 6 species living side by side, suggesting that something interesting occurred around this time, which may have been responsible for, or was a contributing factor to, the observed increase in brain size, particularly in Homo erectus. The large number of deep-water lakes appearing temporarily in the Rift Valley around 1.8 million years ago indicates that at this time the climate, and in particular the level of rainfall, was varying quickly and violently. Similar climate variation occurs around 1 million years ago and 200,000 years ago, and this appears to be correlated with increase in hominin brain size. The theory is that rapidly changing climatic conditions in the Rift Valley at these specific times played an important role in driving the increases in brain size. The selection pressures that may have led to these increases are unclear. Selection for adaptability was probably an important factor, but social factors such as the ability to live in large groups and intraspecies competition as a result of the larger number of species living side by side, particularly around 1.8 million years ago, must also have played a role. Having said that, it does appear that climate variation in the Rift Valley 1.8 million, 1 million and 200,000 years ago could have been a contributing factor to the development of our intelligence. This is known as the pulse climate variability hypothesis. We can now bring all these threads together to reveal a surprising and, for me, dizzying hypothesis, which, if correct, sheds new light on the immensely contingent nature of the existence of our modern civilization, or, in simpler language, why we are bloody lucky to be here. The three dates, 1.8 million, 1 million and 200,000 years ago, correspond to the times when the Earth's orbit was at its most elliptical. As described earlier, the mechanism by which climate changes due to precession at these times is well understood. The pulse climate variability hypothesis asserts that the unique geology and position of the Great Rift Valley amplified these changes, and that early hominins responded by increasing their brain size. If this is correct, our brains evolved as a response to changes in the Earth's orbit, driven by the precise arrangement of the orbits of the other planets around the Sun, and precession, driven primarily by the gravitational interaction between the Moon and Earth's axial tilt, both of which date back to a collision early in the history of the solar system. And all this is plainly blind luck. Without an inconceivably unlikely set of coincidences, and the way these conspired together to change the climate in one system of valleys in wonderful Ethiopia, we wouldn't exist. If this is correct, then what a response! I held a brain for the cameras at St. Paul's Teaching Hospital in Addis. It is the most complex single object in the known universe, a most intricate example of emergent complexity, assembled over 4 billion years by natural selection, operating within the constraints placed upon it by the laws of physics and the particular biochemistry of life on Earth. The brain contains around 85 billion individual neurons, which is of the same order as the number of stars in an average galaxy. But that doesn't begin to describe its complexity. Each neuron is thought to make between 10,000 and 100,000 connections to other neurons, making the brain a computer way beyond anything our current technology can simulate. When we do manage to simulate one, I have no doubt that sentience will emerge. Consciousness is not magic. It is an emergent property consistent with the known laws of nature. But that doesn't lessen the wonder one iota. Out of this evolutionary marvel, we emerge. Thoughts, feelings, hopes, and dreams exist on Earth because of electrical activity inside a 1.5 kilogram blob of stuff, which hasn't changed much since the earliest modern humans began the long journey out of Africa. If you could travel back in time and bring a newborn baby from 200,000 years ago into the 21st century, allowing it to grow up in our modern society with a modern education, it could achieve anything a modern child could. It could even become an astronaut. Which sets up one more question. If the hardware was present 200,000 years ago, then what changed to lift us from the Great Rift Valley into space? An unprecedented duel with nature. The best thing we can do now is just to listen and hope, said Cliff Mitchellmore, broadcasting from the BBC studios 24 minutes from the expected splashdown of Apollo 13. On the 17th of April 1970, I was too young to watch the live broadcast, but I've seen the recording many times since. Grainy pictures from the deck of the USS Iwo Jima, its flight deck crammed with nervous sailors off the coast of Samoa. Patrick Moore and Geoffrey Pardo, grim-faced in the studios, and James Burke famously with fingers crossed behind his back. Apollo Control, Houston, we've just had loss of signal from Honeysuckle. Honeysuckle Creek Tracking Station in Canberra, Australia, was the last ground station to contact Apollo 13 before it entered the Earth's atmosphere on its way home. Signal loss during re-entry is routine high drama on all space missions. The ionization of the atmosphere caused by the frictional heating of the spacecraft blocks radio signals, typically resulting in radio silence for 4 minutes. On Apollo 13, 6 minutes passed in silence. The brilliance of the BBC's quartet of commentators was in the silence they allowed on the airwaves. The only sound was the static of the NASA feed, a moment of genuine tension. No need for vacuous media babble. Nobody could bring themselves to speak. We'll only know whether that heat shield was damaged by that explosion 3 days ago, when they come out of radio blackout in just over 2 minutes, said Burke. Silence. As 4 minutes passed, Houston reports, 10 seconds to end of radio blackout. Silence. Houston. We've had a report that Orion 4 aircraft has acquisition of signal. They're through, says Burke. Let's not anticipate because the parachutes may have been damaged. Chutes should be out, murmurs Burke, not broadcasting, just saying. There they are! There they are! They've made it, remarks Moore, and then applause. I make it no more than 5 seconds late, shouts Burke. No more than 5 seconds late. The safe return of Apollo 13 was arguably NASA's finest hour. 55 hours, 54 minutes, and 53 seconds into the mission, 320,000 kilometers from Earth, lunar module pilot Jack Swigert switched on a system of stirring fans in the hydrogen and oxygen tanks in the service module, a routine procedure. A piece of Teflon insulation inside the tank had been damaged, it was later discovered, by a series of unlikely events that happened on the ground during the preparation of the spacecraft for flight. The wire shorted, the tank exploded, and the side of the service module was blown off, critically damaging the spacecraft's power supply systems and venting the crew's oxygen supply out into space. The command module, the only part of the spacecraft capable of surviving a re-entry through the Earth's atmosphere, was now running on batteries, and with a rapidly diminishing oxygen supply that would not keep the astronauts alive long enough to return to Earth. The only option was to shut down the command module and retreat to the lunar module, effectively using it as a life raft. Lovell later spoke of how he didn't regret the mission at all. He was robbed of his moon landing, which must have been doubly frustrating given he'd already flown to the moon on the historic Apollo 8 mission. But his reaction, revealed in interviews in later life, offers great insight into the character of a test pilot. We were given the situation, Lovell explained, to really exercise our skills and our talents to take a situation which was almost certainly catastrophic and come home safely. That's why I thought that 13 of all the flights, including Apollo 11, that 13 exemplified a real test pilot's flight. Both Lovell and Hayes have said that the idea of not returning safely to Earth never really came up. There was nothing there that said irrefutably, we don't have a chance. Hayes was correct, of course, because they did return safely. But they only had enough food and water to sustain 2 people for a day and a half, and had to improvise a carbon dioxide filter to provide them with enough breathable air for the return journey. Locked in the lunar module with limited supplies of food and water, and temperatures dropping towards freezing, life was far from comfortable. With the command module powered down to preserve the sparse battery supplies left after the loss of the fuel cells, the crew had to survive in a hostile environment with limited resources. Like so many outposts of human civilization throughout history, shortage of water was a primary concern. Water was critical on the lunar module for 2 reasons. As well as being needed to keep the crew hydrated and to rehydrate the food, it also cooled the electrical systems on the spacecraft. Conserving water therefore became a critical part of the plan to return to Earth. Reducing their intake to just 1/5 of a normal human water ration, each of the crew suffered severe dehydration, and together they lost 31.5 pounds in weight, nearly 50% more than any other Apollo crew. Despite the discomfort, setting a new mission trajectory and navigating their way along it remained the primary challenge. The standard way to make in-flight course corrections on Apollo was to use the command module's main engine. But the system was located close to the damaged site, and mission controllers decided that lighting it was too great a risk. Instead, the decision was made to use the LM's descent engine to send them around the far side of the Moon and back to Earth in 4.5 days. This is known as a free return trajectory, a slingshot around the Moon at the correct angle to return directly to Earth. No one knew if an engine designed for a completely different purpose would perform this function successfully. But they knew that if it failed, they would not return. 5 hours after the initial explosion, the LM engine was fired for a 35-second burn, successfully putting the crew onto a free return trajectory. This solved one problem, but raised another. Calculations of the trajectory estimated return to Earth 153 hours after launch, which would push the key reserves on the craft too low for comfort. So it was decided to speed up the spacecraft with another burn, cutting the total time of the voyage by 10 crucial hours. Such were the slim margins on Apollo 13. The main navigation system in the command module was out of action, so Lovell had to calculate the correct navigational inputs, while back at base, Mission Control worked through the same calculations as a cross-check. Lovell also got to use his sextant, which he played with on Apollo 8, to navigate by the stars for real. The calculations are preserved as handwritten notes in the Lunar Module's Systems Activation Checklist. This was the checklist Lovell and Hayes would have used to fly down to the Moon's surface. Now useless, Lovell used the waste paper to write down instructions to put the ship on course for Earth. 2 hours after they rounded the far side of the Moon, the LM engine fired, following Lovell's handwritten checklist, increasing the speed of the spacecraft by 860 feet per second and buying them 10 precious hours. The most dramatic rescue in the history of human spaceflight stands as a testament to the brilliance of the 3 test pilots Lovell, Hayes and Swigert, and also to the brilliance of the engineers on the ground, who simply knew their stuff. NASA's Apollo engineers were young by today's standards. The average age of the team in mission control for the splashdown of Apollo 11 was 28 years old. This is one of the reasons why the United States reaped such a colossal economic reward from its investment in Apollo. The generation of scientists and engineers who worked on and were inspired by Apollo went out into the wider economy and delivered a huge investment return. A series of studies, including one by Chase Econometrics, showed that for every dollar invested in Apollo, at least $6 or $7 was returned as increased GDP growth. This should, of course, be bloody obvious. New knowledge grows GDP. But every generation of politicians seems to require re-educating to understand the difference between spending and investment. And while I'm polemicizing, let me say that the usual political argument that public support is needed for such large investments is drivel. Firstly, the investment in NASA wasn't that large, never exceeding 4.5% of the federal budget throughout the lifetime of Apollo. And secondly, it is a politician's job to lead from the front, make the case that investment in knowledge, in pushing the boundaries of human capabilities and exploring all frontiers, both physical and intellectual, is the key to the future wealth, prosperity, and security of civilization. Aspire to be Kennedy, not a hand-wringing apologist for intellectual and technological decline. The 9 Apollo flights to the Moon remain the furthest modern humans have explored beyond the Rift Valley in our 200,000-year history. Homo sapiens first left Africa in large numbers 60,000 years ago. So on geological timescales, we didn't hang around. Our ancestors followed waves of earlier hominins. Homo erectus were in Southeast Asia 1.6 million years ago, and 500,000 years later Neanderthals had colonized Europe, and Homo floresiensis were in southern Asia. The details of the migration 60,000 years ago are particularly well understood as a result of the combination of genetic, archaeological, and linguistic studies. The precision comes in part from the tracking sequences of mitochondrial DNA, which is passed down from the mother and not shuffled by sex. This makes it relatively stable and easy to track. Changes are caused by mutations alone. The most widely accepted interpretation of the data suggests that a small population of between 1,000 and 2,500 individuals left East Africa 60,000 years ago and moved north across the Red Sea and through Arabia. The group then split, moving into southern Europe 43,000 years ago and traveling through India and into Australia on roughly the same timescale. The crossing into North America via eastern Russia was probably later, around 15,000 years ago. These early groups of humans were hunter-gatherers. It's been estimated that the basic social units would have reached a maximum of around 150 individuals. This is known as Dunbar's number, after the British anthropologist Robin Dunbar, who suggests that the largest social group amongst any given population of primates is related to the size of their brains, specifically the neocortex. Dunbar's number can be observed today in the size of the average person's social network, both in the real world and online. Our hardware, the brain, has not changed appreciably since the first humans appeared in Africa 200,000 years ago. These social groups would have lived in loosely bound tribes, perhaps reaching a size of between 1,000 and 2,000 individuals, operating within an area of around 100 kilometers. Populations would stabilize, perhaps in response to social factors, but also as a result of increased mortality rates caused by parasitic diseases and diminishing per capita resource availability, before fragmenting and spreading. In this fashion, the rate of progression of our ancestors across the globe has been estimated to have been around 0.5 kilometers per year, or 15 kilometers per generation. Population density did not rise significantly beyond these levels until these proto-societies shifted from a hunter-gatherer lifestyle to agriculture around 12,000 years ago. This shift was the trigger for the development of civilization, the most important single step following the migration out of Africa in the journey from ape-man to spaceman. There are many competing theories as to the reason for the domestication of crops, but many note the correlation between the first evidence of agriculture and the beginning of the current interglacial period known as the Holocene, 12,000 years ago. In the Fertile Crescent around modern-day Jordan and Syria, people known as the Natufians were beginning to settle into larger communities, perhaps because of the relatively benign climate. The area would have been forested and rich in wild cereals, fruits and nuts rather than the austere desert of today. One theory is that a brief 1,000-year cold period known as the Younger Dryas, beginning around 10,800 BCE, triggered drier conditions in the region, forcing the Natufians to begin cultivating the previously abundant wild crops on which they had come to rely. Whatever the reason, it's generally agreed that the foundational crops of modern agriculture, including wheat, barley, peas and lentils, were all to be found in the Fertile Crescent by 9,000 BCE, and by 8,000 BCE, the banks of the Nile were being cultivated. At approximately the same time, evidence of farming can be found in Asia's Indus Valley, in China, and in Mesoamerica. This suggests that there was no single environmental or developmental cause for agriculture, because it appeared independently at many sites across the world. Rather, our large brains and relatively large social groups were ready to take up the challenge when the need arose. Once agriculture was established, larger numbers of people could live together, taking advantage of the more stable food supply. The freedom from continual hunting and gathering would have introduced a new aspect to human life, free time, and it was used to great effect. Some of the earliest farmers settled in a place known as Beida in modern-day Jordan around 7,000 BCE. Living in round stone-built houses, they grew barley and wheat and kept domesticated goats, engaged in ritual and ceremony, and buried their dead. Importantly, each of these activities was carried out in specific areas of the settlements, the beginning of town planning. By the 2nd century BCE, a Semitic people known as the Nabateans lived around Beida. They employed new technologies to increase the reliability of farming and constructed walled agricultural terraces on the hillsides around the village to collect and store water. Animal husbandry was also expanding, with the domestication of cows, pigs, donkeys, and horses. Even previously dangerous animals were coerced into living with humans. There is evidence that the Nabateans kept dogs. As the great empires of Egypt, Greece, and Rome prospered, the Nabateans remained partially nomadic, driving their camel trains across the desert along the long-established trade routes between North Africa and India and the great cities of the Mediterranean. But then, around 150 BCE, they decided to try something different. A few kilometers south of Beda, in a narrow gorge naturally formed in the soft sandstone rock, they built the city of Petra. Today, tourists stream through a magnificent passageway lined with buildings carved out of the desert rocks and known as the Sikh. But 2,000 years ago, the great and good of Mesopotamia, Rome, and Egypt would have walked this route into this jewel of late antiquity. The grandeur of the buildings is still overwhelming. They stand not as great architecture for their time, but as simply great, with no caveat. The most famous is called Al-Khazne, which means treasure box, because of the carved urn above the entrance, which Bedouin legend has it contains the treasure of a pharaoh. Monumental architecture is a common feature in the rise of human civilization. It is a statement of power and grandeur to impress and cow outsiders, but it also serves an internal purpose, cementing the position of the rulers in the hierarchy, and therefore providing the stability and security on which civilization rests. Over time, a virtuous circle emerges. The buildings help the civilization prosper, and the more prosperous the civilization, the more impressive the buildings become. Petra's wealth was derived from its location. Built within a natural gorge, the area is prone to flash floods, which provided precious water in a landscape that was arid by the time the Nabateans began to build. The city also sits at the fulcrum of the ancient nomadic trade routes, along which wood, spices, incense, and dyes were transported from Africa and India, and into the great Mediterranean civilization beyond. The appetite of the Greeks and Romans for exotic goods was insatiable. Black pepper alone fetched 40 times its own weight in gold in a Roman market. Petra, because of its strategic location, controlled all that trade and taxed it. Today, 1,500 years after the city was abandoned, it is still a magnificent sight, an overused but entirely accurate statement. Talk to an archaeologist, however, and you quickly realize how much more impressive it would have been in its heyday. The hillsides running down the valley from the carved tombs are scattered with rocks, but closer inspection reveals them to be bricks, the remains of houses, temples, and palaces. Everything from Al-Khazne to the houses would have been covered in white plaster and painted in bright colors which would have appeared resplendent against the monochrome desert sands. To build on this scale required a huge labor force. Petra was home to at least 30,000 people living in a few square kilometers of desert. Such a population density required technological innovation on a metropolitan scale, and the Nabateans, perhaps more than any other civilization in antiquity, were masters of fluid engineering. Virtually every drop of rainwater that fell on the surrounding hillsides was captured in grooves and stored in giant reservoirs and cisterns. They were better at plumbing than the Romans, who employed the Petran engineers in Rome. Petra had the world's first pressurized water system, which could deliver 12 million gallons of water a day into the city. Outside the city, the irrigation system continued out into the surrounding fields, lining the hillsides in still visible terraces. The Nabateans didn't simply build a city, they terraformed a landscape. I stood and imagined the ancient valley views with some awe. The mountain slopes would have been green with maize, barley, pulses, and vineyards. A desert turned green and feeding this grandest of desert civilizations for 6 centuries. Whenever I see the ruins of Petra, Rome, Athens, or Cairo, I wonder what Earth would be like today if the great civilizations of antiquity had not fallen. I blame the philosophers for not discovering the scientific method earlier and inventing the electric motor. How hard can it be? Agriculture, then, was fundamentally important to the rise of civilization because it enabled large numbers of people to live in one place and gave them access to resources and time which would have been unavailable to hunter-gatherers. With resources and time comes the division of labor, freeing up a small but important subset of individuals to engage in pursuits other than those necessary for immediate survival. Farmers, stonemasons, priests, soldiers, administrators, and artisans emerge, together with a ruling class who begin to direct the construction of monumental architecture, partly for their own selfish ends, and cities like Petra become possible. Petra was a relative latecomer in the emergence of the cities and civilizations of antiquity. The first great ancient civilization, the Old Kingdom of Egypt, arose around 2600 BCE along the fertile and farmed banks of the Nile, and precisely the same pattern of agriculture, followed by social stratification, ritual, and monumental architecture, can be seen. Present also in the Old Kingdom, and possibly developed there, was the one final vitally important innovation we will soon discuss: the written word. It all seemed so simple when written down on a piece of paper. The BBC prepares something known as a call sheet, which tells a film crew everything they need to know about a trip. Call sheets are very neat. All the timings work beautifully, carefully documenting flights, ground transfers to locations, and filming and rest periods, all of course in accordance with health and safety regulations and all that. Things never quite work out the way they're envisaged back in the office, of course. But filming the return of the Expedition 38 crew from the International Space Station to the Kazakh Steppe in March 2014 was the wildest adventure I've experienced. The call sheet said that we would fly into Astana on the 8th of March, arriving at 1 a.m. on the 9th into our hotel. After a leisurely breakfast at 9 a.m., we drive to a city called Karaganda, which has a spectacular statue of Yuri Gagarin in the town square. There we'd meet up with our drivers, who, embedded with Roscosmos, the Russian space agency, would drive us out to the landing site the following morning, arriving in time for a hot meal and a good rest on the steppe, ready to film the landing on the morning of the 11th, after, of course, a hot breakfast. We'd then drive back to the airport, hop on a flight, and be home in time for lunch on the 12th. A doddle. Bollocks. The steppe of central Kazakhstan in March is a featureless frozen wilderness covering around 800,000 square kilometers of the country's interior. There are no towns and few roads, just tufts of stunted brown grass and snow fading into an ice-grey leaden sky. In March 2014, temperatures were unseasonably cold, falling below -20 degrees C at night, and it was snowing. Our team had standard 4x4 vehicles, which got stuck in the snow by mid-afternoon the day before the landing, even though we'd set off 3 hours earlier than the 6 a.m. officially sanctioned health and safety call time because of the weather. This was problematic because our 8-man spaceman film was constructed carefully around this moment, the return of 3 human beings from space. Over vodka, cold meat, and bread, we discussed our options. We'd been helped along the snowy roads by a Russian team from the Siberian city of Tobolsk in 2 spectacular 6-wheel drive vehicles hand-built by a company called Petrovich. Tobolsk is best known for being the place dissidents were sent during the Soviet era. Tsar Nicholas II and his family enjoyed the Tobolskian hospitality for a year before being transported to Ekaterinburg to be shot. Mendeleev, the inventor of the periodic table, was born there, but so was Rasputin. It's a tough place, and they know how to build tough vehicles. Our guide from Roscosmos managed to radio the Petrovich team, and they agreed that if we could catch them up in the frozen wilderness, they could take 2 of us out to the landing site. The cameraman and I jumped aboard a pair of snowmobiles and headed out into the rapidly dimming late afternoon twilight in search of the men from Siberia. If we hadn't found them, then presumably you wouldn't be reading this. But we did. It was a difficult decision to jump on the snowmobiles. We didn't have a satellite phone because they are illegal in Kazakhstan, and nobody spoke English, so we couldn't quite assess the level of difficulty associated with finding these 2 Siberian needles in a Kazakh steppe. And we didn't know who the Siberians actually were. It seemed that they were freelancers, hired to take photographs and broadcast live television pictures back from the landing site for the Russian Space Agency. We also had to decide whether we could make the film with only 2 people. Much as I spend a lot of time dreaming about jettisoning directors, producers and executives, there is a reason why we usually take a crew of 6. Sound is particularly important. You don't really miss the sound man until he's not there. Our sound man on the series is called Andy, but we always called him Sound Man. There are too many other things to remember. As it turned out, the Petrovich crew were a hospitable and professional bunch. Although their willingness to spend many days out in the wilderness waiting for the Soyuz, they'd driven down from Siberia and were in no hurry to get home, played on our minds. Approaching midnight on the night before the landing, we received a message from Roscosmos that the landing might be postponed due to the poor weather, and the decision was made to camp out on the steppe and wait. In the distance, we could make out a small group of farm buildings through the snow, and we headed towards them. In broken English, one of the crew told us that it is a Kazakh tradition to welcome travellers into your home at any time of the day or night and offer them food. And so we found ourselves inside a farmhouse that appeared to have heated walls and resembled the inside of an oven, eating a feast of jam, bread, assorted sweets and horse, all washed down with vodka, which the Petrovich crew carried in large crates alongside their satellite broadcasting hardware. It was unforgettable. Human Universe was filmed as a love letter to the human race, and time and again when I found myself immersed unexpectedly in a culture, I've been reminded about why it is appropriate to want to write one. At 4 a.m., soaked in vodka, the call came through. Commander Oleg Kotov, Sergei Ryazansky and Mike Hopkins had climbed aboard the Soyuz and were preparing to depart the International Space Station. I was elated because I genuinely thought the landing would be called off, and I had no idea what that would have meant other than waiting for the storms to clear on the steppe. At 6:02 Kazakh time, the Soyuz TMA-10M, the 199th Soyuz to fly since 1967, undocked from the ISS. This is the point of no return, except in an emergency. Just 2 hours and 28 minutes later, it fired its engine for a pre-programmed burn of 4 minutes and 44 seconds. This reduced the spacecraft's velocity by 128 meters per second relative to the station, which in its orbit that day was traveling at 7,358 meters per second. That number is not arbitrary. It is given by a simple equation which can be derived easily from Newton's law of gravitation and his second law of motion, F equals ma. We leave it as an exercise for the listener to show that these 2 laws of nature can be rearranged to show that the velocity v of any object in a circular orbit a distance r from the center of the Earth, mass me, is given by v equals the square root of gme over r. To derive this result, you need to know that the force required to maintain an object of mass m in a circular orbit is mv squared over r. The space station orbits at an altitude of between 330 and 445 kilometers. Let's choose the middle ground of 387 kilometers. This is a back-of-the-envelope calculation. Estimate is the name of the game, as my old physics teacher used to say at school. The radius of the Earth is 6,378 kilometers, and the mass of the Earth is 5.97219 times 10 to the 24 kilograms. Newton's gravitational constant is 6.67384 times 10 to the minus 11 meters cubed per kilogram per second squared. Do the calculation yourself. Maths is good for you. With these numbers, v is approximately 7,675 meters per second, which is close enough. The difference is due to the precise altitude of the ISS that day. I love doing little calculations like this. They reveal the immense power of mathematical physics. This really is the orbital velocity of the International Space Station, and it is forced to be so by laws of nature first published by Isaac Newton in 1687. If you've never done a calculation like this before, you should feel elated. The biologist Edward O. Wilson called this feeling the Ionian enchantment, a poetic term he introduced to describe the realization, credited to Thales of Miletus in 600 BCE, that the natural world is orderly and simple and can be described with great economy by a small set of laws. It is nothing short of wonderful that we can calculate the orbital velocity of the International Space Station together in a few lines of a popular book, and this points us neatly towards the story of the last great innovation in the ascent from ape-man to spaceman, the written word. But after all, who knows and who can say whence it all came and how creation happened? The gods themselves are later than creation, so who knows truly whence it has arisen? Ancient Brahmin verse. A neat piece of logic. There is tension at the interface between science and language. Language is concerned with human experience. Everyone understands what's meant by questions such as, "Why are you late?" "I'm late because my alarm clock didn't go off." But this answer is incomplete and could be followed by a series of further questions in an attempt to establish precisely why. Why didn't it go off? Because it's broken. Why is it broken? Because a piece of solder melted on the circuit board. Why did the solder melt? Because it got hot. Why did it get hot? Because it's August and my room is hot. Why is it hot in August? Because of the details of the Earth's orbit around the Sun. Why does the Earth orbit the Sun? Because of the action of the gravitational force. Why is there a gravitational force? I don't know. All scientific why questions end with "I don't know" if you keep pushing far enough, because our scientific understanding of the universe is not complete. The most fundamental description we have for anything comes down to a set of theories describing the smallest known building blocks of the universe and the forces of nature that allow them to interact with each other. These theories are known as laws of physics, and when we ask about the origin of these laws, the answer is we don't know. This is because in the Big Bang model, our understanding of physics before 10 to the minus 43 seconds after the origin of the visible universe is virtually non-existent, and the origin of the laws lies at some point before that. The laws themselves are later than creation, and who knows truly whence it has arisen. Our best theory of space and time, Einstein's general theory of relativity, no longer applies at the earliest times. The conditions were so extreme in those first moments, known as the Planck epoch, that some kind of quantum theory of gravity, which we do not possess, will be needed to describe it. The universe is now 13.798 plus or minus 0.037 billion years old, according to our current best measurements and theoretical understanding, and has been gently expanding and cooling ever since the Big Bang. The universe appears to be gently increasing its expansion rate, and approximately 68% of the energy in the universe is associated with this sedate acceleration. The energy has a name, dark energy, but its nature remains one of the great unsolved challenges for 21st century theoretical physics. Of the 32% that remains, approximately 27% is in a form of matter known as dark matter. The nature of this is also unknown, but it probably comes in the form of as yet undiscovered subatomic particles. The remaining 5% makes up the stars, planets, and galaxies we see in the night sky, and of course human beings. The part of the universe we can see is around 93 billion light-years across, and has reached a relatively chilly temperature of 2.72548 plus or minus 0.00057 Kelvin due to its expansion. The question of the origin of the universe is an old one in philosophy, and often framed in terms of the first cause argument. Leibniz is associated with a proof of the existence of God in this context, which goes something like this. Everything that exists must have either an external cause or must be eternal. If there are eternal things, then they must necessarily exist because they don't have a cause. Since the universe exists and is not eternal, it must have an external cause, and to avoid infinite regress, that cause must be an eternal and necessary thing, which we'll call God. This is quite a neat piece of logic, obviously because Leibniz wasn't an idiot. I don't consider such questions to fall necessarily within the domain of science. Rather, science is concerned with answering more modest questions, and this is the reason for its power and success. The goal of science is to explain the observed features of the natural world. By explain, I mean build theories that make predictions that are in accord with observation. This is a humble idea. There is no a priori aim to discover the reason for the existence of our universe or to build theories of everything. Science proceeds in tiny steps, attempting to find explanations for the blue sky, the green leaves of plants, or the stretched, red-shifted light from distant galaxies. Sometimes those tiny steps build up to something rather grand, like a measurement of the age of the observable universe, but that's not what anyone set out to do. This is why science is more successful than any other form of human thought when applied to questions within its domain, which is the explanation of the natural world. It starts small and works its way slowly and methodically forwards, deepening our understanding in careful increments. Our chapter title, Why Are We Here?, might therefore appear to be unanswerable by science. It's too grand a question. But that may no longer be the case, because the careful steps are taking science into this territory, and the scientific language is now in place to at least address the question, what happened before the Big Bang? This is clearly a prerequisite for being able to make any meaningful attempt to address the reasons for our existence, although it is surely not sufficient. Immediately, I have to explain a semantic distinction before 1,000 philosophers throw their togas aside and prepare to engage in a naked yet civilized and eloquent battle of ideas. I am defining the term Big Bang as the astronomer Fred Hoyle originally introduced it into physics in 1949. It is to be understood as the beginning of the hot, dense state in which our observable universe once existed. Conventional cosmological theory, as described in Chapter 1, traces the evolution of the universe backwards in time, with conditions getting hotter and denser until the point where we are unsure of the correct rules of physics. Currently, this is earlier than approximately 10 to the minus 10 seconds, which is associated with the current power of the Large Hadron Collider. If the universe existed in some other form before the hot, dense state came into existence 13.798 billion years ago, then that's what I'm referring to as the time before the Big Bang. Science might accidentally wander into Leibniz's territory if, for example, this time before the Big Bang were discovered to be infinite, or that the state before the Big Bang was logically necessary and describable by current or yet-to-be-discovered laws of physics. Such a theory would also have to explain precisely all the properties of the universe we see today. From a scientific perspective, of course, we don't care about Leibniz. It is not the role of science to prove or disprove the existence of God. Rather, we are only interested in taking our careful steps backwards in time, as far as the evidence and theoretical understanding allow. The exciting thing is that developments in cosmology since the 1980s now point quite firmly towards the existence of a state before the Big Bang, as defined above, and that is primarily what this chapter is about. This chapter is also about you. I suspect most of us have mused about the question, why are we here? For some, the question and answer may be absolutely central to their lives. For others, myself included, it's something I used to think about on a hillside, desolate, beside a punctured bicycle, whilst wearing a second-hand overcoat I bought from Affleck's Palace. But my existentialism faded with my hair. Having said that, a little existentialism, like the Manchester rain, never did anyone any harm. So let's place ourselves at the centre of things for a while, and explore the immense contingency of our personal existence, as a warm-up for the much deeper problem of the origin of the universe itself. It's a pretty deep chapter, this, so put on unknown pleasures, grab a bottle of cheap cider, and let's get going. If, in a moment of solipsism, you decide to work out the odds of your own existence, you might come to the conclusion that you are astonishingly special. You began as a particular egg inside your mother, fertilized by a particular sperm from your father. There were 180 million sperm around that day, each with a different genetic code, only one of which became you in combination with one of your mother's million or so genetically unique eggs. So without going any further, you might feel lucky. If you chose to carry on, you might factor in the odds of your parents having sex on that particular day, because sperm are constantly manufactured. Then there are the odds of them meeting at all, and the odds of them being them. And whilst we're picking up increasing armfuls of odds at the 1 in 100 million level, recall from Chapter 1 that there exists an unbroken line of your ancestors stretching back over 3.8 billion years to Luca, the last universal common ancestor. if any one of those living things had died before it reproduced, you wouldn't exist. That's pretty lucky, but also completely devoid of any meaning at all. Yes, the odds of you existing are almost but not quite zero, but given the existence of the human race and a mechanism for procreation, someone has to be born. So whilst the probability of any given individual existing is tiny, it is inevitable that new babies will be born every day. Seen in this light, you are not special, and your existence in the grand scheme of things is entirely understandable. Time for Joy Division Insider. This demolition of your individual self-importance relied on the fact that a mechanism exists for the inevitable production of large numbers of human beings, given the important precondition that humans already exist. We've explored the road to human existence at length in the book already, and argued that complex multicellular life and intelligence at or beyond the level of humans may be rare in our universe. It's also clear that there are fundamental properties of the universe itself that are necessary for the existence of any form of life. The universe must live long enough and have the right properties for stars to form, and those stars must be capable of producing the chemical elements out of which living things are made, carbon being the most important. What do we mean by properties? We're back to the nature of the laws of physics once again, because they describe the behavior of matter and forces at the most fundamental level. The laws restrict the possible physical structures that are allowed to appear in the universe. And stars, planets, and human beings are all examples of such possible physical structures. Questions now naturally arise, more modest perhaps than our grand "why are we here" puzzle, but more amenable to scientific inquiry. How do the laws of nature allow for human beings to exist? And by how much could those laws vary before life could no longer exist in the universe? Let us begin in the spirit of taking small steps, with a brief summary of the known fundamental laws of nature. Attempting to describe the laws that govern the existence of everything from galaxies to human beings in a single paragraph of a book of a TV series might seem overly ambitious. It is at one level, otherwise everyone would complete physics, chemistry, and biology degree courses in an afternoon. What we can do, however, is to outline the known fundamental laws in a concise and accurate way. So let us do that. There are 12 known particles of matter. They are arranged into 3 families or generations. You are made out of particles in the first generation alone. Up quarks and down quarks bind together to make protons and neutrons, which in turn bind together to form your atomic nuclei. Your atoms are composed of electrons bound to those nuclei. Molecules, such as water and DNA, are built up out of collections of atoms bound together. That's all there is to you. 3 fundamental particles arranged into patterns. Particles called gauge bosons carry the forces of nature. There are 4 known fundamental forces: the strong and weak nuclear forces, electromagnetism, and gravity. To see how this all works, let's focus on the familiar electromagnetic force. Imagine an electron bound to the atomic nucleus of one of your atoms. How does that binding happen? The most fundamental description we have is that the electron can emit a photon, which you can think of as a particle of light. That photon can be absorbed by one of the quarks inside the nucleus, and this emission and absorption acts to assert a force between the electron and the quark. There is a vast number of ways in which the electrons and the quarks inside the nucleus can emit and absorb photons, and these all combine to keep the electron firmly glued to the nucleus. A similar picture can be applied to the quarks themselves. They also interact via the strong nuclear force by emitting and absorbing force-carrying particles called gluons. The strong nuclear force is the strongest known force, the clue is in the name, and binds the quarks together very tightly indeed. This is why the nucleus is significantly smaller and denser than the atom. Only quarks and gluons feel the strong nuclear force. Finally, there is the weak nuclear force. This is mediated by the exchange of the W and Z bosons. All known particles of matter feel the weak nuclear force, but it is extremely weak relative to the other two, which is why its action is unfamiliar, but not unimportant. The Sun would not shine without the weak nuclear force, which allows protons to convert into neutrons, or more precisely, up quarks into down quarks, which has the same result. This is the first step in the nuclear burning of hydrogen into helium, the source of the Sun's energy. During the conversion of a proton into a neutron, an anti-electron neutrino is produced along with an electron. The neutrino is the remaining particle in the first generation we haven't discussed yet. Because neutrinos only interact via the weak nuclear force, we are oblivious to them in everyday life. This is fortunate because there are approximately 60 billion per square centimetre per second passing through your head from the nuclear reactions in the Sun. If the weak force were a little stronger, you'd get a hell of a headache. Actually, you wouldn't, because you wouldn't exist. And this foreshadows the subject of the fine-tuning of the laws of nature we will undertake later in this chapter. The one remaining type of particle is the Higgs boson. Empty space isn't empty, but is jammed full of Higgs particles. All the known particles, apart from the photon and the gluons, which are massless, interact with the Higgs particles, zigzagging through space and acquiring mass in the process. This is the counterintuitive picture that was confirmed by the discovery of the Higgs boson at CERN's Large Hadron Collider in 2012. 2 further generations of matter particles have been discovered. They are identical to the first generation, except that the particles are more massive because they interact with Higgs particles more strongly. The muon, for example, is a more massive version of the familiar electron. The reason for their existence is unknown. This is all there is in terms of the description of the fundamental ingredients of the universe. There are almost certainly other particles out there somewhere. The dark matter that dominates over normal matter in the universe by a factor of 5 to 1 is probably in the form of a new type of particle which we may discover at the Large Hadron Collider, or a future particle accelerator. The evidence for dark matter is very strong, and comes from astronomical observations of galaxy rotation speeds, galaxy formation models, and the cosmic microwave background radiation that we met in Chapter 1 and will meet again later in this chapter. But because we don't know what form the dark matter takes, we are not able to incorporate it into our list. The mathematical framework used to describe all the known particles and forces other than gravity is known as quantum field theory. It's a series of rules that allows the probability of any particular process occurring to be calculated. The whole thing can be described in one single equation, known as the Standard Model Lagrangian. Here it is. L equals -1/4 W mu nu W superscript mu nu, -1/4 B mu nu B superscript mu nu, -1/4 G mu nu G superscript mu nu, plus psi bar j gamma mu bracket I delta mu minus G tau j dot W mu minus G dash yj B mu minus G s T j dot G mu bracket psi j plus d mu phi squared plus mu squared phi squared minus lambda phi to the 4th minus bracket yj psi bar jl phi psi jr plus y dash j psi bar jl phi c psi jr plus conjugate close bracket. It takes a lot of work to use this piece of mathematics to make predictions, but the predictions are spectacularly accurate and agree with every experimental measurement ever made in laboratories on Earth. This equation even predicted the existence of the Higgs particle. That's how good it is. It probably looks like a set of squiggles unless you're a professional physicist, but in fact it isn't too difficult to interpret, so let's just dig a little deeper. The 12 matter particles are all hidden away in the symbol psi j. The Standard Model is a quantum field theory, because particles are represented by objects known as quantum fields. There's an electron field, an up quark field, a Higgs field, and so on. The particles themselves can be thought of as localized vibrations in these fields, which span the whole of space. Fields will be important to us later, when we'll want to think about a certain type of field that may have appeared in the very early universe, known as a scalar field. The Higgs field is an example of a scalar field. The mathematical terms between the two psi j's on the second line describe the forces and how they cause the particles to interact. The forces are also represented by quantum fields. The term -GSTJ.g mu, for example, describes the gluon field that allows the quarks in the psi-j terms to bind together into protons and neutrons. The term GS is known as the strong coupling constant. It's a fundamental property of our universe that encodes the strength of the strong nuclear force. Each of the forces has one of these coupling constants. We'll want to discuss these coupling constants later because they define what our universe is like and what is allowed to exist within it. The last two lines deal with the Higgs boson. The strength of the interaction between a matter particle and the Higgs field is contained in the YJ terms, which are known as Yukawa couplings. These must be inserted to produce the observed masses of the particles of matter. That's pretty much it. Here ends our crash course on particle physics. The central point is that there exists a remarkably economical description of everything other than gravity, and it is contained within the Standard Model. We considered the gravitational force in some detail in Chapter 1. It's described by Einstein's theory of general relativity, which is what physicists call a classical theory. There are no force-carrying particles in Einstein's theory. Instead, the force is described in terms of the curvature of space-time by matter and energy, and the response of particles to that curvature. A quantum theory of gravity, which we have already noted will be necessary to describe the first fleeting moments in the history of the universe, would involve the exchange of particles known as gravitons, but as yet nobody's worked out how to construct such a description. This is why Einstein's theory remains the only fundamental non-quantum theory we have. For completeness, let's refresh our memory of Einstein's theory of general relativity. G mu nu equals 8 pi gt mu nu. General relativity, like the Standard Model, contains a coupling constant encoding the measured strength of gravity, G, Newton's gravitational constant. The amount of dark energy is inserted by hand, in accord with observations, as was the case for the strengths of the forces and the masses of the particles in the Standard Model. General relativity and the Standard Model are the rules of the game. They contain all our knowledge of the way that nature behaves at the most fundamental level. They also contain almost all the properties of our universe that we think of as fundamental. The speed of light, the strength of the forces, the masses of the particles, encoded as the strength of their interaction with the Higgs bosons via the Yukawa couplings, and the amount of dark energy are all in these equations. In principle, any known physical process can be described by them. This is the current state of the art, but it doesn't mean that we know how everything works and can all retire by a long shot or a well-timed cover drive. Most games are skin deep, but cricket goes to the bone. John Arlott and Fred Truman. I timed a cover drive properly once when I was 14 years old playing at Hollingwood Cricket Club near Oldham. Front foot, head in line with the ball, sweet sound of the middle, 4 runs. I know what I have to do, but I never did it quite as well again. Cricket is an art built on simple rules, first codified by the members of the Marylebone Cricket Club on the 30th of May 1788. A significant date in world history, according to historians with good taste. Those original laws still form the basis of the game today. There are 42 of them, and they define the framework within which each game evolves. Yet, despite the rigid framework, no two games are ever alike. The temperature and humidity of the air, a light scatter of dew on the grass, the height of grass on the wicket, and hundreds of other factors will subtly shift and change throughout the game. More importantly, the players and umpires are each complex biological systems whose behavior is far from predictable, with the exception of Geoffrey Boycott. The presence of so many variables makes the number of possible permutations effectively infinite, which is why cricket is the most interesting of human pursuits, excluding science, sex, and wine tasting. Knowledge of the laws is therefore insufficient to characterize the infinite magic of the game. This is also true for the universe. The laws of nature define the framework within which things happen, but do not ensure that everything that can happen will happen in a finite universe. That rather obscure finite caveat will be important for us later on. Virtually all of science beyond particle physics and theoretical cosmology is concerned with the complex outcomes allowed by the laws, rather than the laws themselves. And in a certain sense, our solipsistic initial question, why are we here, is also a question about outcomes rather than laws. The answer to the question, why did England beat Australia in the Great Ashes series of 2005, is not to be found in the MCC rulebook. And similarly, the natural world that emerges from the Standard Model and general relativity cannot be understood simply by discovering the laws themselves. It's worth noting that the laws of nature were not written by the MCC or even the committee of the Yorkshire County Cricket Club. We had to work them out by watching the game of the universe unfold, which makes their discovery even more wonderful. Imagine how many matches would have to be viewed in order to deduce the laws of cricket, including but not restricted to the Duckworth-Lewis method. The great achievement of 21st century science is that we've managed to work out the laws of nature by doing just this, observing many millions of complex outcomes and working out what the underlying laws are. The Standard Model, then, cannot be used to describe complex emergent systems such as living things. No biologist would attempt to understand the way that ATP is produced inside cells using the Standard Model Lagrangian, and no telecommunications engineer would use it to design an optical fiber. They wouldn't want to, even if they could. You wouldn't gain any insight into how a car engine works by starting off with a description of its constituent subatomic particles and their interactions. So whilst it's important that we have a detailed model of nature at the level of the known fundamental building blocks, we must also understand how the complexity we observe around us emerges from these simple laws, if we're to make progress with our difficult why question. On Monday the 27th of March 1905 at 8:30 a.m., William Jones arrived at Chapman's Oil and Colour Shop on Deptford High Street, ready for a day's work. Jones normally arrived a few minutes after the shop manager Thomas Farrow had raised the shutters. On this particular Monday, however, the shutters were down. Farrow lived with his wife Anne above the shop, but no matter how hard Jones knocked on their door, there was no response. This was a most unusual start to the day, and his concern increased when a glimpse through a window revealed chairs strewn across the floor of the normally tidy shop. Jones and another local resident forced the door, to be confronted by Farrow lying dead in a pool of blood. Anne had been similarly bludgeoned in her bed, although she clung to life for 4 more days without regaining consciousness. Such scenes were not uncommon in Edwardian London. The reason that this crime is of note is because it was the first in the world to use a new technology to catch and convict the killers. On an inner surface of the empty cash box, the police noticed a fingerprint. They already had a suspect, a local man named Alfred Stratton, who was arrested 3 days later along with his brother Albert. The Strattons' fingerprints were taken, and a positive match was made between the cash box print and Alfred Stratton's right thumb. Although fingerprints were never used before in a murder case, expert witnesses convinced the jury that the complex patterns of the cash box fingerprint could only belong to Alfred Stratton. The jury took just 2 hours to find the Stratton brothers guilty of murder, and the pair was sentenced to death by hanging, with justice swiftly dispatched on the 23rd of May. Take a look at your fingerprints now. There is seemingly endless complexity in the swirls and ridges. Since every human being carries different fingerprints on the hands and the soles of their feet, which aren't fingerprints but there isn't a word for them, the size of database required to characterize every human being's fingerprints would be colossal. One of the most important properties of nature, however, is that the blueprints for the construction of the natural world are far simpler than the natural world itself. In modern language, there is a tremendous amount of data compression going on. The instructions to create fingerprints are far simpler than the fingerprints themselves, and more than that, the same instructions run over and over again from slightly different starting points in the embryonic stage of our development always lead to different fingerprints. This behavior shouldn't come as a surprise. The sweep of desert dunes or the patterns in summer clouds are all described by a handful of simple laws governing how sand grains or water droplets behave when agitated by shifting air currents, buffeted by chaotic thermals and winds, and reordered by the action of the forces of nature. And yet from a simple recipe, complexity emerges. The quest to understand how the boundless variety of the natural world emerges from underlying simplicity has been a central theme in philosophical and scientific thought. Plato attempted to cast the world available to our senses as the distorted and imperfect shadow of an underlying reality of perfect forms accessible through reason alone. The modern expression of Plato's ethereal dualism was captured eloquently by Galileo 500 years ago. The book of nature is written in the language of mathematics. The challenge is not only to discern the underlying mathematical behavior of the world, but also to work back upwards along the chain of complexity, to explain how those forms that Plato would have defined as imperfect arise from the assumed lower-level perfection. A rather beautiful early example of this quest is provided by Galileo's illustrious contemporary, Johannes Kepler. A brief history of the snowflake. Johannes Kepler is rightly best known for his laws of planetary motion that paved the way for Newton to write Principia. Hidden within his illustrious CV, however, is a publication that had a rather more whimsical, earthbound ambition. 2 years after publishing the first part of Astronomia Nova in 1609, Kepler published a short 24-page paper entitled De Nive Sexangula, on the six-cornered snowflake. It is a beautiful example of a curious scientific mind at work. In the dark December of 1610, Kepler was walking across the Charles Bridge in Prague when a snowflake fell on the lapel of his coat. In the freezing night he stopped and wondered why this ephemeral sliver of ice possessed a six-sided structure, in common with all other snowflakes, notwithstanding their seemingly infinite variation. Others had noticed this symmetry before, but Kepler realized that the symmetry of a snowflake must be a reflection of the deeper natural processes that underlie its formation. Since it always happens when it begins to snow that the first particles of snow adopt the shape of small six-cornered stars, there must be a particular cause, wrote Kepler. For if it happened by chance, why would they always fall with 6 corners and not with 5 or 7? Kepler hypothesized that this symmetry must be due to the nature of the fundamental building blocks of snowflakes. This stacking of frozen globules, as he referred to it, must be the most efficient way of building a snowflake from the smallest natural unit of a liquid like water. To my mind, this is a leap of genius, and a tremendously modern way of thinking about physics. The study of symmetry in nature lies at the very heart of the Standard Model, and abstract symmetries known as gauge symmetries are now known to be the origin of the forces of nature. This is why the force-carrying particles in the Standard Model are known as gauge bosons. Kepler was searching for the atomic structure of snow before we knew atoms existed, motivated by the observation of a symmetry in nature, the six-sided shape of all snowflakes. The inspiration for this idea, which is way ahead of its time, came from a peculiar source. In the years leading up to the publication of De Nive Sexangula, Kepler had been in communication with Thomas Harriot, an English mathematician and explorer. Amongst multiple claims to fame, Harriot was the navigator on one of Sir Walter Raleigh's voyages to the New World, and had been asked to solve a seemingly simple mathematical problem. Raleigh wanted to know how best to stack cannonballs to make the most efficient use of the limited space on the ship's deck. Harriot was driven to explore the mathematical principles of sphere packing, which in turn led him to develop an embryonic model of atomic theory and inspire Kepler's consideration of the structure of snowflakes. Kepler imagined replacing cannonballs with globules of ice, and supposed that the most efficient arrangement creating the greatest density of globules was the six-sided hexagonal form he observed in the snowflake on his shoulder. Kepler also observed hexagonal structures across the natural world, from beehives to pomegranates and snowflakes, and presumed that there must be some deeper reason for its ubiquity. Hexagonal packing, as Kepler referred to it, must be the tightest possible, so that in no other arrangement could more pellets be stuffed into the same container. This became known as the Kepler conjecture. It took almost 400 years to prove Kepler's conjecture, and this required the help of a 1990s supercomputer. Despite the time lag, Kepler's work had a more immediate impact, inspiring the beginnings of modern crystallography that led eventually to the discovery of the structure of DNA. What a lovely example of serendipity coupled with curiosity and a sprinkling of genius. From cannonballs to snowflakes to the code of life. As for Kepler's original thought on that frozen bridge, he never found the connection between the underlying structure of his ice globules and the hexagonal symmetry of snowflakes. Even though he realized that the regular patterns must reveal something about the shape of the building blocks of snowflakes and the details of the packing, he couldn't explain the ornate complexity or the flatness of the structure. Instead, he acknowledged his failure with the good grace of a true scientist. "I have knocked on the doors of chemistry," he writes at the end of his paper, "and seeing how much remains to be said on this subject before we know the cause, I would rather hear what you think, my most ingenious man, than wear myself out with further discussion." 3.5 centuries later, Japanese physicist Yukichiro Nakayara made the first artificial snowflakes in a laboratory. Writing in 1954, he describes a process that begins not with the snowflake itself, but with smaller substructures called snow crystals, which are in turn built up from collections of ice crystals, the globules Kepler was searching for. The hexagonal packing that Kepler suspected to be the origin of the snowflake symmetry begins with the formation of these ice crystals, when water molecules link together in a hexagonal structure via hydrogen bonds. Hydrogen bonding occurs because of the structure of the water molecules themselves, with a greedy oxygen atom hungry for electrons grabbing them off two hydrogen atoms, forming covalent bonds that lock the H2O molecules together, leaving a residual positive electrical charge in the vicinity of the two protons and a negative charge in the vicinity of the oxygen. This slight separation of charge in the water molecules allows them to bind together into larger structures through the mutual attraction and repulsion of the electrical charges, just as an electron is bound into its position around an atomic nucleus. The entire configuration, including the structure of the oxygen nucleus and the single protons that comprise the hydrogen nuclei, can be predicted in principle by the standard model of particle physics. Yet the details of any particular snowflake are beyond computation, because the seemingly infinite variety reflects the precise history of the snowflake itself. Once ice crystals form as agglomerations of water molecules held together by hydrogen bonds, they cluster around dust particles in the air, building on their underlying hexagonal symmetry to form larger snow crystals. As the crystals begin the long journey down to Earth, they join in ever larger, more complex combinations, shaped by endless variations of air temperature, wind patterns, and humidity, into myriad unique forms. The symmetry is all that remains of the simplicity, and it takes a careful and patient eye to see the endless variation for what it is, a reflection of the complex history of the snowflake, convoluted with the underlying simplicity of the laws of nature. The most vivid example of emergent complexity, and the closest to our hearts, is life. As we discussed in Chapter 2, the origin of life on Earth has a sense of inevitability about it, because its basic processes are chemical reactions that will proceed given the right conditions. Those conditions were present in the oceans of Earth 3.8 billion years ago, possibly earlier, and they led to the emergence of single-celled organisms. The fateful encounter which produced the eukaryotic cell around 2 billion years ago looks rather more like blind chance, but it happened here and laid the foundations for the Cambrian explosion 530 million years ago. There is a bit of hand-waving going on here, though, and to make a more persuasive case that all the complexity of Darwin's endless forms most beautiful can at least in principle emerge from simple underlying laws, one more example is in order. Perhaps the most beautiful manifestation of the artful complexity of nature can be found in the spots, stripes, and patterns on the coats and skin of living things. Emergent pattern writ large across venomous striped surgeonfish, emperor angelfish, zebra swallow-tailed butterflies, and the big cats of Africa and Asia. Everyone agrees that these patterns evolved as a result of natural selection of one form or another, and the raw material for the variation was provided by random mutations in the genetic code. But a very challenging scientific question of fundamental importance in modern biology is precisely how patterns such as these appear. How the leopard got its spots. Zebra moved away to some little thorn bushes where the sunlight fell all stripy, and the giraffe moved off to some tallish trees where the shadows fell all blotchy. "Now watch," said the zebra and the giraffe. "This is the way it's done. 1, 2, 3, and where's your breakfast?" All they could see were stripy shadows and blotched shadows in the forest, but never a sign of zebra and giraffe. That's a trick worth learning. Take a lesson from it, leopard. Then the Ethiopian put his 5 fingers close together and pressed them all over the leopard, and wherever the 5 fingers touched, they left 5 black marks all close together. Rudyard Kipling's Just So story, How the Leopard Got His Spots, tells the story of an Ethiopian man and a leopard. They went hunting together, but one day the man noticed that the leopard wasn't very successful. The reason, he deduced, was that the leopard had a plain, sandy coat, whereas all the other animals had camouflage. "That's a trick worth learning, leopard," he said, taking his fingers and thumb and pressing them into the leopard's coat to give it the distinctive 5-pointed pattern. If you don't believe in evolution by natural selection, this is the most plausible theory open to you. If you do, then what remains is to identify the mechanism by which the pattern is formed. The answer might appear to be solely a matter of genetics, but genes are not the whole story. It would take a terrific amount of information to instruct every single cell to colour itself according to its position on the leopard's skin, and this is indeed not what is done. Nature is frugal and deploys a much more efficient mechanism for producing camouflage patterns. As with so many things in this book, I get to say yet again that this is an active area of research, and therefore exciting. The reason for the attention is that camouflage patterns on the skin self-organize during the development of the embryo, and embryonic development is of course fundamental to an understanding of biology. In the case of the leopard, it is thought, though not proven, that the camouflage is an example of a Turing pattern, named after the great Bletchley Park codebreaker and mathematician Alan Turing. In 1952, Turing became interested in morphogenesis, the process by which an animal develops its shape and patterning. He was particularly interested in the mathematics behind regularly repeating patterns in nature, such as the Fibonacci numbers and golden ratio in the leaf arrangements of plants and the scales of pineapples, and the appearance of camouflage patterns such as the tiger's stripes and the leopard's spots. Turing's influential and groundbreaking paper, The Chemical Basis of Morphogenesis, published in March 1952, begins with a simple statement. It is suggested that a system of chemical substances called morphogens, reacting together and diffusing through a tissue, is adequate to account for the main phenomena of morphogenesis. These systems are known as reaction-diffusion systems, and they can produce patterns from a featureless initial mixture if the two reactants diffuse at different speeds. There's a nice analogy that describes how such a system can work. This analogy was published by J.D. Murray in Notices of the AMS, June-July 2012. Why are there no three-headed monsters? Mathematical modelling in biology. Imagine a dry field full of grasshoppers. They are strange grasshoppers because when they get warm, they sweat, generating a large amount of moisture. Now imagine that the field is set alight in several different places. The flames will spread at some fixed speed, and if there were no grasshoppers, the whole field would be charred. As the flames approach the grasshoppers, however, they will start to sweat, dampening the grass behind them and inhibiting the flames as they hop away ahead of the approaching flames. Depending on the different parameters, including the different speeds of the flames and the grasshoppers and the amount of sweat necessary to quell the advancing flames, a Turing pattern can be formed, with areas of charred grass and green areas where the inhibiting grasshoppers prevented the fire from taking hold. It is thought that the leopard gets its spots in this way during embryonic development. An activator chemical, fire, spreads through the skin and stimulates the production of the dark pigmented spots, charred grass, but is inhibited by another chemical, sweating grasshoppers, spreading with a higher diffusion rate. The precise pattern produced depends on the constants of nature of the system, such as the speeds at which the chemicals diffuse, and on what a mathematician would call the boundary conditions, the size and geometry of the grassy field in our analogy. In embryonic development, it is the size and shape of the embryo when the reaction diffusion begins that determines the type of pattern produced. A long and thin domain produces stripes. A domain that is too small or too large produces uniform color. In between can be found the distinctive coat patterns of cows, giraffe, cheetah, and of course the leopard. Computer simulations of Turing patterns have been remarkably successful, not only in describing the generic features, particularly of mammalian coats, but also of some of the interesting details seen in nature. For example, the mathematical models predict that it is possible for spotted animals to have striped tails, as cheetahs do, but not for striped animals to have spotted tails, and indeed no such examples exist. Kepler's snowflakes and the leopard spots are two picturesque examples of emergent complexity, the appearance of intricate, ordered patterns from the action of simple underlying laws. Nature contains systems far more complex than these, of course, you being a case in point. But to return to the question at the beginning of our solipsistic meander, the reason that you exist, given the laws of nature, is that you are allowed to. Just as all snowflakes and all leopards' coats are unique in detail because of their individual formation histories, so you are unique because no two human beings share a common history. But we wouldn't read any deep meaning into the existence of one particular snowflake in a snowstorm, and the same is true for you. Our focus should therefore shift from trying to explain the appearance of humans, or our planet, or even our galaxy, to a rather deeper question: the origin of the whole framework, of space-time and the laws that govern it, and the allowed structures within it. What properties of the laws themselves are essential for galaxies, planets, and human beings to exist? After all, as we've noted, the laws might be mathematically elegant and economical, but they do contain a whole host of seemingly randomly chosen numbers discovered by experimental observation and with no known rhyme or reason to them. The constants of nature, such as the strength of the forces, the masses of the particles, and the amount of dark energy in the universe. How dependent is our existence on these fundamental numbers? Our universe appears to be made for us. We live on a perfect planet, orbiting around a perfect star. This is, of course, content-free whimsy. The argument is backwards. We have to be a perfect fit for the planet because we evolved on it. But there are interesting questions when we look deeper into the laws of nature and ask what properties they must have to support a life in the universe. Take the existence of stars, for example. Stars like the Sun burn hydrogen into helium in their cores. This process involves all four forces of nature working together. Gravity kicks it all off by causing clouds of dust and gas to collapse. As the clouds collapse, they get denser and hotter, until the conditions are just right for nuclear fusion to occur. Fusion starts by turning protons into neutrons through the action of the weak nuclear force. The strong nuclear force binds the protons and neutrons together into a helium nucleus, which in itself exists on account of the delicate balance between the strong nuclear force holding it together and the electromagnetic force trying to blow it apart because of electrically charged protons. When stars run out of hydrogen fuel, they perform another series of equally precarious nuclear reactions to build carbon, oxygen, and the other heavy elements essential for the existence of life. What happens if the strength of these forces, those fundamental constants of nature we met earlier in the chapter, are varied a bit? There are many examples of apparent fine-tuning in nature. If protons were 0.2% more massive, then they would be unstable and decay into neutrons. That would certainly put an end to life in the universe because there would be no atoms. The proton mass is ultimately set by the details of the strong and electromagnetic forces and by the masses of the constituent quarks, which are set by the Yukawa couplings to the Higgs field in the Standard Model. There really isn't much freedom at all. The mother of all fine tunes, however, is the value of our old friend dark energy, the thing that is causing our universe to gently accelerate in its expansion. Although dark energy contributes 68% of the energy density of the universe, the amount of dark energy in a given volume of space is actually small, very small, 10 to the minus 27 kilograms per cubic meter to be precise. The point is that every cubic meter of our universe has this amount of dark energy in it, and that adds up. Explaining why dark energy has this small but non-zero value is one of the great problems in cosmology, not least because if a particle physicist sits down with a quantum field theory and decides to calculate how big it should be, it turns out that it would be more naturally of the order of 10 to the 97 kilograms per cubic meter. That's a lot bigger than 10 to the minus 27 kilograms per cubic meter. Over a million times bigger, in fact. That's embarrassing for the particle physicists, of course, but from the perspective of fine-tuning, it's even worse. If the value of dark energy were only 50 times larger than it is in our universe, rather than somewhere else in this immensely large theoretical range, then it would have become dominant in the universe around 1 billion years after the Big Bang, during the time that the first galaxies were forming. Because dark energy acts to accelerate the universe's expansion and dilute matter and dark matter, gravity would have lost the battle in such a universe, and no galaxies or stars or planets or life would exist. What could possibly account for this incredible piece of luck? It can't really be luck. The odds are too long by a Jeffrey Boycott innings. One possibility is that there is some as yet unknown physical law or symmetry that guarantees that the amount of dark energy will be very close to, but not quite, zero. This is certainly possible, and there are physicists who believe that this may be the case. The other possibility, which was raised by one of the fathers of the Standard Model, Steven Weinberg, is that the value of dark energy is anthropically selected. Anthropic arguments appear at one level to be a statement of the obvious. The properties of the universe must be such that human beings can exist, because human beings do exist. This is, of course, true, but it is fairly devoid of content from a physical perspective, unless there is some way in which all possible values of dark energy, and indeed all the other constants of nature, are realized somewhere. If, for example, there exists a vast, possibly infinite swathe of different domains in the universe, or indeed an infinity of other universes, each with a different amount of dark energy selected by some mechanism from the span of allowed values, then we would indeed have a valid anthropic explanation for our special human universe. It must exist because they all do, and of course we appear in the one that permits our existence. But surely it makes no sense to take refuge in a vast infinity of universes to explain our existence. Absolutely correct. If that's why the idea is introduced, it's no better than a God of the Gaps explanation. If, however, there was some other reason, based on observations and theoretical understanding, that suggested an infinity of universes, then such an anthropic explanation for our perfect human universe would be admissible. Remarkably, and that remarkably overused word is appropriate for once, this outlandish suggestion is a widely held view amongst many cosmologists. If we look at our universe on the largest distance scales, by which I mean at distance scales far larger than the size of single galaxies, it has a number of properties that any theory of its origin has to explain. The most precise picture of the young universe we have is the photograph of the cosmic microwave background radiation, CMB, taken by the Planck satellite. This is the afterglow of the Big Bang, a photograph of the universe as it was 380,000 years after the initial hot, dense phase, when the expansion had cooled things down sufficiently for atoms to form. The most obvious feature of the CMB is that it's extremely uniform, glowing at a temperature of 2.72548 degrees above absolute zero, with small fluctuations at the level of 1 part in 100,000. Those very tiny temperature differences are represented by the colors in the photograph. This uniformity is extremely difficult to explain in the standard Big Bang model for a simple reason. Our observable universe today is 90 billion light-years across. This means that if we look out to the CMB from opposite sides of the Earth, we are looking at two glowing parts of the ancient sky that are now separated by 90 billion light-years. The universe, however, is only 13.8 billion years old, which means that light, the fastest thing there is, has only had time to travel 13.8 billion light-years. Two opposite parts of the CMB could therefore never have been in contact with each other in the standard Big Bang model. And there is absolutely no reason why they should be almost precisely the same temperature. I've emphasized almost in the previous sentence because, as we noted, there are very slight variations in the CMB at the level of 1 part in 100,000, and these are very important. The universe was never completely smooth and uniform everywhere, and these variations in density are encoded into the CMB as differences in temperature. The regions of slightly greater density ultimately seeded the formation of the galaxies, and so without them, we wouldn't exist. What caused these small variations in the otherwise ultra-smooth early universe? Another fundamental property of the universe that is difficult to explain is its curvature, or lack of it, which can also be measured from the CMB. Space appears to be absolutely flat, a veritable ice rink. Recall from Chapter 1 that the shape of space is related to the density and distribution of matter and energy in the universe through Einstein's equations. In the standard Big Bang theory, the universe doesn't have to be flat. In fact, it requires a great deal of fine-tuning to keep it flat over 13.8 billion years of cosmic evolution. Instead, the radius of curvature is measured to be much greater than the radius of the observable universe, more than 60 orders of magnitude larger. That's a big problem. In the early 1980s, the need to explain these and other properties of the observable universe led a group of Russian and American physicists to propose a radical idea. The modern version, the best-known proponents of which are Alan Guth, Andrei Linde, and Alexei Starobinsky, is known as the theory of inflation. We'll describe a particular version of inflation below, driven by something called a scalar field, which was first described by Andrei Linde. Space-time existed before the Big Bang, and for at least some of that time was described by Einstein's theory of general relativity and a quantum field theory like the Standard Model. The central idea in quantum theory is that anything that can happen does happen. Everything that is not explicitly ruled out by the laws of nature will happen given enough time. One of the types of things permitted to exist in quantum field theory are scalar fields. We've met an example of a scalar field earlier in the chapter in the guise of the Higgs field, which we know to exist because we've measured it at the Large Hadron Collider. Scalar fields have the property that they can cause space to expand exponentially fast. We touched on such a scenario in Chapter 1 without being explicit about the mechanism. It is the de Sitter's matterless solution to Einstein's field equations first discovered in 1917. Given general relativity and quantum field theory, therefore, it must be the case that scalar fields will fluctuate into existence in such a way that an exponential expansion of spacetime is triggered. In this exponential phase, space-time expands faster than the speed of light. This might sound problematic if you know some relativity, but it isn't. The universal speed limit exists for particles moving through space-time, but does not apply for the expansion of space-time itself. In a tiny fraction of a second, around 10 to the minus 35 seconds in fact, an exponential expansion of this type can inflate a piece of space-time as tiny as the Planck length to a quite mind-boggling size, trillions of times larger than the observable universe. Any pre-existing curvature is completely washed out, leading to a flat observable universe. It's like looking at a square centimetre-sized piece of the surface of a balloon of a light year in radius. You won't see any curvature, no matter how hard you try. Likewise, any variations in density will be washed out, leading to the smooth and uniform appearance of the CMB. Perhaps the greatest triumph of inflationary models such as these, however, is that they don't predict a completely uniform, homogeneous and isotropic universe. Quantum theory doesn't allow for absolute uniformity. Empty space is never empty, but a fizzing, shifting soup of all possible quantum fields. Like the surface of a stormy ocean, waves in the fields are constantly rising and falling, and the exponential expansion can freeze these undulations into the universe. Remarkably, when calculations using the known laws of quantum theory are carried out, the sort of density fluctuations that result from such a mechanism are precisely of the form seen in the CMB. These quantum fluctuations are the seeds of the galaxies, and therefore the seeds of our existence, frozen into the oldest light in the cosmos, and photographed by a satellite built by the people of Earth 13.8 billion years later. Inflation in this guise explains the observable properties of our universe, and in particular all the details of the CMB, which has been measured to high accuracy. This is why it is currently widely accepted as an essential ingredient by many cosmologists. As if this wasn't enough to get excited about, however, there is much more. One obvious question that arises is this: if inflation gets going, how does it stop? The answer is that inflation stops completely naturally, but with a fascinating twist that drives right to the heart of our "why are we here" question. The scalar field driving inflation fluctuates up and down in accord with the laws of quantum theory, just like the waves on the surface of an ocean. If the energy stored in the field is high enough, inflation begins. One might expect that such a rapid expansion would dilute the energy extremely rapidly, causing inflation to stop. But scalar fields have the interesting property that their energy density can stay relatively constant as space expands. You can think of the expanding space as doing work on the field, pumping energy into it and keeping its level high. And in turn, the high level of the field's energy continues to drive the expansion. This might sound like the ultimate free lunch, and in a sense it is, almost, although gradually the energy will become diluted and decay away. The time this takes depends on the size of the initial fluctuation in the field and the details of the field itself, but in general, the higher the initial energy, the longer the field takes to fall in value as the expansion continues. An analogy often used to picture this scenario is to imagine a ball rolling down the side of a valley. The height of the ball up the valley side represents the energy density of the scalar field. When the ball is high up, the energy in the field is high, driving the inflationary expansion. As the ball rolls slowly down the valley, the energy reduces and inflation turns off. At the valley floor, the ball oscillates back and forth until it comes to rest. The scalar field likewise oscillates, and in doing so, dumps its energy into the universe in the form of particles. In so doing, it creates a hot, dense soup, which we identify as the Big Bang. In other words, inflation ends naturally, and the standard Big Bang follows. The decay of the scalar field that drove inflation is the cause of the Big Bang. Let us step back a moment and recap with broad brushstrokes, because we seem to be wandering onto Leibniz's territory, and that's an astonishing place for physics to have arrived at. Our claim is that there exists a quantum field that causes the universe to expand exponentially fast for some period of time, and in doing so, produces all the features of the universe we observe today, including the existence of galaxies and the matter out of which they are made. This is a triumph, and is now part of cosmology textbooks. Before the Big Bang, there was inflation. Fine, our philosopher friends would say. But what happened before inflation? Here we must leave the textbooks and become a little more speculative, but not too speculative. We're still going to be working within the domain of mainstream physics. There is an extension of what we might term standard inflationary theory. It's known as eternal inflation. Put simply, there seems to be no reason why inflation should stop everywhere at the same time. There should always be regions of the universe where the scalar field fluctuates to such high values that the exponential expansion continues, and these regions will always come to dominate the universe, however rare they may be, because they are exponentially expanding. Where inflation stops, Big Bangs herald the beginning of more sedately expanding regions like ours, but elsewhere, there is an ever-growing exponentially expanding universe, constantly spawning an infinity of Big Bangs. This theory, known as eternal inflation, leads to an infinite, immortal multiverse, growing fractal-like without end. This is truly mind-numbing, but we must emphasize that it is an entirely natural extension of standard inflationary cosmology. Eternal inflation opens up even more exciting possibilities. As we discussed above, one of the great mysteries in physics today is the origin of the constants of nature, such as the strength of gravity, the masses of the particles, and the value of dark energy. These values appear to be fine-tuned for the existence of life, and understanding where they come from is a prerequisite for understanding our existence. In eternal inflationary models, each mini-universe can have different values of these constants, and different effective laws of physics. The word effective is important. The idea is that there is some overarching framework out of which our laws and the constants of nature are selected randomly. If this is correct, then each of the infinite number of mini-universes that branch off the fractal inflationary multiverse can have different effective laws of physics, and all possible combinations will be realized somewhere. No matter how fine-tuned our laws appear for the existence of life, it is inevitable that such mini-universes as ours will exist, and there will be an infinite number of each possible set of combinations. There is no fine-tuning problem. Given the multiverse, we are inevitable. This is reminiscent of our rejection of your own personal uniqueness whilst listening to Joy Division at the beginning of the chapter. Yes, in isolation, the odds of you existing are almost vanishingly small. But given a mechanism for producing human beings, babies are born all the time, and their existence is not surprising. Here we have a mechanism for producing universes. And with an even greater statistical sledgehammer, the mechanism doesn't simply produce a few billion of them, it produces a potentially infinite number. This is a quite stunning theoretical model, and I understand that it sounds like wild speculation. It isn't, though. Inflation is probably correct in some form, in the sense that before what we call the Big Bang, there was an exponential expansion of space-time. Scalar fields, which are known to exist, have the correct properties to drive such an expansion, although there are other theoretical models of inflation as well. Theoretical physicists studying inflationary models have discovered that almost all of them are eternal, in the sense that they stop inflating in patches rather than all at once. This means that the potential for creating universes in the guise of inflation is always expanding faster than it is decaying away, and it will therefore never stop. We live in an infinite, eternal, fractal multiverse, comprised of an infinite number of universes like ours, alongside an infinite number of universes with different physical laws. We exist because it is inevitable. Almost. There is one very important caveat to this picture. Recent research suggests that eternal inflationary models may be eternal in the future, but not in the past. They never stop, but they may have to start. I can't give you a definitive answer to this ultimate question because nobody yet knows. I can quote from André Linde's recent review of inflationary cosmology, Inflationary Cosmology After Planck, 2013. In other words, there was a beginning for each part of the universe, and there will be an end for inflation at any particular point. But there will be no end for the evolution of the universe as a whole in the eternal inflation scenario. And at present, we do not know whether there was a single beginning of the evolution of the universe as a whole at some moment t equals 0, which was traditionally associated with the Big Bang. And so we reach the end. Defining the Big Bang as the initial hot, dense phase of our observable universe that gave rise to the CMB 380,000 years later, we understand what happened before. There was a period of inflationary expansion, which could have been driven by a scalar field in accord with the known laws of physics. That inflationary expansion is probably still going on somewhere, spawning an incalculable number of universes as we speak, and it will continue doing this forever. We live in an eternal universe, in which everything that can happen does happen. And we are one of the things that can happen. Did the whole universe have a beginning, an essential external cause in the spirit of Leibniz's God? We still don't know. Possibly there was a mother of all Big Bangs, and if so, we will certainly need a quantum theory of gravity to say anything more. What does this mean? The wonderful thing for me is that nobody knows, because the philosophical and indeed theological consequences of eternal inflation have not been widely debated and discussed. My hope is that in trying to summarize the issues regrettably briefly and necessarily superficially in the television series, and in a little more depth here, these ideas will be accessible to a wider audience and stimulate discussion. This is desirable and necessary, because ideas are the lifeblood of civilization, and societies assimilate ideas and become comfortable with their implications through understanding and debate. If eternal inflation is the correct description of our universe, it will be the artists, philosophers, theologians, novelists, and musicians, alongside the physicists, who explore its meaning. What does it mean if the existence of our universe is inevitable? What does it mean if we are not special in any way? What does it mean if our observable universe, with all its myriad galaxies and possibilities, is a vanishingly small leaf on an ever-expanding fractal tree of universes? What does it mean if you are because you have to be? I can't tell you. I can only ask, what does it mean to you? For small creatures such as we, the vastness is bearable only through love. Carl Sagan. They must have descended into the darkness for a reason. Their burning dry grass torches would have filled the caverns with acrid smoke, sucking the oxygen from the wet air. They would have moved carefully, fearfully perhaps, enveloped in a dim, flickering sphere of red, fading into a profound, silent dark, the like of which I don't experience. A child held her hand against the rock and blew a red pigmented mixture across it with a straw. She smiled. My hand. Her companions reached into the pigment and in careful movements inked a line of dots beside the handprint. The precision of a young imagination. A retreat into the lightness of the cave mouth. Perhaps we'll come back someday, she thought. Over 40,800 years later, I held my hand next to hers, because the experts on the Upper Paleolithic told me that the handprints are always those of children, and most likely always female. El Castillo in northern Spain contains some of the oldest cave art in the world. It is not known precisely how old, because the pigments themselves cannot be dated. The art is covered in calcite, which dripped and crystallized across the handprints and dots, as the whole of recorded history played out above. Calcite contains uranium-234 atoms, which decay with a half-life of 245,000 years into thorium-230, which in turn decays with a half-life of 75,000 years. Thorium is not soluble in water, so there was none when the limestone formed. By measuring the concentrations of the uranium isotopes 234 and 238 and the thorium-230, a precise date for the formation of the calcite can be measured. This gives a minimum date for the art, since of course it must have been created before it was covered. The limestone covering the red dots formed 40,800 years ago. The oldest handprint was covered 37,300 years ago. These dates are significant because before 41,000 years ago, there is no evidence of modern humans in Europe. Homo sapiens arrived tantalizingly close to the minimum age of the art in the darkness of El Castillo, leading some anthropologists to suggest that the art is not human. Rather, it might have been created by our close cousins, the Neanderthals, who dominated Europe at the time. I find this possibility profoundly interesting and moving. It's interesting because the creators of this art had all the attributes that we might lazily refer to as uniquely human. The retreat into the deep caves was undoubtedly a sophisticated response to the world. This is not mere decoration, because cave art like this is not found near the cave entrances where these people lived. Its creation is highly ritualized. The darkness is integral. One of the most beautiful pieces in El Castillo is a bison, half carved out of a column of rock and shaded with pigments to emphasize the arch of its back. When illuminated by torchlight, the rock casts a flickering animal shadow onto the cave wall. The interaction of light and dark was important to the rituals carried out here before history, perhaps before humans. The cave resonates with ideas, curiosities, and fears. It represents a border, the transition from existence to living. If this is a human place, it's a record of the first stumbling steps towards humanity. But if it is Neanderthal, it is a record of an ending, an ascent cut short. Perhaps we'll come back someday, thought the little girl in my imagination. Not long afterwards, her species became extinct, outcompeted by their incoming cousins. Perhaps. It is possible that the date coincides with the migration of Homo sapiens into Europe because the art is indeed human. Some anthropologists believe that the art may have been a response to the native Neanderthal population, a sort of prehistoric shock and awe, asserting cultural dominance and engendering a sense of community and superiority in the nascent human population. Things never change. If this is the case, the Neanderthals inadvertently played a role in our ascent. The roles may have been reversed, however. Perhaps our ancestors found a young, emerging, and more sophisticated culture when they crossed the Mediterranean. A species distantly related to us, whose desire to explore the darkness we assimilated. Perhaps our intellectual climb was, in part, a response to them. Intellectual superiority does not guarantee survival. Witness the fall of classical civilization. This possibility is illustrative of a fact that we modern humans often subconsciously rest in the shadows. Things can end forever. Species become extinct, and that doesn't only apply to animals with feathers and no feelings. The Neanderthals became extinct, and they may have begun to imagine a future before they lost it. The red handprints of El Castillo are overwhelming in this context. Go there. Hold your hand up to hers. Hear the giggles. Picture the smiles. Imagine the beginnings of hope. And listen to the silence. At least 40,800 years later, we can use our knowledge of nuclear physics to move backwards through time to piece together her story. Science is a time machine, and it goes both ways. We are able to predict our future with increasing certainty. Our ability to act in response to these predictions will ultimately determine our fate. Science and reason make the darkness visible. I worry that lack of investment in science and a retreat from reason may prevent us from seeing further, or delay our reaction to what we see, making a meaningful response impossible. There are no simple fixes. Our civilization is complex. Our global political system is inadequate. Our internal differences of opinion are deep-seated. I'd bet you think you're absolutely right about some things and virtually everyone else is an idiot. Climate change, Europe, God, America, the monarchy, same-sex marriage, abortion, big business, nationalism, the United Nations, the bank bailout, tax rates, genetically modified crops, eating meat, football, X Factor or Strictly. The way forward is to understand and accept that there are many opinions, but only one human civilization, only one nature, and only one science. The collective goal of ensuring that there is never less than one human civilization must surely override our personal prejudices. At least we have come far enough in 40,800 years to be able to state the obvious, and this is a necessary first step. We've woken up at the wheel of the bus and realized we don't know how to drive it. Sudden impact. On the 15th of February 2013 at 9:13 a.m., a 12,000-ton asteroid entered Earth's atmosphere traveling at 60 times the speed of sound. It came from the direction of the Sun, so there was never any chance of seeing its approach. The rock broke up at an altitude of 29 kilometers, depositing over 20 times the energy of the Hiroshima bomb into the sky above the Russian town of Chelyabinsk. Thousands of buildings were damaged by the shockwave, and 1,500 people were injured, mainly by flying glass, as windows smashed in multiple cities across the region. Sound waves from the explosion rattled around the globe twice, and were detected by a nuclear weapons monitoring station in the Antarctic. The Russian Parliament's Foreign Affairs Committee chief, Alexei Pushkov, took to Twitter. Instead of fighting on Earth, people should be creating a joint system of asteroid defense. Naive idealism? Overreaction? Hollywood? Not really. 16 hours later, a 40,000-ton asteroid named 367943 Duende streaked by at an altitude of 27,200 kilometers, well within the orbits of many of our satellites, although it missed them all. This one had a name, because it was discovered by astronomers in Spain in 2012. There is a 1 in 3,000 chance that Duende will strike the Earth before 2069. If it does, it could destroy a city, which isn't too bad. Before Chelyabinsk, the last recorded large impact was the Tunguska event over Siberia in 1908. The shockwave created by the airburst flattened 2,000 square kilometers of forest in an energy release close to that of the United States' most powerful hydrogen bomb test at Bikini Atoll in March 1954. Events on this scale are thought to occur on average once every 300 years, and could easily wipe out a densely populated region. The best-known impact in popular culture was the Chicxulub event in Mexico's Yucatan Peninsula 66,038,000 plus or minus 11,000 years ago, which wiped out the non-avian dinosaurs. Precision is important when available. If they'd had a space program, Carl Sagan once quipped, or perhaps lamented, the dinosaurs would still be around, although in that case we wouldn't. The Chicxulub asteroid was probably around 9.5 kilometers in diameter, and the energy release of such an object exceeds that of the world's combined nuclear arsenal by a factor of 1,000. Or if you like scary statistics, that's 8 billion Hiroshima bombs. Such events are estimated to occur on average every 100 million years, give or take, and are quite capable of destroying human civilization and possibly causing our extinction. At the other end of the scale, rocks of around 1 millimeter in diameter hit the Earth at a rate of 2 a minute. Alexei Pushkov was right. It is absolute idiocy not to pay attention to the danger of impacts from space, and fortunately our space agencies have begun to do so. NASA's Near-Earth Object Program created the Sentry system in 2002, which maintains an automated risk table continually updated by new observations from astronomers around the world. I'm writing these words on the 3rd of September 2014, and there are currently no high-risk objects in the table, although there are 13 asteroids with the potential to impact Earth that have been observed within the last 60 days. The risk posed by an asteroid is quantified on the Torino scale. Every known near-Earth asteroid is assigned a value on the Torino scale between 1 and 10, calculated by combining the collision probability with the energy of the collision in megatons of TNT. Asteroid 99942 Apophis reached level 4 on the Torino scale in December 2004. Initial observations and calculations suggested this 350-meter-wide asteroid had a 1 in 37 chance of a potential collision with the Earth on the 13th of April 2029, and a further chance of hitting us 7 years later if it missed first time around. This would not have been a civilization-threatening event, but it could have laid waste to a small country. Subsequent observations have effectively ruled out the risk from 99942 Apophis, but statistically speaking, such an impact is expected to occur every 80,000 years or so. Although the Sentry table is currently benign, there are at least 2 very good reasons why we shouldn't relax and forget about impact risks. Firstly, we haven't detected all of the threatening objects by any means, as the Chelyabinsk event so effectively reminded us. And secondly, we don't currently know precisely what to do if we do observe an asteroid with our name on it, which could happen tomorrow. In 2016, a new early warning system called ATLAS, Asteroid Terrestrial Impact Last Alert System, came online. 8 small telescopes scan the sky for any sign of faint objects that may pose a threat to the Earth. ATLAS will give up to 3 weeks warning of an impact, which is enough time to evacuate a large region, but probably not an entire country. The cost of our global insurance policy? 1/3 of the annual wages of Manchester United striker Wayne Rooney. Such comparisons always sound childish, of course. I'm well aware of how capitalism functions, and I know that Wayne Rooney generates income for the Manchester United Corporation in excess of his wages. But the aim of this chapter is to argue that there is a flaw in the majestic edifice of human civilization, our myopic and cavalier disregard for our long-term safety. In my view, the reason for the short-sighted approach is that nothing catastrophically bad has happened to humanity in recorded history that we haven't inflicted upon ourselves. Unless, of course, you believe in Noah's Ark. And even that was presumably down to us, because one assumes that God is usually quite a patient sort. One of the central themes of this book has been to argue that the human race is worth saving, because we are a rare and infinitely beautiful natural phenomenon. One of the other themes is that we are commonly and paradoxically ingenious and stupid in equal measure. I do not personally think that there is anyone out there to save us, and so it follows that we will have to save ourselves. At least, that would seem to me to be a good working assumption. This is why I don't feel naive, idealistic, or like a particularly radical member of the student union in a Che Guevara t-shirt when I ask the question, is it reasonable to spend less on asteroid defense than on a footballer's annual salary? When I look in the mirror and think about that, my face assumes an interesting shape. You should try it. NASA is working hard in the face of apathy to do something to close the gap between the capabilities of the dinosaurs and us. 20 meters beneath the surface of the Atlantic Ocean, 8 kilometers off the coast of Key Largo, Florida, is the Aquarius Reef Base. Originally constructed as an underwater research habitat to study coral reefs, it is used by NASA to train astronauts for future long-duration space missions. The base allows for saturation diving, which greatly increases the length of time a researcher can spend exploring the reefs. On a normal scuba dive, a diver can spend a maximum of 80 minutes at a depth of 20 meters without having to go through decompression. The diver can remain at this pressure for several weeks, however, as long as they decompress when they return to the surface, a process that takes almost a day. Since the air pressure inside Aquarius is the same as the pressure outside in the water, researchers living inside the base can spend many hours a day exploring the seabed using standard scuba equipment, but with the important caveat that they cannot return to the surface a few meters above their heads. If anything goes wrong, they must return to Aquarius and deal with the problem inside the base. For all practical purposes, therefore, they are isolated. It's not possible to panic or simply lose patience and return to civilization above. This is why NASA uses the Aquarius base to train astronauts to work in a hostile environment and test their psychological suitability for long-duration space missions. Filming inside Aquarius was a personal highlight of human universe. We didn't want to have to decompress, of course, so we had a strict time limit of 100 minutes inside the base, spread over 2 dives. The ex-US Navy diver in charge of our dive was wonderfully clear as far as timings were concerned. If I say leave, you don't smile and take one more shot, you leave. Otherwise you stay, for a long time. Your choice. I know you media types. Aquarius has the look and feel of a spacecraft from a science fiction film. There are 6 bunk beds piled 3 high at one end, and a galley area complete with microwave and sink at the other. In between there are control panels, some books on marine life, and a laptop computer station. Above the table, there is a single round window looking out across the reef. Through an airlock-style exit, there is a dive platform with access to the scuba tanks and the open sea. NASA's Extreme Environment Mission Operations, NEMO, team had just completed a 9-day mission when we arrived. Led by Akihito Hoshide of the Japanese Aerospace Exploration Agency, the mission was part of the long-term goal of landing astronauts on an asteroid and developing the capability to deflect one should the need arise. There are strong scientific and commercial reasons for exploring asteroids. They are pristine objects that will allow us to better understand the formation of our solar system over 4.5 billion years ago, and rich in precious metals precisely because they are pristine. On Earth, heavy metals such as palladium, rhodium, and gold migrated into the Earth's core, leaving the accessible crust depleted. Asteroids are too small to have separated in this way, leaving the primordial abundances of these valuable metals untouched and accessible. Whether for commercial, scientific, or practical reasons, learning how to land on asteroids, exploit their resources, and manipulate their orbits is clearly an eminently sensible thing to do. And make no mistake, we will have to move one at some point. Seeing the future. In the year 35,000 CE, the red dwarf Ross 248 will approach the solar system at a minimum distance of 3.024 light-years, making it the closest star to the Sun. 9,000 years later, it will have passed us by, ceding the title of nearest neighbor to Proxima Centauri once again. Coincidentally, in 40,176 years, Voyager 2 will pass Ross 248 at a distance of 1.76 light-years. We know this because we can predict the future. We've encountered Newton's laws several times in this book. In Chapter 3, we used them to calculate the velocity of the International Space Station in a circular orbit around the Earth. At a distance r from the center of the Earth, the velocity v is v equals the square root of gme over r. Let's look at this equation in a different way by rewriting it as dx by dt equals the square root of gme over r. Here we've used the notation of calculus. That may strike fear into your heart if you haven't done any mathematics since school, but don't worry. All we need to know is the meaning of the symbol dx by dt. In words, this denotes the rate of change of the position of the space station with respect to time, otherwise known as its velocity, v. You have an intuitive feel for this, even if you've never done any mathematics. If you get into your car and drive it away from your house in a straight line at a velocity of 30 kilometers per hour, then in 1 hour, you will be at a position 30 kilometers away from your house, in the direction in which you drove the car. The equation is telling us what the position of the space station will be at some point later in time, given knowledge of where it is and how it is moving in the present. It predicts the future. This sort of equation is known as a differential equation. In Chapter 4, we wrote down the rules of the game, Einstein's general theory of relativity and the standard model of particle physics. The notation is a little more complicated, but in the standard model you'll notice the symbols d mu and delta mu, which are more complicated versions of dx by dt. In Einstein's equations, there are also these so-called derivatives hidden away in the compact mathematical notation. The known fundamental laws of physics all function in this way. Given knowledge of how some system or collection of natural objects is behaving now, we can compute what they will be doing at some time in the future. The system in question may be a solar system, a collection of atoms and molecules, or the weather. There are practical limitations, of course, and the weather forecast is a good example. Earth's climate system is very complicated, with many hundreds of thousands of variables. Ocean currents in the Pacific might affect future rainfall in Oldham, and so long-term forecasting of local weather conditions comes with increased uncertainty. People do, of course, make statements, often based on human experience rather than science, which are more likely to be right than wrong. Red sky at night, shepherd's delight; red sky in the morning, shepherd's warning. This is often true in countries like the UK, whose weather is dominated by westerly winds, because a red sunset is usually a sign of high pressure to the west, which is associated with fine weather. But if you're doing well in a statistically significant sense using folklore or ancient wisdom, it's because the patterns and regularities you're using to make your predictions emerge from underlying physical laws which are described by differential equations. The laws of physics, in essence, reflect the underlying simplicity of nature and the regularity with which it behaves. They're not magic. We can describe the natural world using mathematics because it is regular and behaves consistently. It is my opinion that we must observe a universe that behaves in a regular and consistent way, because such behavior is necessary for complex structures like brains to evolve. A universe of anarchy with subatomic particles interacting without some sort of framework or rules would surely not support life, or indeed any structures at all. This is known as a selection effect. We observe a universe whose behavior can be described by a limited set of differential equations because we wouldn't exist if it were not so. This is my opinion, and there are scientists and philosophers who might disagree. It could be the case that there is no simple underlying framework to the universe, and our success to date has deceived us. Or perhaps the ultimate laws are and will forever remain beyond human understanding. We might simply not be smart enough to figure them out. There are also systems that cannot be described using differential equations. The patterns generated in Conway's Game of Life are an example, where algorithmic rules are used to generate complex patterns, and even computing devices such as Turing machines. But what can be said with certainty is that as far as we can tell, the natural world does behave in a way that is amenable to a description based on the differential equations of physics. And these allow us to predict the future, given knowledge of the present. This is why our asteroid defense system will work if we make enough high-precision observations of the sky. Sort of. Caveats. There are always caveats. We should be confident in science. It works. But it has limitations, some of which are fundamental. We've encountered Newton's laws of motion and gravitation time and again in this book. They're very simple, the archetypal physical laws, and are used every day by engineers, navigators, and asteroid watchers. One of the simplest imaginable real-life systems to which Newton's law of gravitation can be applied is a single planet orbiting around a single star. For this case, Newton's laws allow for a precise prediction of the future position of the planet. The orbit is predictable and periodic, which is to say the planet returns to precisely the same position around the star every orbit. It's clockwork, the way the solar system is often pictured. If a third object, a moon, say, is introduced, it was proved in the late 19th century by Heinrich Burns and later Henri Poincaré that no general solution to Newton's equations can be found. There are a handful of special cases, which are still being discovered, for which there are repeating solutions, but in general, the orbits of three bodies acting under gravity never repeat. Their motion around each other traces out a tremendous, ever-changing mess. This isn't a failure of mathematics. Natural systems really do behave in this way. The solar system is a case in point. The planets orbit like clockwork on timescales of millions of years, but we are currently unable to predict the Earth's orbit for more than 60 million years into the future. Beyond that, the sensitivity of the predictions to uncertainties in our current knowledge of the Earth's orbit and the gravitational influence of other bodies in the solar system become too great. This isn't only a reflection of our lack of knowledge. It also reflects an important fundamental point, which is that solar systems such as ours are unstable over long timescales. Their behavior is chaotic. The apparent clockwork can break down into a whirling, unpredictable swarm. Recent simulations suggest that Mercury could be wrenched out of its orbit and collide with the Sun, and that even the Earth may have a close encounter with Venus or Mars on time periods of 3 to 5 billion years. The words could and may are emphasized for a reason. These predictions are statistical in nature. It's estimated that there is a 1% chance that Mercury will be thrown into a much more elliptical orbit during the next 5 billion years. The uncertainty is down to the extreme sensitivity of the predictions to what physicists call the initial conditions, the current knowledge of precisely where everything in the solar system is at this instant, and how everything is moving at this instant. Other errors are caused by our precise knowledge of the mass and shape of all the objects in the solar system, not to mention the slight perturbations from incoming comets and the ever-shifting asteroids. The area of physics and mathematics concerned with such systems is called chaos theory, and as the pioneer of the field Edward Norton Lawrence put it, nature's complexity usually leads to a situation in which approximate knowledge of the present, which is in practice all we ever have, does not approximately determine the future. For the asteroid hunters, this is an intensely problematic truth. It is not possible to observe an asteroid once and then pop its position and velocity into a computer to work out whether it will ever hit us. Instead, a gravitational keyhole system is used. A keyhole is a small volume of space close to the asteroid's current orbit. If an asteroid passes through the keyhole, perhaps because of a gravitational nudge from some other object in the solar system, then it is highly likely that it will impact the Earth on its next pass. 99942 Apophis was assigned such a keyhole in 2004 when it was classified as 4 on the Torino scale. Fortunately, it didn't pass through, and this is why it is currently classified as harmless. The keyhole system reflects the fundamental unpredictability of complex physical systems over long timescales. This is why we have to keep observing and retain a keen understanding of the fundamental limits of our calculational prowess. Science isn't magic. This realization is, of course, important in a practical sense, if one is interested in saving the planet from asteroid impact. But it's also very important to embed caution and humility into our/my polemical celebration of the power of science. Scientific predictions are not perfect. Scientific theories are never correct. Scientific results are always preliminary. Whole fields of study can be rendered obsolete by new discoveries. But, I insist, science is the best we can do, because it is not simply another arbitrary system of thought based on dreamt-up human axioms. It is the systematic study of nature, based on observations of the natural world and our understanding of those observations. Scientific predictions are not matters of opinion. At any given time, science provides the best possible estimate of what the future might bring, given our current understanding. The predictions may be wrong, they may be inaccurate, the errors may be fundamental in origin, but there is simply no other rational choice than to act according to the best available science. Imperfect though by necessity, its predictions will always be. The wonder of it all. As of September 2014, in a population of 7.24 billion, 545 people have been to space, 24 people have broken free of the Earth's gravitational pull, and 12 have landed on another world. In 2013, Charlie and Dorothy Duke, a retired church-going couple from New Braunfels, Texas, reached their 50th wedding anniversary. With 2 grown sons and 9 grandchildren, Charlie and Dottie must have celebrated a life well lived, captured in photographs adorning the walls and mantelpieces of the family home. There is one Duke family photograph, however, that holds a unique place in history. I myself have a copy of it on my wall at home, signed by Charlie, and it's one of my favorite things. The photograph, taken in 1972, is an image of Charlie, Dottie, and their 2 young sons Charles and Thomas when they were just 6 and 4 years old. The picture itself is of no particular note, a simple portrait of a family in 70s clothes, sitting on a bench in a garden. It's not dissimilar to one of me and my granddad photographed at around the same time. I was in Oldham, the Dukes were in Florida. The reason I have a copy of the Duke's photograph is not what it is, we are not related, but where it is. Charlie and Dorothy Duke are the only grandparents on Earth who can point their grandchildren's eyes towards the moon and tell them there is a photo of Grandma, Grandpa, Dad, and Uncle resting on the surface. Charlie Duke was the pilot of Orion, the Apollo 16 lunar module. At the age of 36, he remains the youngest human ever to have walked on the moon. Together with Commander John Young, my childhood hero, the 2 astronauts spent 3 days in late April 1972 exploring the Descartes Highlands, covering almost 27 kilometers in the lunar rover. The primary scientific aim of the mission was to explore the geology of the lunar highlands. It was thought that the unique rock formations around the landing site were formed by ancient lunar volcanism, but Young and Duke's exploration demonstrated that this explanation was incorrect. Instead, the landscape had been forged by impact events, scattering material outwards from the craters and littering the surface with glass. After 3 days on the lunar surface and setting a lunar land speed record of 17 kilometers per hour, Charlie Duke removed his family portrait from his spacesuit pocket, placed it on the lunar surface, and snapped it with his Hasselblad. Inscribed on the back are the words, "This is the family of astronaut Duke from planet Earth. Landed on the moon, April 1972." I remember being 4 years old in Oldham when Apollo 16 was on the moon. 42 years later, I talked to Duke for hours in a diner in Texas, with absolutely no regard at all for the film crew trying to make human universe. "When I stepped onto the moon, it occurred to me that nobody had ever been here before. You looked out onto the most pristine desert, the most incredible, beautiful place I've ever seen. No life, nothing like Earth. The rolling gray lunar surface with the blackness of space above. How ambitious was Apollo?" I asked. "They gave us 8.5 years to do it, and we did it in 8 years and 2 months. Nobody even knew how to do it," replied the test pilot, who was used to doing things that nobody can do. "Yeah, sure. 15 minutes in space and we're going to land on the moon in 8.5 years? But the remarkable part is that we did it, and I had a part in it." "Would it be possible now?" "No. We don't have the manpower to do it. 400,000 people and unlimited budget, and you can do a lot. And that's what we had." What do you say to people who criticize manned exploration? There's surely more to human exploration than just science. "It's the wonder of it all," replied the astronaut. "And that's what we bring, what manned flight brings to the human spirit, the human being. The wonder of it all. The beauty of the universe, the orderliness of the universe. And you see it with your own eyes, and it just captures your imagination. Let's see it. Let's do it. And let's discover it. That's been the human spirit all along." I think Apollo is the greatest human achievement. People argue with me, of course. Gil Scott-Heron wrote a song called Whitey's on the Moon. A rat done bit my sister Nell with Whitey on the moon. Her face and arms began to swell, and Whitey's on the moon. I can't pay no doctor bill, but Whitey's on the moon. 10 years from now I'll be paying still while Whitey's on the moon. The economics of Apollo are interesting. As Charlie said, the budget was whatever it had to be to get to the moon by 1970. At the peak of spending in 1966, NASA received 4.41% of the federal budget, equivalent to around $40 billion today. That's a lot of money, almost half the United Kingdom's annual debt interest bill. That's meant to be sarcastic, of course. The total cost of Apollo was in the region of $200 billion at today's prices, which is around a quarter of the cost of the UK's bank bailout programme initiated in October 2008. That's unfair, a city type might splutter over a glass of Don Ruinart, because that money was an investment in financial stability and has been repaid, give or take the odd 100 billion, which is neither here nor there. My reply would be yes, but Apollo was probably the most savvy investment in modern history. In 1989, the then US President George Bush said Apollo provided the best return on investment since Leonardo da Vinci bought himself a sketch pad. Many academic studies have been carried out, and the most commonly quoted figure is that for every dollar spent on Apollo, $7 was returned to the economy over the period of a decade. Why? Because Project Apollo was conceived and executed in a tremendously smart way, distributing high-technology jobs and R&D projects across the country. It was also unarguably inspirational, propelling thousands of kids into science and engineering. The average age in Mission Control Houston on the 20th of July 1969, when Neil Armstrong landed on the moon, was 26. The old man in charge, Gene Kranz, was 36, and the old man flying the lunar module was 35. What happened to all those brilliant engineers? They went out into the economy, of course, took the technology and expertise developed for the moon landings, and invented the modern world. The kids they inspired became known as Apollo's children, the generation of optimists, steeped in possibility, who powered the United States economy through the last third of the 20th century. The world loves this America, the one that flies to the moon not because it's easy, but because it's hard. I think America has lost its way, which might seem rich from a citizen of a small island that spends more on the wages of Premier League footballers annually than it does on research into the physical sciences and engineering, including its contributions to CERN, the European Space Agency, and all UK-based scientific facilities. We've lost our way too. And so has the world. The World Bank defines R&D as current and capital expenditures, both public and private, on creative work undertaken systematically to increase knowledge, including knowledge of humanity, culture and society, and the use of knowledge for new applications. The United States spent 2.79% of its GDP on increasing knowledge in 2012. The UK spent 1.72%. It has been estimated that the return on R&D spending in today's world economy is approximately 40 to 1. Imagine what we could do if we took these figures seriously. My granddad, sitting behind me in that 1972 family Christmas photograph, was born in 1900. He was 3 years old when on the 17th of December 1903 at Kill Devil Hills in North Carolina, Orville Wright took the controls of the Wright Flyer and lifted off the ground for 12 seconds. He was 68 when he saw Neil Armstrong walk on the moon. Orville Wright himself died in the year that Neil Armstrong began studying aeronautical engineering at Purdue University, Indiana. I still find it hard to believe that I have spoken to someone who was born before powered flight, and to someone who walked on the moon. It's important to notice that this sentence can't be followed. Someone who walked on the moon, comma, and someone who... what? Where will the next generation of Apollo's children come from? Perhaps a new superpower will take America's place as the great exploring nation. China and India, those re-emergent cradles of civilization, have ambitions in space. As Jacob Bronowski wrote in The Ascent of Man, humanity has a right to change its color. But I share his regret that the retreat of Western civilization may leave Shakespeare and Newton as historical fossils, in the way that Homer and Euclid are. If that is the case, it will be our choice. 2 more astronauts followed Duke and Young onto the lunar surface. They left at 10:55 p.m. GMT on the 14th of December 1972. Commander Gene Cernan, as he prepared to step onto the ladder of the lunar module, quietly spoke the final words from the moon. "I'm on the surface, and as I take man's last step from the surface, back home for some time to come, but we believe not too long into the future, I'd like to just say what I believe history will record, that America's challenge of today has forged man's destiny of tomorrow. And as we leave the moon at Taurus Littrow, we leave as we came, and, God willing, as we shall return, with peace and hope for all mankind. Godspeed, the crew of Apollo 17. Gene Cernan, Taurus Littrow Valley, 14th of December 1972. Dreamers, Part 1. Apollo was about many things. It was about winning a race against the Soviets. It was about national pride. It was born out of fear as well as optimism. It was about laying the foundations of American dominance in the late 20th century. It was about economic stimulus. It was about dreams. It succeeded on all fronts. Was it really about dreams? Well, space is there, and we're going to climb it. And the moon and the planets are there. And new hopes for knowledge and peace are there. And therefore, as we set sail, we ask God's blessing on the most hazardous and dangerous and greatest adventure on which man has ever embarked. I think so. Kennedy was a politician, but I believe he meant it. So what of the dreamers now? Is the 21st century the era of pragmatism? The era in which we believe because we have to that the interests of shareholders are aligned with the interests of humanity? Innovation funds the shops on New Bond Street, but is that all? A common governmental lament is that new knowledge is not converted efficiently enough into economic growth. Is that what knowledge is for? Who pays for progress? Who should pay for progress? Human Universe is a piece of documentary television, and this book is based on the series. Television is about stories, examples that illustrate a point. Human Universe is also, at heart, optimistic, because I am optimistic. I think we as a civilization could do better, as I'm sure you've gathered, but it would be ridiculous to suggest that we're not doing some things right. In the final episode, we found 2 stories that demonstrate that long-term thinking is not dead. One almost Apollo-like in state-funded grandeur, and the other more modest but equally important. The first was a project I'd visited once before, back in 2009, known as the National Ignition Facility at the Lawrence Livermore National Laboratory in California. The aim is to make a star on Earth. Nuclear fusion is the power source of the stars. The sun releases energy in its core by turning hydrogen into helium. 2 protons approach each other at high speed because the core is hot. The core became hot initially through the collapse of the gas cloud which formed the sun. Protons are positively charged, and therefore repel each other through the action of the electromagnetic force, but if they get close enough, the more powerful nuclear forces take over. The weak nuclear force acts to turn the proton into a neutron, with the emission of a positron and an electron neutrino. The proton and the neutron then bind together under the action of the strong nuclear force to form a deuterium nucleus, which is an isotope of hydrogen, because it contains a single proton, with a neutron attached. Very quickly, another proton fuses with the deuteron to form helium-3, and finally 2 helium-3 nuclei stick together to form helium-4, with the emission of the 2 spare protons. The important result in this convoluted process is that 4 protons end up getting converted into a single helium-4 nucleus, made of 2 protons and 2 neutrons, and the helium-4 nucleus is less massive than 4 free protons. This missing mass is released as energy, in accord with Einstein's equation E equals mc squared, and this is why the sun shines. The energy released in fusion reactions is colossal by terrestrial standards. If all the protons in a cubic centimetre of the solar core were to fuse into deuterium, enough energy would be produced to power the average town for a year. Or to put it another way, 1 kilogram of fusion fuel produces as much energy as 10 million kilograms of fossil fuel, which is approximately 100,000 barrels of oil, with no CO2 emissions. The waste product is helium, which can be used to fill party balloons. Energy is the foundation of civilization. Access to energy underpins everything, from public health to prosperity. Access to clean water is surely more fundamental, you might say, but this requires energy. Even in the most arid regions, desalination plants or deep wells can deliver water in abundance if sufficient energy is available. It isn't, of course. Profligate energy use has a bad name today, but consider this. In every country in which the per capita energy use is greater than half the European average, adult life expectancy is greater than 70 years. Literacy rates are greater than 90%, infant mortality rates are low, and more than 1 in 5 of the population is in higher education. The reason energy use has a bad name is not because it is bad in itself. It is good. It is the foundation of modern civilization, and modern civilization is a good thing. I don't want to live on a subsistence farm, sleep in stifling heat, run the risk of dying of malaria and have no access to clean water or cutting-edge medical care. I'm lucky. I live in a city. I buy all the food I want from nice shops. I have a fulfilling job in a university, and I get to do research at places like CERN, which is interesting. I want everyone in the world to have choices, like I have. And that means I want everyone in the world to have access to energy, like I have. In 2011, 1.3 billion people lacked access to electricity. Yes, energy use is good. The problem with energy is how we produce it. The world produces more than 80% of its energy by burning fossil fuels. This is expected to fall to 76% by 2035, as nuclear and renewables grow in importance. Burning things is humanity's oldest technology. The energy sector is responsible for 2/3 of global greenhouse gas emissions. The most recent scientific modelling suggests that global average temperatures will rise by around 2 to 2.5 degrees C above the average of the years 1986 to 2005 by 2100. The rise could be less, as low as 1 to 1.5 degrees C, or it could be 4 degrees C or more. Some of the uncertainty depends on our actions, and so there are assumptions about future behaviour built into the predictions. But over 90% of computer models agree that global temperatures will have increased by 2100 as a result of greenhouse gas emissions from fossil fuel burning. Nuclear fusion, then, is a good idea. If it can be made to work in an economically viable way, it will provide limitless, clean energy for everyone. It is not the only way of achieving this goal. One can make a case for solar power, and indeed an increased contribution from other renewables and nuclear fission. But it is a possible way to solve the world's energy problems for good, in principle, and is therefore worth exploring. The challenge is technical rather than fundamental, in the sense that we know fusion works because the sun does it. Fusion is difficult to achieve on Earth, primarily because of the colossally high temperatures and pressures required. There are 2 approaches being followed, and each is Apollo-like. In Europe, a worldwide collaboration involving Russia, USA, the European Union, Japan, China, Korea, and India is in the process of constructing ITER. This machine is in effect a magnetic bottle, which can store a plasma at temperatures in excess of 150 million degrees C, 10 times that of the solar core. ITER will use deuterium and tritium, which is another isotope of hydrogen comprising 1 proton and 2 neutrons, to make helium-4. This bypasses the slow initial weak interaction in the Sun that makes deuterium out of hydrogen, making ITER a lot more efficient than our star. Deuterium is extracted from seawater, and tritium is made inside the reactor itself by irradiating a lithium blanket with the spare neutrons produced during the fusion reaction. An 800 megawatt fusion power station of this type would consume around 300 grams of tritium fuel per day. ITER is not particularly telegenic at the moment because it's under construction and will not be commissioned until 2019. This is why we chose to focus on the US National Ignition Facility, which is already up and running. NIF is pure science fiction. In fact, it was used as a set for Star Trek Into Darkness. It is the world's largest laser system by an order of magnitude. The laser delivers 500,000 gigawatts of power onto a target smaller than a peppercorn in a series of increasingly powerful hammer blows tuned to arrive with a precision of better than 1/10 of a billionth of a second. That is 1,000 times the peak energy generating capacity of the United States. This, as you can imagine, creates a bit of a bang. The peppercorn-sized target contains deuterium-tritium fuel, just like ITER. The laser pulses raise the temperature of the pellet's gold container, and the X-ray radiation produced drives a rapid collapse of the fuel, initiating fusion. The devil is in the detail. The precise timing and duration of the laser pulses and the shape of the gold container all contribute to the chances of success and the efficiency of the process. Despite the tremendous engineering difficulty, in September 2013, more energy was released from a deuterium-tritium fuel pellet than the pellet absorbed, although this was only 1% of the total energy input to the lasers. Nevertheless, this demonstrates that so-called inertial fusion works in principle. The inertial fusion power stations of tomorrow would use far more efficient laser systems, NIFs are now more than a decade out of date, and the fuel pellet technology being developed by NIF. The technology has been demonstrated to work, at least on a vast government-funded research scale, and this is how difficult things like space exploration have to begin. Commercial companies will rarely take such enormous risks, and this means that we, the taxpayers, must pay for the creation of this type of knowledge. As with Apollo, we will be repaid, but the investment horizon is beyond that of the average accountant. It therefore appears that there is no technical reason why such power stations could not be constructed. There is much research to be done, but the barriers are likely to be budgetary rather than fundamental. The United States spends more on pet grooming than it does on fusion research. There's a serious point behind that cheap shot. I think one of the primary barriers to progress is education. I am a believer in the innate rationality of human beings. Given the right education, the right information, and the right tuition in how to think about problems, I believe that people will make rational choices. I believe that if I said to someone, "Here's the deal, you can have limitless clean energy for your lifetime, for your children and grandchildren's lifetimes and beyond, in exchange for grooming your own cat," then most people would reach for a comb. I have to believe that. Otherwise, this book is a futile gesture. The second of our stories couldn't be more different. It involves no high technology and very little cash, but it may have a tremendous impact. Securing the future isn't all about money. It's also about action. The Svalbard Global Seed Vault is modest and beautiful from the outside. In common with all publicly funded construction projects in Norway, the simple door on an Arctic hillside is a work of art, created by Divek Sanne. In the summer, it reflects the eternal sun. In winter, fiber-optic cables shine in the perpetual night. The doorway leads into a converted coal mine deep in the permafrost. There are 3 caverns, each maintained at a temperature of -18 degrees C by a cooling system. The temperature was chosen very precisely. It's the temperature at which seeds metabolize slowly but do not die. At -18 degrees C, the most hardy seeds remain viable for over 20,000 years. Only one of the caverns is in use. The other two are for the future. Inside, there are over 800,000 populations of seeds from almost every country in the world. All the seeds are agricultural crop varieties, the raw material for and the foundation of global food production. Seeds from America and Europe nestle next to those from Asia and Africa. Syrian seeds rescued from the recent troubles in Aleppo, the home of a local seed bank, sit beside those from North Korea, South Korea, China, Canada, Nigeria, Kenya, and so on around the world. The vault contains virtually the whole history of human agriculture, stretching back to its origins in the Fertile Crescent all those years ago. Each seed population reflects some choices that were made, some environmental challenge, or perhaps simply the taste of a farmer or his village. There are varieties manipulated by multinationals, or carefully cultivated and cherished by isolated tribes. The boxes are food for the imagination, time capsules, the stuff of dreams. They are also of fundamental importance. Why protect agricultural seeds? The answer is that biodiversity is a very good thing. Life on Earth forms a tangled web, a great genetic database distributed across hundreds of thousands of extant species of animals, plants, insects, and countless single-celled organisms. The more species there are, the more data there is in the database, and the more chance the whole biosphere has of responding to the challenges, be they from disease, natural or human-induced climate change, loss of natural habitat, or whatever. This is obvious. If there are genes somewhere in the great database of life that allow wheat to grow with less water, and the climate becomes more arid, then those genes will be valuable to us. If we lose particular genes, then we lose them for good. Today, fewer than 150 species of crop are used in modern agriculture, and 12 of these deliver the majority of the world's non-meat food supply. There is diversity in the form of different varieties, of course. There are estimated to be more than 100,000 varieties of rice. But the overwhelming majority of crop species used throughout human history are no longer cultivated. They are stored, however, in seed vaults, ready for use if needed. The Svalbard Global Seed Vault is a backup, our insurance policy, ensuring that even if countries lose their seed vaults through natural disasters, war, or simple neglect, then irreplaceable parts of the great genetic database of life will not be lost with them. The Norwegian government owns the seed vault, but the depositors own the seeds. A charitable trust, the Global Crop Diversity Trust, meets most of the operating costs through an endowment fund. Carey Fowler was the executive director of the trust during the establishment of the seed vault. He was a pleasure to speak to when we filmed in Svalbard. A dreamer, yes, but a dreamer who gets things done. Those of us in my field, we live in a world of wounds, said Fowler. We see the injuries, we see the loss of diversity, the extinction, and at a certain point, enough is enough, and you try to figure out what can we do that's not just stopgap, that really is long-term, and that puts an end to the problem of crop diversity. Because we know that we're going to need this crop diversity in the future. It's the biological foundation of agriculture. We'll need it as long as we have agriculture. Which is as long as civilization exists, I added. Fowler nodded. After that, we won't be bothered, will we? The Svalbard Global Seed Vault is built, effectively, for eternity, or at least for tens of thousands of years. It is supported by practically all the governments of the world, and is a genuine investment in our future, based on sound science, and an understanding of the potential challenges and risks that we may face as a single global civilization. It's not big, flashy, or expensive, but it's important. And perhaps as importantly, somebody actually did it. I find that inspiring.
Our universe is filled with countless mysteries and secrets, from the vast expanses of space teeming with galaxies, stars and planets, to the massive forces that control the very fabric of reality. Let us take you on a fascinating journey to some of the most mind-blowing mysteries in deep space. Embarking from the aftermath of the Big Bang, a monumental explosion that occurred approximately 13.8 billion years ago, we venture into an era where the universe was in its infancy, teeming with high temperatures and dense energy. This initial burst set the stage for the universe's formation, marking the beginning of space and time as we understand them. In the fleeting moments following the Big Bang, the universe was an incredibly hot and dense point. Within fractions of a second, it began expanding at an exponential rate, cooling as it did so, allowing for the formation of the fundamental forces of nature, including gravity, electromagnetism, and the nuclear forces. As the universe expanded and cooled, conditions became ripe for the creation of the first subatomic particles, such as quarks and electrons. These particles, born out of the energy from the Big Bang, eventually combined to form protons and neutrons. The universe, however, was still too hot for these protons and neutrons to combine into atoms. It wasn't until about 380,000 years after the Big Bang, as the universe continued to cool, that protons and neutrons began to combine to form the nuclei of the simplest elements, hydrogen and helium, through a process known as nucleosynthesis. Hydrogen, the most abundant element in the universe, and helium, the second most abundant, were the primary products of this early nucleosynthesis. Trace amounts of lithium were also produced during this period. The creation of these elements set the foundation for the complex chemistry that would eventually lead to the formation of stars, galaxies, and planets. As the universe continued to expand and cool, gravity began to pull together clouds of hydrogen and helium gas, leading to the formation of the first stars. These first stars played a crucial role in the evolution of the universe. Through nuclear fusion in their cores, they forged heavier elements such as carbon, oxygen, and iron. The life cycles of these stars, including their eventual explosion as supernovae, dispersed these heavier elements into space, seeding the cosmos with the ingredients necessary for the formation of new stars, planets, and eventually, life itself. The cosmic microwave background radiation, or CMB, is a faint glow that permeates the universe, offering a snapshot of the cosmos a mere 380,000 years after the Big Bang. This glow is not just a relic of the past, but a treasure trove of insights into the early universe, its composition, and its evolution. The CMB's discovery in the 1960s was a pivotal moment in astrophysics, providing strong evidence for the Big Bang theory. This radiation is the afterglow of the universe's explosive birth, stretched and cooled over billions of years as the cosmos expanded. Its uniformity and slight variations tell us a compelling story about the universe's infancy. One of the most fascinating aspects of the CMB is its astonishing uniformity. Across vast expanses of space, the temperature of this radiation is incredibly consistent, about 2.7 Kelvin or minus 270.45 degrees Celsius, with minuscule fluctuations. These minute temperature variations are crucial for cosmologists because they represent the seeds from which galaxies, stars, and eventually planets formed. Essentially, these fluctuations in density and temperature underpin the large-scale structure of the universe we observe today. The CMB also serves as a profound probe into the composition of the early universe. By studying its light, scientists can infer the universe's makeup at that time, revealing a cosmos filled predominantly with hydrogen and helium, the simplest and most abundant elements. This elemental composition supports theories of nucleosynthesis, predicting how the first elements formed in the universe's nascent moments. The polarization of the CMB light, akin to the way certain sunglasses can block out glare by aligning light waves, offers additional clues about the early universe. Another intriguing insight from the CMB is the glimpse it offers into the nature of dark matter and dark energy, mysterious components that constitute most of the universe's mass-energy content. The way CMB radiation is scattered and its interaction with matter over cosmic timescales helps cosmologists map out the influence of dark matter in clumping matter together and the role of dark energy in accelerating the universe's expansion. In the wake of the Big Bang, the universe was a formless expanse of energy, primed to evolve into the structured cosmos we observe today. This transition from chaos to order was governed by the emergence and shaping of the laws of physics, fundamental principles that dictate the behavior of the universe. Initially, in the universe's first moments, temperatures were unimaginably high, and the four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were unified. As the universe cooled, these forces began to separate, a process pivotal to the formation of the cosmos as we know it. The first to split was the strong nuclear force, responsible for holding the nuclei of atoms together. This separation set the stage for the formation of the first subatomic particles, including quarks and electrons, mere fractions of a second after the Big Bang. As the universe continued to expand and cool, quarks coalesced to form protons and neutrons, the building blocks of atoms. This period, known as the quark epoch, was crucial for determining the amount and types of matter that would dominate the universe. Following this, the universe entered the electro-weak epoch, where the electromagnetic and weak nuclear forces distinguished themselves. This differentiation was vital for the creation of various types of particles and antiparticles, and for the processes that led to the predominance of matter over antimatter in the universe. Without this asymmetry, matter and antimatter would have annihilated each other, leaving the universe devoid of the galaxies, stars, and planets we see today. As the universe aged, it cooled sufficiently for the first atoms to form, a phase known as recombination, occurring around 380,000 years after the Big Bang. This was a pivotal moment, as it allowed photons, particles of light, to travel freely for the first time, creating the cosmic microwave background radiation, a snapshot of the universe at that time. The laws of physics, particularly electromagnetism, played a crucial role in this process, dictating how electrons and nuclei combine to form neutral atoms. Gravity, the weakest but most far-reaching force, began to sculpt the large-scale structure of the universe during this period. Regions slightly denser than their surroundings began to collapse under their own gravity, forming the first stars and galaxies. This gravitational clustering is a process that continues to shape the cosmos, driving the formation of galaxy clusters and superclusters. Over billions of years, the interplay of these forces under the laws of physics facilitated the evolution of the universe from a hot, dense state to the vast and varied cosmos we observe today. Elements formed in the hearts of stars were scattered into space by supernovae, seeding the cosmos with the building blocks for new stars, planets, and eventually life. The laws of physics, emergent in the aftermath of the Big Bang, not only dictated the creation and behavior of the universe's fundamental particles, but also guided the evolution of the cosmos from simplicity to complexity. As we delve deeper into the mysteries of the cosmos, the process of galaxy formation and evolution stands as a cornerstone of modern astrophysics, offering a window into the dynamic ballet of matter under the influence of gravity in an expanding universe. This narrative unfolds over billions of years, tracing back to the subtle fluctuations in the density of matter shortly after the Big Bang, which we've seen imprinted in the cosmic microwave background radiation. The story begins in the primordial soup of the early universe, a nearly uniform field peppered with slight overdensities. These overdensities, though minuscule, were the seeds of all future structures in the universe. Under the relentless pull of gravity, regions of higher density began to attract more matter, growing increasingly larger and denser. This gravitational accretion was the first step in the long journey of galaxy formation. As these regions pulled in more gas and dark matter, a mysterious form of matter that does not emit, absorb, or reflect light but exerts gravitational effects on visible matter, they began to collapse under their own gravity. This collapse led to the formation of dark matter halos, invisible scaffolds around which visible matter could clump together. Within these dark matter halos, gas clouds continued to collapse, heating up as they densified, until the conditions became ripe for the birth of stars. This marked the emergence of the first galaxies, simple and small compared to the vast spiral and elliptical galaxies we observe today. Over time, these early galaxies began to evolve and interact. Some merged, pooling their stars and gas to form larger galaxies, while others were torn apart by gravitational forces. This era of cosmic evolution was chaotic, marked by frequent collisions that spurred bursts of star formation, known as starbursts, which shaped the galaxy's structures and compositions. Galaxy evolution is also a tale of internal change. Stars within galaxies live their lives on timescales ranging from millions to billions of years, depending on their masses. Massive stars burn through their nuclear fuel rapidly, ending their lives in supernova explosions that seed the galaxy with heavier elements. These elements, in turn, become the building blocks of new stars and planets, enriching the galaxy and influencing future generations of stars. Meanwhile, the supermassive black holes that lurk at the centers of most, if not all, large galaxies also play a crucial role in shaping their host galaxies. As these black holes accrete matter, they can emit vast amounts of energy, influencing star formation across the galaxy. Through these processes, galaxies grow and evolve, their shapes and sizes reflecting their histories of formation, interaction, and internal processes. Spiral galaxies, with their rotating disks and spiral arms, elliptical galaxies, ranging from nearly spherical to elongated ovals, and irregular galaxies, with no distinct shape, all tell stories of their origins and the dynamic universe in which they reside. As we explore the cosmos, supermassive black holes emerge as cosmic architects, exerting a profound influence on the galaxies they inhabit. Lurking at the heart of nearly every large galaxy, these colossal entities, with masses ranging from millions to billions of times that of our Sun, play a key role in shaping the evolution and characteristics of galaxies. Supermassive black holes are not just cosmic oddities, they are central players in the galactic narrative. Their gravitational pull can dictate the motion of stars and gas clouds within a galaxy, influencing its overall structure and dynamics. But their influence extends beyond mere gravitational sway. As material spirals into a supermassive black hole, it heats up and emits intense radiation across the electromagnetic spectrum, from radio waves to X-rays. This radiation can have far-reaching effects on the galaxy's environment. One of the most dramatic impacts of supermassive black holes is their role in regulating star formation within galaxies. The process, known as feedback, occurs when the energy released by the black hole as it accretes matter heats up and disperses the surrounding gas clouds that would otherwise collapse to form new stars. This feedback mechanism can quench star formation, effectively halting the growth of the galaxy. It's a delicate balance. Too much activity from the black hole can blow away the galaxy's gas, starving it of the material needed for future stars, while too little can lead to unchecked star formation, dramatically altering the galaxy's character. The interaction between supermassive black holes and their host galaxies is a dynamic dance. The growth of these black holes is closely linked to the evolution of their galaxies. Observations suggest a correlation between the mass of a supermassive black hole and the properties of its host galaxy's bulge, the dense group of stars at the galaxy's center. This relationship implies that the growth of black holes and galaxies is interconnected, possibly through cycles of gas accretion and star formation regulated by the black hole's feedback. In addition to their role in regulating star formation, supermassive black holes can also drive the formation of galactic structures. For example, jets of material ejected at near-light speeds from the poles of actively accreting black holes can carve out vast cavities in the intergalactic medium, influencing the distribution of gas and the formation of galaxy clusters. Supermassive black holes also contribute to the cosmic ecosystem through their dramatic end-of-life events. When galaxies merge, a common occurrence in the cosmic history, their central black holes can eventually collide and merge, releasing vast amounts of energy in the form of gravitational waves. These ripples in the fabric of space-time can provide insights into the fundamental laws of physics and the violent processes at the heart of galaxy evolution. Let us talk a bit about stars. The life cycle of a star is a story of transformation, a journey that not only shapes the destiny of the star itself, but also plays a pivotal role in the creation of elements, the building blocks of the universe. This cycle begins in the cold, dark clouds of interstellar gas and dust, where the seeds of stars lie waiting for the spark of creation. The first stage in the life cycle of a star is its birth, which occurs in nebulae, immense clouds of gas and dust. Within these nebulae, regions of higher density, aided by the gravitational pull of existing matter, begin to collapse under their own gravity. As the gas clumps together, it heats up, and when the core of this collapsing cloud reaches a sufficient density and temperature, nuclear fusion ignites. This fusion process marks the birth of a new star, converting hydrogen into helium and releasing energy in the form of light and heat. This is how a star enters the main sequence phase of its life, a period of stability where it spends most of its existence, balancing the outward pressure of nuclear fusion with the inward pull of gravity. The next stages in a star's life depend on its mass. Medium-sized stars like our Sun will swell into red giants as they exhaust their hydrogen fuel and begin to fuse helium into heavier elements like carbon and oxygen. Eventually, these stars shed their outer layers into space, creating beautiful objects known as planetary nebulae. What remains is the core, which collapses into a white dwarf, a dense, hot remnant that slowly cools and fades over billions of years. For more massive stars, the journey is even more dramatic. After burning through their initial hydrogen, they progress to fusing heavier elements, ultimately leading to iron in their cores. Fusion stops at iron because fusing iron consumes more energy than it releases, leading to a catastrophic collapse of the star's core. This collapse triggers a supernova explosion, an event so powerful it can briefly outshine an entire galaxy. Supernovae are crucial for element formation, as they produce and scatter many of the heavier elements, beyond iron, throughout the cosmos. The remnants of these explosions can form either a neutron star, an incredibly dense object composed mostly of neutrons, or if the star was sufficiently massive, a black hole, a point in space where gravity is so strong that not even light can escape. Stars, through their life cycles, are the universe's forges, creating and distributing the elements that make up worlds and life itself. Every atom of carbon, oxygen, and iron in our bodies was formed in the heart of a star, or in the fiery blast of a supernova, linking us intimately to the cosmos. Supernovae, neutron stars, and black holes represent some of the most dramatic and significant phenomena, each playing a unique role in the universe's evolution and in our understanding of physics. These celestial events and objects are not only fascinating in their own right, but also crucial for the synthesis of elements and the structure of the cosmos. Supernovae are the spectacularly explosive deaths of stars, events so bright they can momentarily outshine entire galaxies. They occur in two main scenarios, either at the end of a massive star's life when its core collapses under the force of its own gravity, or through the accumulation of material by a white dwarf from a companion star, leading it to exceed a critical mass and undergo a thermonuclear explosion. Supernovae play a critical role in the cosmos by dispersing elements heavier than iron into space. These elements, forged in the heart of stars or during the supernova explosion itself, are essential for the creation of planets and life. The energy released by supernovae also influences the structure of the surrounding interstellar medium, triggering star formation in some regions while dispersing gas and dust in others. Neutron stars are one of the possible remnants of supernovae explosions, formed when the core of a massive star collapses to such an extent that protons and electrons combine to form neutrons. These objects are incredibly dense, with a mass comparable to that of the Sun, but packed into a sphere only about 20 kilometers in diameter. Neutron stars possess intense gravitational and magnetic fields, with some emitting regular pulses of radiation as pulsars. These pulsars serve as cosmic lighthouses and have been used by astronomers to probe the universe's properties, including testing theories of gravity and measuring cosmic distances. Black holes, the most mysterious of these cosmic phenomena, form when the core of a supermassive star collapses under its gravity, creating a point in space where the gravitational pull is so strong that not even light can escape. Their existence was predicted by Einstein's theory of general relativity, and they have been the subject of intense study ever since. Black holes play a significant role in the dynamics of galaxies. Supermassive black holes at the centers of galaxies regulate star formation and galaxy evolution through their gravitational influence and the energetic processes associated with accretion of matter. The significance of supernovae, neutron stars and black holes extends beyond their role in cosmic element synthesis and structure formation. They are natural laboratories for extreme physics, allowing scientists to study conditions of gravity, density and energy that are unattainable on Earth. The observation and modeling of these phenomena have led to profound insights into the nature of matter, space and time. The formation of planetary systems around stars is a captivating chapter in the cosmic narrative, revealing how the swirling clouds of gas and dust coalesce into the diverse worlds that orbit our universe's countless stars. This process, while complex, begins with the collapse of a molecular cloud, much like the birth of stars themselves. Within these vast clouds, pockets of increased density, perhaps nudged by the shock wave from a nearby supernova, begin to collapse under their own gravity, forming a rotating disk of gas and dust around a new central star. This star, fueled by nuclear fusion, lights up its corner of the cosmos, while the material in the surrounding disk begins the intricate dance of planet formation. Over time, particles within the disk collide and stick together, forming clumps that grow into planetesimals, the building blocks of planets. Through a process of accretion, these planetesimals continue to collide and merge, growing into protoplanets. The inner part of the disk, where it is hotter, tends to form rocky planets like Earth and Mars. In contrast, the outer regions, where it's cold enough for ice to form, give rise to gas giants and icy worlds. But the journey from a swirling disk of debris to a bustling planetary system is influenced by several factors, not least of which is the central star's properties. Its mass, luminosity, and magnetic activity can significantly impact the formation process and the eventual composition of the planetary system. Additionally, interactions between emerging planets can lead to dynamic changes, with some being ejected from the system or colliding with others to form larger bodies. When considering what makes a planet habitable, the concept of the habitable zone, or the Goldilocks zone, comes to the forefront. This zone is the range of distances from a star where conditions might be just right, not too hot and not too cold, for liquid water to exist on a planet's surface, a crucial factor for life as we know it. However, being in the habitable zone is just one piece of the puzzle. A planet's atmosphere and magnetic field can also play critical roles in maintaining surface conditions conducive to life. An atmosphere can regulate temperature, protect the surface from harmful radiation, and provide essential elements for life, while a magnetic field can shield the planet from stellar winds, preserving its atmosphere over time. The planet's composition, geological activity, and the presence of water in liquid form are essential factors that contribute to its habitability. Geological activity, for instance, can recycle carbon through the planet's mantle and atmosphere, stabilizing the climate over geological timescales. The quest to discover exoplanets, planets beyond our solar system, employs a fascinating array of methods, each unveiling new worlds in the vast expanse of space. This pursuit not only expands our understanding of planetary systems, but also brings us closer to answering the age-old question, are we alone in the universe? One of the most successful techniques for finding exoplanets is the transit method, which detects the slight dimming of a star's light as a planet passes in front of it. This method has been particularly fruitful, thanks to missions like NASA's Kepler Space Telescope, which monitored the brightness of thousands of stars, uncovering a diverse array of exoplanets. Another technique is the radial velocity method, which measures the star's motion towards and away from us, caused by the gravitational tug of an orbiting planet. This method can provide information about the planet's mass and its orbit. Direct imaging, though challenging, involves capturing actual images of exoplanets by blocking out the star's light, allowing astronomers to study the planet's atmosphere. Meanwhile, the gravitational microlensing method relies on the bending of light from a distant star caused by a planet's gravitational field, briefly magnifying the distant star's light in a way that can reveal an orbiting planet. Among the thousands of exoplanets discovered, several stand out for their unique characteristics or potential habitability. For instance, Kepler-22b was one of the first planets found in the habitable zone of its star, raising possibilities of liquid water on its surface. Another intriguing world is TRAPPIST-1e, one of 7 Earth-sized planets orbiting the dwarf star TRAPPIST-1, which has captured imaginations with its potential for water and habitability. Then there's Proxima Centauri b, located in the habitable zone of Proxima Centauri, the closest star to the Sun. Its discovery sparked excitement about the possibility of studying a potentially habitable planet that's relatively nearby in cosmic terms. Meanwhile, HD 209458b, known as Osiris, stands out for being the first planet where an atmosphere was detected, offering a glimpse into the composition of exoplanetary atmospheres. Each of these discoveries brings a unique insight into the diversity and complexity of planetary systems across the galaxy. They also underscore the remarkable progress in our ability to detect and study distant worlds, moving us closer to understanding the conditions that might support life elsewhere in the cosmos. The ongoing search for exoplanets not only pushes the boundaries of our knowledge, but also continually redefines our place in the universe, reminding us of the endless possibilities that lie among the stars. The existence of dark matter and the effects of dark energy on the universe's expansion are among the most profound discoveries in modern cosmology, reshaping our understanding of the universe's composition and its dynamic evolution. Dark matter, a form of matter that does not emit, absorb, or reflect light, making it invisible to current telescopic technology, has been inferred through its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. One of the earliest pieces of evidence for dark matter came from the observation of the rotation curves of galaxies by Vera Rubin in the 1970s. Rubin found that stars at the outer edges of galaxies were moving faster than expected based on the visible mass alone, suggesting the presence of an unseen mass influencing their motion. Further evidence comes from the phenomenon of gravitational lensing, where the gravity of a massive object, like a galaxy cluster, bends the light of more distant galaxies behind it. The amount of bending observed indicates that there is much more mass present than what can be accounted for by visible matter alone, pointing to dark matter. Additionally, measurements of the cosmic microwave background radiation, the afterglow of the Big Bang, provide a snapshot of the early universe that matches predictions only when dark matter is included, reinforcing its existence. On the other hand, dark energy, a mysterious force driving the accelerated expansion of the universe, has been primarily evidenced by observations of distant supernovae. In the late 1990s, astronomers studying Type Ia supernovae, which serve as standard candles for measuring cosmic distances, discovered that these supernovae were fainter than expected. This faintness implies that the universe's expansion has been accelerating, not slowing down due to gravity as previously thought. This acceleration can be explained by the presence of dark energy, which constitutes about 68% of the total energy content of the universe. The effects of dark energy are not only observed in the accelerated expansion of the universe, but also have profound implications for its ultimate fate. If dark energy continues to dominate, the universe may continue expanding indefinitely, leading to a cold and empty cosmos in the far future. Alternatively, if dark energy's nature changes, it could lead to different scenarios, including the recollapse of the universe or an even more rapid expansion. Together, dark matter and dark energy form the foundation of the lambda cold dark matter model, the standard model of cosmology that describes the evolution of the universe from the Big Bang to its current state. Diving further into the unknown forces in space, we encounter phenomena such as quasars, pulsars, gamma-ray bursts, and the enigmatic nature of space magnetic fields. Each of these astronomical phenomena offers a unique window into the extreme environments and processes that govern the universe. Quasars, or quasi-stellar objects, are the intensely luminous hearts of distant galaxies, powered by supermassive black holes. As matter spirals into these black holes, it forms an accretion disk, heating up to incredible temperatures and emitting vast amounts of energy across the electromagnetic spectrum, especially as visible light, X-rays, and ultraviolet radiation. Quasars are among the most brilliant and distant objects in the universe, shining with the light of billions of stars, even though they are compact enough to fit within our solar system. They serve as crucial beacons in understanding the early universe, revealing how supermassive black holes grow and how galaxies form and evolve around them. Pulsars, on the other hand, are the remnants of massive stars that have exploded in supernovae and collapsed into dense neutron stars. These neutron stars are incredibly small, about 20 kilometers in diameter, but extraordinarily dense, with masses comparable to that of the Sun. Pulsars emit beams of electromagnetic radiation from their magnetic poles, and as they rotate, these beams sweep across space like the beams of a lighthouse. When the Earth intersects with one of these beams, we detect pulses of radiation, hence the name pulsar. Pulsars are precise cosmic clocks, allowing astronomers to study the properties of space and test theories of gravity. Gamma-ray bursts, or GRBs, are the most energetic explosions in the universe, briefly outshining entire galaxies with their extraordinary bursts of gamma rays. These bursts can last from a few milliseconds to several minutes and are thought to originate from two primary processes: the collapse of massive stars into black holes, leading to supernovae, or the collision of neutron stars. GRBs provide insights into the processes driving these cataclysmic events and the nature of the early universe, offering clues about the rate of star formation and the origins of heavy elements. Space magnetic fields, pervasive throughout the cosmos, play a fundamental role in shaping the interstellar medium, guiding cosmic rays, and influencing the formation and evolution of galaxies. These magnetic fields can be generated by the movement of conductive fluids inside stars and planets, a process known as the dynamo effect, or can be remnants from the early stages of the universe's formation. They are detected through their effects on cosmic particles and the polarization of light from distant stars and galaxies. Understanding space magnetic fields helps astronomers decipher the magnetic structures of galaxies, the behavior of interstellar gas and dust, and the dynamics of astrophysical jets. In the quest to understand life's potential beyond Earth, scientists have delineated essential conditions that must be met for life as we know it to thrive. These conditions include the presence of liquid water, a source of energy, and a suitable chemical environment that includes carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Liquid water acts as a solvent for biochemical reactions, energy is necessary for metabolic processes, and the right chemical elements are the building blocks of life. The search for signs of life, or biosignatures, on exoplanets and within our solar system employs a variety of innovative methods. For exoplanets, the transit method, which detects planets as they pass in front of their host stars, provides opportunities not only to discover new worlds, but also to analyze their atmospheres. During a transit, a small fraction of starlight filters through the planet's atmosphere, allowing scientists to identify the chemical signatures of gases that could indicate biological activity. For instance, the presence of oxygen, methane, or nitrous oxide in an exoplanet's atmosphere, especially in combinations unlikely to be produced abiotically, could suggest the possibility of life. Another method involves direct imaging, capturing light from the planets themselves, which allows for the study of their chemical composition, thermal structure, and even surface colors. Though challenging due to the faintness of planets compared to their stars, advances in technology are progressively making this more feasible. Within our solar system, missions to Mars, such as the rovers that traverse its surface, search for evidence of past or present microbial life by analyzing soil and rock samples. These rovers look for signs of organic compounds, water-related minerals, and isotopic signatures that could indicate biological processes. Europa and Enceladus, moons of Jupiter and Saturn respectively, with their subsurface oceans, are also prime candidates in the search for life. Future missions aim to probe these oceans, hidden beneath icy crusts, for signs of life, using techniques ranging from flybys that sample water plumes ejected into space to landers or ice-penetrating probes. The search for life beyond Earth also extends to Venus, where the discovery of phosphine gas in its atmosphere has spurred interest, despite the planet's extreme surface conditions. While the presence of phosphine could have non-biological explanations, it underscores the diverse environments in which scientists are searching for life. Human space exploration, aimed at unlocking the mysteries of the cosmos and ensuring the long-term survival of our species, faces a host of challenges alongside its ambitious objectives. From the technical and physiological hurdles of long-duration travel to the logistical and ethical considerations of colonization efforts, these endeavors push the limits of current technology and human resilience. One of the primary challenges in long-duration space travel is ensuring the health and well-being of astronauts. Extended periods in space expose crews to significant risks, including the effects of microgravity on muscle and bone density, radiation exposure outside the Earth's protective magnetosphere, and the psychological stresses of confinement and isolation. Addressing these concerns requires innovative solutions, such as improved radiation shielding, exercise regimes to combat muscle and bone loss, and measures to support mental health. Another significant hurdle is the development of life support and sustainability systems that can operate efficiently over long periods. These systems must provide air, water, and food, recycling as much as possible to minimize resupply missions. Advances in closed-loop life support systems, which recycle waste products back into usable resources, are crucial for long-duration missions and the sustainability of space habitats. The technical challenges of propulsion and energy supply are also paramount. Current propulsion technologies limit the speed at which spacecraft can travel, extending mission durations and the time astronauts are exposed to space's hazards. Developing faster propulsion systems, such as nuclear thermal or electric propulsion, could significantly reduce travel time, making missions to Mars and beyond more feasible. Additionally, reliable energy sources are essential for powering spacecraft and future colonies. Solar power, nuclear reactors, and in situ resource utilization, extracting and using materials found on other planets, are among the solutions being explored. As human presence in space expands to include longer missions and eventual colonization, ethical and logistical considerations come to the forefront. Who will have the right to visit or settle in space? How will we ensure the protection of other planets' environments? The establishment of legal and ethical frameworks for space exploration and the use of space resources is critical. The objectives of human space exploration are as varied and ambitious as the challenges. They include conducting scientific research to understand the universe and our place in it, searching for extraterrestrial life, testing technologies for living and working in space, and eventually establishing human settlements on other planets to ensure humanity's survival. Mars, with its relatively Earth-like characteristics, has been a primary focus for colonization efforts, but the Moon is also seen as a stepping stone for deeper space exploration. Fast radio bursts, or FRBs, are one of the cosmos's most mysterious phenomena, brief flashes of intense radio waves from space that last only milliseconds yet emit as much energy as the Sun does in days or even weeks. First discovered in 2007, these enigmatic signals have puzzled astronomers and sparked a flurry of research aimed at deciphering their origins and implications. Originating billions of light-years away, FRBs are characterized by their incredible brightness and short duration. Despite their fleeting nature, they have been detected in various parts of the sky, with some sources emitting repeated bursts while others are observed as singular events. This distinction has led researchers to propose different mechanisms for their origins. Theories range from highly magnetized neutron stars, known as magnetars, and their explosive activities, to more exotic possibilities, such as connections to black holes, or even, though highly speculative and without evidence, signals from advanced extraterrestrial civilizations. The study of FRBs is not just about understanding these bursts themselves, but also about using them as cosmic tools. Due to their journey through the vast expanses of the universe, FRBs interact with the intergalactic medium, allowing scientists to probe the unseen matter distributed throughout the cosmos. This interaction with electrons and magnetic fields in space alters the properties of the bursts, providing clues about the distribution of matter in the universe, including the elusive dark matter. Moreover, the localization of FRBs to specific galaxies has opened new avenues for cosmological studies. By measuring the dispersion and delay of the signals caused by their interaction with cosmic matter, astronomers can estimate the universe's large-scale structure and even test theories of gravity and relativity over cosmic distances. The ongoing detection and study of FRBs, facilitated by advancements in telescope technology and global collaboration among observatories, promise to unravel more about these cosmic enigmas. Each new discovery brings us closer to understanding not only the nature of FRBs, but also the fundamental properties of the universe, from the distribution of matter to the extreme conditions around compact objects like neutron stars and black holes. Now, let's talk about rogue planets. Enigmatic wanderers of the cosmos, they are worlds that do not orbit a star but instead drift through space on their own. These mysterious objects challenge our traditional views of planetary systems and offer intriguing insights into the diversity and dynamism of the universe. The origins of rogue planets are as fascinating as they are varied. Some may have formed in orbit around a star before being ejected from their native systems by gravitational interactions, possibly with other planets, or as a result of a passing star's disruptive influence. Others might have formed independently in vast molecular clouds, much like stars, but failed to acquire enough mass to ignite nuclear fusion and shine as stars do. These processes underscore the chaotic nature of young planetary systems and the fragile balance that allows planets to remain in stable orbits. Rogue planets are intriguing not only because of their solitary journeys through the galaxy, but also because of the implications they hold for our understanding of planetary formation and the potential for life beyond Earth. The discovery of these wandering worlds suggests that planetary systems may be more dynamic and varied than previously thought. It also raises the possibility that rogue planets could outnumber stars in our galaxy, pointing to a vast population of unseen objects drifting in the darkness of space. The study of rogue planets poses significant challenges, as their lack of a bright star makes them difficult to detect. However, techniques such as gravitational microlensing, where a rogue planet passes in front of a distant star and briefly magnifies its light, have provided evidence of their existence. Future observations with more sensitive instruments may reveal more about these elusive worlds, including their sizes, compositions, and the conditions on their surfaces. One of the most captivating questions surrounding rogue planets is whether they could harbor life. While the absence of a host star would seem to preclude the possibility of a life-supporting environment, some theories suggest that a thick atmosphere or internal heat sources, such as residual heat from formation or radioactive decay, could provide the necessary conditions for life in some form. The exploration of these possibilities opens new avenues for the search for life in the universe, extending beyond the traditional focus on planets within the habitable zones of stars. Diving deeper into these unusual cosmic mysteries, the WOW signal represents one of the most intriguing and enduring mysteries in the search for extraterrestrial intelligence. Detected on August 15, 1977, by the Big Ear radio telescope at Ohio State University, the WOW signal was a sudden, strong radio signal lasting 72 seconds, originating from the direction of the constellation Sagittarius. The signal's intensity and characteristics were so remarkable that upon reviewing the data, astronomer Jerry R. Amon circled the alphanumeric sequence representing the signal's intensity, 6 EKWJ5, and wrote WOW in the margin, giving the signal its name. The origins of the WOW signal have been the subject of speculation and investigation for decades. Its narrowband frequency, closely matching the hydrogen line, 1420 MHz, is what one might expect from an intentional broadcast because hydrogen is the most abundant element in the universe, making this frequency a logical choice for interstellar communication. However, despite numerous attempts, the signal has never been detected again, leading to a wide range of theories about its source, including interstellar scintillation, a passing comet, or a burst of natural background noise. Yet none of these explanations have definitively solved the mystery, leaving the possibility open that the signal could have been a transmission from an extraterrestrial civilization. The implications of the WOW signal extend far beyond its potential origins. It has significantly impacted the search for extraterrestrial intelligence, SETI, highlighting both the potential and the challenges of detecting and interpreting signals from beyond our planet. The WOW signal has underscored the importance of continuous monitoring of the cosmos for signs of intelligent life and has driven the development of more sensitive detection methods and protocols for verifying extraterrestrial signals. The WOW signal has captivated public imagination, serving as a poignant reminder of our place in the universe and the possibility that we are not alone. The fate of the universe, a subject of both fascination and intense study, is intertwined with cutting-edge theoretical frameworks like string theory, the concept of the multiverse, and the speculative possibilities of wormholes and time travel. These ideas not only expand our understanding of the cosmos, but also open up profound questions about the nature of reality and our place within it. One potential outcome for the universe's fate, based on current understanding, is the continued acceleration of its expansion, leading to a scenario known as the Big Freeze, or heat death. In this scenario, the universe would expand indefinitely, stars would burn out, and galaxies would drift apart, eventually leading to a cold, dark, and lifeless cosmos. This outcome is supported by observations of dark energy, a mysterious force that appears to be driving the acceleration of the universe's expansion. Another possibility is the Big Crunch, where the universe's expansion eventually reverses, leading all matter and energy to collapse back into a singularity, potentially setting the stage for another Big Bang. However, current observations suggest that the universe's expansion is accelerating, making the Big Crunch less likely. Theoretical frameworks like string theory, which proposes that the fundamental constituents of the universe are one-dimensional strings rather than point-like particles, offer a deeper understanding of the universe's fabric. String theory is also a cornerstone of the multiverse concept, which posits that our universe might be just one of many universes, each with its own physical laws and constants. This idea challenges the notion of our universe's uniqueness and raises the possibility that other universes could harbor vastly different forms of existence. Wormholes, hypothetical passages through space-time that could connect distant points in the universe or different universes altogether, offer intriguing possibilities for space travel and communication. While purely speculative at present and fraught with theoretical challenges, wormholes capture the imagination as potential shortcuts through the cosmos, opening up discussions about the nature of space-time and the possibility of interstellar or even interuniversal travel. Time travel, another speculative concept, is deeply entwined with our understanding of the universe's structure. While time travel to the future is theoretically possible through the effects of time dilation as predicted by Einstein's theory of relativity, travel to the past presents formidable paradoxes and challenges under current physical laws. However, the exploration of these concepts pushes the boundaries of our understanding of causality and the fabric of space-time. In exploring these potential outcomes and theoretical frameworks, we confront the limits of our current knowledge and the vastness of the unknown, the fate of the universe, the reality of the multiverse, and the possibilities of wormholes and time travel not only challenge our understanding of the cosmos, but also invite us to ponder the fundamental nature of existence. As we delve deeper into these mysteries, we continue to push the frontiers of science, philosophy, and our quest to understand the cosmos. The likelihood of extraterrestrial life and intelligence has long captivated scientists and the public alike, leading to the development of several frameworks and efforts aimed at understanding and finding life beyond Earth. Central to this quest is the Drake equation, a probabilistic formula proposed by astronomer Frank Drake in 1961 to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. The Drake equation synthesizes several variables into a single formula, each representing a factor considered necessary for the development of such civilizations. These factors include the rate of star formation in our galaxy, the fraction of those stars that have planetary systems, the number of planets per solar system with an environment suitable for life, the fraction of suitable planets on which life actually appears, the fraction of life-bearing planets on which intelligent life evolves, the fraction of civilizations that develop a technology that releases detectable signs of their existence into space, and the length of time such civilizations release detectable signals into space. While the equation provides a framework for estimating the number of extraterrestrial civilizations, the actual values of most of its variables remain uncertain. This uncertainty stems from our limited knowledge of the processes that lead to the emergence of life and the development of technological civilizations, as well as the vastness and complexity of the Milky Way galaxy. Consequently, estimates of the number of communicative civilizations in the galaxy have varied widely, depending on the values assigned to the variables in the equation. Despite its uncertainties, the Drake equation has played a crucial role in framing the scientific discussion about extraterrestrial life and guiding research and exploration efforts. It highlights the key factors that influence the emergence of life and civilization beyond Earth, and serves as a starting point for debates and studies in astrobiology and the search for extraterrestrial intelligence. The efforts of SETI, an initiative dedicated to searching for signs of intelligent life beyond Earth, have been directly influenced by the Drake equation. SETI researchers use a variety of techniques, including listening for radio and optical signals that might be emitted by extraterrestrial technologies. Although no definitive evidence of extraterrestrial intelligence has been found to date, SETI's ongoing efforts underscore the scientific community's commitment to exploring the possibility of life beyond our planet. Following the exploration of the Drake equation, we encountered the Fermi paradox, which starkly contrasts the equation's optimistic numbers with the conspicuous silence of the cosmos. Named after physicist Enrico Fermi, the paradox articulates a compelling contradiction. Given the high probability of extraterrestrial civilizations' existence, why have we found no evidence of them? The universe is vast, with billions of stars in our galaxy alone, many of which host planets in habitable zones where life as we know it could thrive. The age of the universe allows ample time for intelligent life to arise and make its presence known across the cosmic expanse. Yet, our searches for signals or signs of such civilizations have yielded nothing but silence. This silent void raises profound questions about the nature of life in the universe and our understanding of it. Several hypotheses have been proposed to explain the Fermi paradox. One suggestion is that while life may be common, the emergence of intelligent life capable of interstellar communication is exceedingly rare. Another possibility is the Great Filter hypothesis, which posits that there is a highly improbable step required for life to progress from simple to complex and intelligent forms, and humanity has either passed this filter or it lies ahead, posing a dire risk to our survival. Other explanations delve into the behavior and fate of civilizations, suggesting that technological civilizations may have short lifespans, either self-destructing or shifting their communications to modes undetectable to us. Additionally, there's the concept of the zoo hypothesis, which speculates that extraterrestrial civilizations intentionally avoid contact with humanity to allow for natural evolution and societal development, much like zookeepers trying to avoid disturbing the animals. Diving into the realm of cosmic anomalies brings us to the Great Attractor, a mysterious region in space that exhibits a gravitational force strong enough to affect the motion of galaxies over hundreds of millions of light-years. Located in the direction of the Hydra and Centaurus constellations, the Great Attractor lies at a distance of approximately 220 million light-years from Earth. This region poses a significant puzzle to astronomers, because it influences the velocities of galaxies, including our own Milky Way, drawing them towards it at an astonishing rate of millions of kilometers per hour. The complexity of studying the Great Attractor stems from its position in the zone of avoidance, an area of the sky obscured by the dust and gas of the Milky Way's galactic plane, making direct observation challenging. Despite these difficulties, advances in X-ray and radio astronomy have allowed scientists to peer through the galactic dust and begin to unravel the mystery. The evidence suggests that the Great Attractor is not a single massive entity, but rather a concentration of galaxy clusters, forming a part of an even larger structure known as the Laniakea supercluster, which encompasses our galaxy and about 100,000 others. The gravitational pull of the Great Attractor and its role in the motion of galaxies highlight the interconnectedness of cosmic structures and the dynamic nature of the universe. It serves as a reminder of the vast scales and forces at play beyond our local environment, pushing the boundaries of our understanding of the cosmos. Diving into the mysteries of our solar system, unusual comet orbits stand out as celestial puzzles that intrigue scientists and astronomers. Comets, often described as dirty snowballs, are composed of ice, rock, and organic compounds, and their orbits can tell us a great deal about the outer reaches of our solar system and the forces at play within it. Some comets exhibit highly eccentric orbits, bringing them close to the Sun, where they develop spectacular tails, before sending them back into the distant reaches of the solar system, or even ejecting them from the solar system entirely. These orbits challenge our understanding of the solar system's dynamics and hint at the influence of unseen objects or events. One explanation for these unusual orbits is the gravitational influence of the Oort cloud and the Kuiper belt, two vast regions of space filled with icy bodies located beyond the orbit of Neptune. The Oort cloud in particular is thought to be a spherical shell surrounding the solar system, home to billions of comets. Occasionally, the gravitational pull from passing stars or the galactic tide, the gravitational force exerted by the Milky Way itself, can disturb comets in these regions, sending them into the inner solar system on highly eccentric orbits. Another fascinating theory involves the presence of an as-yet undiscovered massive object in the outer solar system, sometimes referred to as Planet 9. This hypothetical planet could be responsible for the unusual orbits observed in some trans-Neptunian objects and comets, shepherding them into orbits that confound expectations based on the known gravitational influences of the solar system. The study of comet orbits not only deepens our understanding of the solar system's structure and the forces shaping it, but also provides insights into the solar system's history. By tracing the paths of these icy wanderers, scientists can glean information about the distribution of mass in the solar system's outer regions and the potential for interactions with interstellar objects. As our observational techniques and computational models improve, so too will our understanding of these unusual comet orbits, offering answers to long-standing questions and undoubtedly raising new ones about the complex dance of celestial bodies within our solar system. Titan and Enceladus, two of Saturn's moons, are captivating celestial bodies that have intrigued scientists with their unique and complex phenomena, significantly advancing our understanding of the diversity and potential habitability of environments within our solar system. Titan, Saturn's largest moon and the second largest in the solar system, is enveloped by a thick, nitrogen-rich atmosphere that is laced with organic molecules, some of which are the building blocks of life as we know it. This dense atmosphere creates a veiled world beneath, with a surface showcasing rivers, lakes, and seas, not of water, but of methane and ethane. These hydrocarbon seas are of particular interest because they represent an environment entirely alien to Earth, yet possibly capable of supporting life forms adapted to cold, liquid methane environments. Additionally, Titan's atmosphere undergoes a cycle similar to Earth's water cycle, but with methane and ethane, including clouds, rain, and liquid bodies on the surface, offering a fascinating parallel to Earth's hydrological dynamics in an utterly alien context. Enceladus, on the other hand, is a smaller moon of Saturn, famous for its active geysers ejecting plumes of water vapor and ice particles from cracks in its icy surface. These geysers hint at a subsurface ocean beneath the moon's icy crust, raising the tantalizing possibility of an environment where life could exist. The ejected material, which contributes to one of Saturn's rings, has been directly sampled by spacecraft, revealing complex organic compounds, salts, and silica particles. The presence of these compounds suggests that Enceladus's ocean is not only liquid, but also in contact with the Moon's rocky mantle, where hydrothermal processes could provide the energy necessary for life. The phenomena observed on Titan and Enceladus underscore the diversity of potentially habitable environments in our solar system beyond the Earth. Titan challenges our concepts of habitability with its cold hydrocarbon-based system, while Enceladus presents a more familiar water-based potential habitat, albeit under the ice. Both moons exemplify the varied ways in which the conditions for life might exist and persist in the cosmos, expanding the search for extraterrestrial life to include worlds with environments radically different from our own. As missions continue to explore these moons and others like them, we inch closer to understanding the complexity of the solar system's moons, the processes that drive their unique phenomena, and the potential for life in environments once thought to be inhospitable. The nature of spacetime, a foundational concept in modern physics, intertwines the three dimensions of space with the one dimension of time into a single four-dimensional continuum. This revolutionary idea, rooted in Albert Einstein's theory of general relativity, posits that the presence of mass and energy warps the fabric of spacetime, dictating the motion of objects and the flow of time itself. Spacetime is not a static backdrop against which events unfold, but an active, dynamic entity that is shaped by and shapes the universe's contents. The Sun, Earth, and all celestial bodies, through their mass, create curvatures in spacetime that dictate their gravitational interactions. This curvature is what we perceive as gravity. For instance, Earth orbits the Sun not because it is being pulled by the Sun in a direct manner, but because the Sun's massive presence has curved spacetime in such a way that Earth's path through space is a stable orbit. The implications of spacetime being a malleable fabric extend to how we understand the movement of light, the flow of time, and the structure of the universe. Light, although it has no mass, follows the curvature of spacetime, leading to phenomena such as gravitational lensing, where light from a distant star is bent around a massive object like a galaxy cluster. Similarly, the flow of time is affected by the warping of spacetime. Time moves slower in stronger gravitational fields, a prediction of general relativity confirmed by precise experiments. This effect, known as gravitational time dilation, has practical applications, such as adjustments made to account for time differences between GPS satellites in orbit and receivers on Earth. The concept of spacetime has not only deepened our understanding of gravity, but also laid the groundwork for exploring more complex phenomena, such as black holes and the expansion of the universe. Black holes, regions of spacetime with gravity so strong that nothing, not even light, can escape, represent extreme distortions of spacetime where the known laws of physics reach their limits. The universe's expansion, on the other hand, suggests that spacetime itself is stretching, carrying galaxies with it, and leading to the observed redshift of distant galaxies. The concept of the universe as finite yet unbounded is one of the most intriguing aspects of modern cosmology, offering a way to reconcile the vastness of the cosmos with the possibility of its having a limited volume. This idea, rooted in the geometry of spacetime described by general relativity, suggests that the universe can be spatially finite without having any edges or boundaries. To understand this concept, one can draw an analogy with the surface of the Earth. Imagine the Earth's surface as a two-dimensional space. It is finite in area, meaning you can only travel so far before returning to your starting point, yet it has no edges where you could fall off. Extending this analogy to the three-dimensional space of the universe, it's possible for the universe to curve back onto itself in a higher dimension, creating a closed geometry. In such a universe, if you could travel far enough in a straight line, you would eventually return to your starting point, despite never encountering a boundary or edge. This concept arises from Einstein's theory of general relativity, which allows for various possible shapes of the universe depending on its density and the nature of its expansion. A closed universe, one that is finite yet unbounded, would result from a density high enough to eventually halt the expansion of the universe and reverse it into a contraction, leading to a big crunch. However, current observations, including measurements of the cosmic microwave background radiation and the rate of the universe's expansion, suggest that the universe is flat on large scales and likely infinite in extent. Yet, the possibility of a finite yet unbounded universe remains a fascinating topic of theoretical exploration. The potential for higher dimensions beyond the three spatial dimensions and one time dimension we experience in our daily lives opens up a realm of fascinating possibilities that stretch the boundaries of our understanding of the universe. This concept, which is integral to several advanced theories in physics, including string theory and M-theory, suggests that the universe contains more dimensions than are apparent to us. In string theory, for instance, particles are not point-like entities but rather one-dimensional strings that vibrate at different frequencies. These vibrations determine the particle's properties, such as mass and charge. To be consistent and free of anomalies, string theory requires the existence of additional spatial dimensions, specifically 10 dimensions, 9 spatial dimensions plus 1 time dimension. These extra dimensions are hypothesized to be compactified or curled up at scales so small that they are undetectable by current instruments. The existence of higher dimensions could provide explanations for several phenomena in physics that are otherwise difficult to account for, such as the relative weakness of gravity compared to the other fundamental forces. If gravity can leak into extra dimensions, this could explain why it appears weaker in the four-dimensional space-time we inhabit. Moreover, higher dimensions offer intriguing possibilities for the universe's structure and the fundamental nature of reality. They could allow for parallel universes or multiple branes, multidimensional objects, floating in a higher dimensional space with our observable universe residing on one of these branes. Interactions between branes in the higher dimensional space could potentially give rise to phenomena within our four-dimensional universe, such as the Big Bang. The exploration of higher dimensions also has implications for unifying the forces of nature. The quest for a theory of everything, a single, coherent theoretical framework that fully explains and links together all physical aspects of the universe, relies on the concept of higher dimensions to unify general relativity, which governs the macroscopic world, with quantum mechanics, which governs the subatomic world. The Sun, a colossal sphere of hot plasma at the center of our solar system, maintains its energy output through a process known as nuclear fusion. At its core, the Sun fuses hydrogen atoms into helium under extreme pressures and temperatures, a reaction that releases immense amounts of energy. This process is not only the source of the Sun's light and heat, but also the engine driving its long-lasting luminosity. In the Sun's core, where temperatures soar above 15 million degrees Celsius, 27 million degrees Fahrenheit, hydrogen atoms are squeezed under such tremendous pressure that they overcome their natural repulsion for one another. This environment facilitates the fusion of hydrogen nuclei, protons, to form helium-4 nuclei in a series of steps known as the proton-proton chain reaction. Each of these fusion reactions converts a tiny amount of mass into energy, according to Einstein's famous equation E equals mc squared, where E is energy, m is mass, and c is the speed of light. This energy is initially released as gamma rays, which then make their way to the Sun's surface, or photosphere, taking thousands of years. By the time this energy reaches the surface and is emitted as sunlight, it has mostly been transformed into visible light and other electromagnetic radiation. This fusion process is incredibly efficient, converting millions of tons of hydrogen into helium each second, yet it is also slow enough that the Sun has been shining for about 4.6 billion years, and will continue to do so for approximately 5 billion more. The Sun's stability and consistent energy output are crucial for life on Earth, providing the warmth and light necessary for life processes. Solar phenomena, ranging from the benign to the potentially disruptive, have profound effects on Earth, influencing everything from our planet's climate to the technology we rely on daily. These phenomena include solar flares, coronal mass ejections, CMEs, solar wind, and the solar cycle, each impacting Earth in unique ways. Solar flares are intense bursts of radiation emanating from the release of magnetic energy associated with sunspots. While the light from a solar flare can reach Earth in just 8 minutes, the high-energy particles can take hours to days to arrive. Solar flares can affect radio communications, GPS signals, and power grids by ionizing the Earth's upper atmosphere, the ionosphere, disrupting the propagation of radio waves. Coronal mass ejections, or CMEs, are massive bursts of solar wind and magnetic fields rising above the solar corona or being released into space. CMEs can eject billions of tons of coronal material and carry an embedded magnetic field, frozen in flux, that is stronger than the background solar wind interplanetary magnetic field strength. When these ejections collide with the Earth's magnetosphere, they can cause geomagnetic storms, potentially disrupting satellite operations, power grids, and navigation systems. The interaction of CMEs with the Earth's magnetosphere can also lead to spectacular auroras near the polar regions. Solar wind, a stream of charged particles released from the upper atmosphere of the Sun, the corona, affects Earth's magnetosphere and can lead to geomagnetic storms. Continuous but varying in intensity, the solar wind interacts with Earth's magnetic field, compressing it on the day side and extending the night side magnetic tail. This interaction can energize particles trapped in the Earth's magnetosphere, causing them to precipitate into the Earth's upper atmosphere and produce auroras. The solar cycle, an approximately 11-year cycle that marks the rhythmic increase and decrease in solar activity, including the frequency of sunspots, solar flares, and CMEs, influences Earth's climate and space weather conditions. During periods of maximum solar activity, or solar maxima, the Sun emits more ultraviolet radiation, which can lead to greater ozone production in Earth's stratosphere, affecting atmospheric circulation patterns and potentially influencing weather and climate on a regional scale. Beyond these direct impacts, solar phenomena can have broader implications for Earth. For instance, prolonged periods of low solar activity, such as the Maunder minimum in the 17th century, have been associated with cooler global temperatures, suggesting a link between solar activity and climate. Moreover, the increasing reliance on technology makes our society more vulnerable to the effects of solar storms on communication and navigation systems, highlighting the importance of monitoring solar activity and developing resilience strategies. Speculating on the characteristics of advanced civilizations beyond our own involves a fascinating blend of scientific knowledge, philosophical inquiry, and imaginative thinking. Such civilizations, if they exist, would likely have mastered technologies and societal structures far beyond our current capabilities. Their characteristics can be explored through various frameworks, including the Kardashev scale, which categorizes civilizations based on their energy consumption and technological capabilities. A Type 1 civilization on the Kardashev scale has harnessed the energy resources of its entire planet. This would include the full utilization of solar energy, geothermal energy, and other planetary resources. Such a civilization would have overcome many of the environmental and societal challenges we face, such as climate change and energy scarcity. They might have advanced forms of sustainable living with technologies that efficiently recycle waste, manage ecosystems, and possibly control weather patterns to optimize agricultural productivity and prevent natural disasters. A Type 2 civilization extends its energy harnessing capabilities to its entire star system. This includes, most famously, the concept of a Dyson sphere, or similar megastructures that could capture a significant portion or all of the energy output of their star. With such energy at their disposal, these civilizations would likely have mastered space travel within their system, possibly colonizing and terraforming other planets and moons. They could have technologies that manipulate the orbits of planetary bodies, redirect asteroids for mining or defense, and harness the power of other phenomena like black holes or neutron stars. A Type 3 civilization, the pinnacle of the Kardashev scale, controls energy on the scale of its entire galaxy. The capabilities of such a civilization are difficult to fathom. They might be capable of interstellar travel, creating and destroying stars, manipulating the fabric of space-time, and possibly even accessing and exploiting the energy of parallel universes if such concepts are physically meaningful. Their understanding of physics and the universe would be so advanced that their technologies would seem almost magical to us. Across these speculative stages, several characteristics of advanced civilizations can be inferred. Advanced civilizations would possess technology that integrates seamlessly with the laws of physics, possibly blurring the lines between technology and nature. Their technologies would likely be sustainable, highly efficient, and capable of manipulating matter and energy at fundamental levels. The survival of a civilization to reach higher levels of the Kardashev scale implies a degree of social and ethical maturity. They would need to have overcome self-destructive tendencies, such as warfare and exploitation, achieving a harmonious balance between technological advancement and peace. Advanced civilizations would likely retain a drive for exploration and knowledge, pushing the boundaries of science, philosophy, and possibly even transcending physical existence in ways we cannot imagine. The methods and motives for communication with other civilizations, if they choose to do so, would reflect their advanced understanding and capabilities. They might engage in the seeding of life, mentoring younger civilizations, or ensuring the stability of the cosmos against existential threats. A deeper understanding of the universe has profound implications for our perception of our place within the cosmic tapestry. As our knowledge expands through advancements in astronomy, physics, and cosmology, we are continually reminded of the vastness of the universe and the intricate complexities that govern its workings. This expanding understanding influences our perception in several significant ways, reshaping our worldview and challenging our assumptions about life, existence, and our significance in the cosmos. One of the most striking realizations that come from delving deeper into the universe's mysteries is the recognition of our sheer smallness. The universe is unimaginably vast, with billions of galaxies, each containing billions of stars and potentially countless planets. This realization can evoke a sense of humility, highlighting the fragility and preciousness of life on our tiny planet in the vast expanse of space. It underscores the rarity and value of our existence, fostering a sense of universal stewardship and a desire to preserve and cherish the delicate balance of life on Earth. Simultaneously, our deepening understanding of the universe can also inspire a sense of connection and unity. The laws of physics that govern the movement of galaxies also influence the smallest particles on Earth. The same elements that make up the stars are found within us. This universal commonality suggests a profound interconnectedness of all things, from the smallest to the grandest scales, reinforcing the idea that we are an integral part of the cosmos, not mere observers or accidents. The exploration of the universe and the search for extraterrestrial life expand our notions of habitability and life's potential diversity. Discoveries of exoplanets in habitable zones around other stars, and studies of extreme environments on Earth where life thrives, suggest that life could be more common and varied than previously imagined. This possibility challenges anthropocentric views and invites us to consider a broader spectrum of life forms and intelligences, potentially reshaping our understanding of life's nature and the possibilities for communication and interaction with non-human intelligences. The interactions between dark matter and baryonic matter, the normal matter that makes up stars, planets, and all visible objects, play a crucial role in shaping the structure and dynamics of galaxies, influencing both their shape and rotation curves in significant ways. Dark matter, though invisible and not directly detectable, constitutes about 85% of the universe's total matter content. Its presence is inferred from its gravitational effects on visible matter, light, and the structure of the universe. One of the key insights into dark matter comes from observing galaxy rotation curves, the way the velocity of stars and gas clouds orbiting the galaxy center changes with distance from the center. According to Newtonian mechanics, one would expect the rotational speed of objects orbiting a galaxy's center to decrease with distance from the center, similar to how planets in the solar system orbit the sun. However, observations show that the rotational speeds of stars in galaxies remain constant or even increase slightly with distance from the galactic center, defying these expectations. This discrepancy suggests the presence of a substantial amount of unseen mass, attributed to dark matter, exerting gravitational influence. Dark matter forms vast halos that envelop galaxies, extending far beyond the visible edge of the galaxy. The gravitational pull of this dark matter halo is what keeps stars moving at higher velocities than would be expected based solely on the visible mass. This not only explains the flat rotation curves of galaxies, but also plays a critical role in their formation and evolution. During the early stages of the universe, dark matter clumps formed the gravitational scaffolding around which baryonic matter coalesced to form stars, galaxies, and larger structures. The distribution and density of dark matter in these halos influenced the shape and type of galaxies that formed. For instance, dense, compact halos might lead to the formation of elliptical galaxies, while more extended halos with specific angular momentum distributions can give rise to spiral galaxies. The interactions between dark matter and baryonic matter are essential for understanding the large-scale structure of the universe. Dark matter's gravitational effects enhance the clumping of matter in certain regions, leading to the web-like structure of the cosmos, with galaxies and clusters of galaxies linked by filaments of dark matter and separated by vast voids. Discoveries about the intergalactic medium, or IGM, have significantly reshaped our understanding of galaxy formation, highlighting the dynamic and interconnected nature of the universe. The IGM, which consists of diffuse gas and plasma that fills the vast spaces between galaxies, plays a critical role in the cosmic web's structure and evolution, acting as both a reservoir for galaxy formation and a record of the processes that shape the universe. One key discovery is the detection of the cosmic web, a vast network of filamentary structures composed of dark matter and gas that stretches across the universe, linking galaxies and galaxy clusters. Observations, particularly through the absorption lines in the spectra of distant quasars, bright active galaxies far away, have revealed the presence of hydrogen and other elements in the IGM. These absorption lines, known as the Lyman alpha forest, have provided valuable insights into the distribution, temperature, and composition of the IGM, confirming the existence of the cosmic web and its role in galaxy formation. The realization that the IGM is not only a repository of matter, but also a dynamic participant in galaxy evolution, has been transformative. Gas from the IGM falls into the gravitational wells created by dark matter, cooling and condensing to form stars and galaxies. This process, known as accretion, is fundamental to galaxy formation and growth. Furthermore, feedback mechanisms from star formation and active galactic nuclei, where energy is injected back into the IGM, regulate the flow of gas into and out of galaxies, influencing their ability to form stars. Another groundbreaking discovery has been the detection of the missing baryons. Early observations of galaxies and galaxy clusters accounted for only a fraction of the ordinary matter predicted by the Big Bang theory. Studies of the IGM have uncovered these missing baryons in the form of warm-hot intergalactic medium, or WIM, a tenuous, partially ionized gas that permeates the filaments of the cosmic web. The WIM had been difficult to detect due to its diffuse nature and the high temperatures at which it emits and absorbs radiation. But recent observations using X-ray and ultraviolet telescopes have begun to reveal its properties and distribution. The mass of a star is the principal determinant of its life cycle, dictating not only how the star lives, but also how it dies. This mass influences the star's core pressure and temperature, determining the nuclear fusion reactions that can occur, and thus the star's luminosity, temperature, and lifespan. Depending on its initial mass, a star may end its life as a white dwarf, neutron star, or black hole, each marking a different evolutionary path in the cosmos. Stars with masses up to about 8 times that of the Sun follow a similar evolutionary path. They spend the majority of their lives fusing hydrogen into helium in their cores, a phase known as the main sequence. Once the hydrogen fuel is exhausted, these stars expand into red giants, where the core contracts and heats up, enabling the fusion of helium into carbon and oxygen in a shell around the core. For stars like the Sun, This is where nuclear fusion essentially ends. When the nuclear fuel is depleted, the outer layers of the star are ejected, creating a planetary nebula, while the core remains as a white dwarf, a hot, dense remnant roughly the size of Earth, but with a mass close to the Sun's. White dwarfs gradually cool and fade over billions of years. Stars with masses significantly greater than the Sun undergo more complex and energetic lives. After exhausting their hydrogen, these stars become supergiants and can fuse heavier elements in their cores, sequentially burning through helium, carbon, oxygen, and so on, up to iron. Iron fusion, however, consumes energy rather than releases it, leading to a rapid core collapse once a significant amount of iron has accumulated. This collapse triggers a supernova explosion, one of the universe's most spectacular events. The star's outer layers are blown away, while the core collapses into an extremely dense object. If the core's mass is about 1.4 to 3 times that of the Sun, the Chandrasekhar limit, it becomes a neutron star, an object so dense that protons and electrons combine to form neutrons. A sugar cube-sized amount of neutron star material would weigh as much as a mountain on Earth. For cores with masses exceeding roughly 3 solar masses, the gravitational collapse results in a black hole, a point in space where gravity is so strong that not even light can escape. The Schwarzschild radius, or event horizon, marks the boundary beyond which nothing can return. The mass of a star, therefore, sets the stage for its entire life and ultimate fate, from tranquil existences marked by gentle winds of ejected material to violent ends that outshine galaxies. These end states, white dwarfs, neutron stars, and black holes, contribute to the cosmic cycle of matter, seeding the universe with the heavy elements forged in their crucibles, elements that will become part of future stars, planets, and possibly life forms, continuing the grand cycle of cosmic evolution. The study of binary star systems, pairs of stars orbiting a common center of mass, plays a crucial role in enhancing our understanding of stellar evolution and the synthesis of heavy elements. These systems, which make up a significant portion of the stars in the universe, offer unique insights into the lives and deaths of stars, especially in scenarios where one star can significantly influence the evolution of its companion. Binary star systems provide natural laboratories for studying stellar evolution under the influence of a companion. Observing how stars in binary systems interact allows astronomers to test and refine models of stellar structure, evolution, and nucleosynthesis, the process by which stars create heavier elements from lighter ones. One critical phase observed in some binary systems is mass transfer. If one star expands into a red giant or supergiant phase, material from its outer layers can spill over onto its companion, altering the recipient star's mass, composition, and evolutionary path. This process can lead to a variety of exotic objects and phenomena, including blue stragglers, stars that appear younger than they are, cataclysmic variables, and symbiotic stars. Through mass transfer, binary systems can bypass certain evolutionary stages or accelerate into later stages, providing insights into the flexibility and diversity of stellar evolution. Binary star systems, particularly those involving compact objects like white dwarfs, neutron stars, or black holes, are key sites for the synthesis of heavy elements. The most famous example is the merger of 2 neutron stars, which was observed in 2017 through both gravitational waves and electromagnetic radiation. This landmark event confirmed that neutron star mergers are a primary site for the rapid neutron capture process, our process, a nucleosynthesis pathway responsible for creating approximately half of the elements heavier than iron, including gold and platinum. Similarly, systems where a white dwarf accretes material from a companion until it reaches a critical mass can undergo a thermonuclear explosion known as a Type Ia supernova. These supernovae play a vital role in enriching the interstellar medium with iron peak elements and provide a standard candle for measuring cosmic distances. Interactions in binary systems can lead to scenarios where elements synthesized in one star are exposed to the surface of another, offering observable clues about internal processes like dredge-ups and nucleosynthesis that occur in stars. Binary systems are also crucial for understanding the end stages of stellar evolution. For instance, The observation of binary systems containing black holes or neutron stars can shed light on the life cycles of massive stars and the conditions needed to form these dense remnants. The gravitational wave detections from merging black holes and neutron stars in binary systems have opened a new era of astronomy, providing insights into the properties of matter at extreme densities, the rates of such mergers, and their role in the universe's evolution. The exploration of exoplanet atmospheres, though still in its infancy, has already begun to reveal the astonishing diversity of environments that exist beyond our solar system. By comparing these atmospheres to those of planets within our solar system, scientists are uncovering clues about the formation, composition, and potential habitability of these distant worlds. This comparison is crucial for understanding the vast range of planetary environments and assessing the potential for life elsewhere in the universe. Exoplanet atmospheres exhibit a wide range of compositions, temperatures, and weather patterns, some of which are similar to the planets in our solar system, while others are entirely alien. For instance, hot Jupiters, gas giants that orbit very close to their stars, have been found with atmospheres dominated by hydrogen and helium, similar to Jupiter and Saturn, but at temperatures so high that they can vaporize metals. Observations have detected iron, titanium, and even water vapor in the atmospheres of some of these exoplanets, under conditions vastly different from those found in the solar system. Smaller rocky exoplanets have also been observed, with some showing evidence of atmospheres that could potentially harbor water vapor, a key ingredient for life as we know it. However, the range of atmospheric compositions is broad, with some exoplanets exhibiting atmospheres rich in carbon dioxide or methane, and others with no atmosphere at all, reminiscent of Mercury or the Moon. The diversity of exoplanet atmospheres provides insights into the processes of planet formation and evolution. For example, the presence of heavy elements and compounds in the atmospheres of hot Jupiters suggests a complex history of accretion and possibly indicates interactions with the protoplanetary disk or other bodies in their systems. Similarly, the variety in the atmospheric composition of rocky exoplanets points to differences in their initial material, distance from their star, and geological activity. When assessing the potential for life, the comparison of exoplanet atmospheres to those in our solar system highlights the importance of an atmosphere's composition and stability. An atmosphere that can retain liquid water on the planet's surface, protect life from harmful radiation, and maintain a stable climate over geological timescales is ideal. In our solar system, Earth is the only planet that meets all these criteria, serving as a model for identifying potentially habitable exoplanets. The detection of biosignature gases such as oxygen, ozone, methane, or nitrous oxide in an exoplanet's atmosphere could suggest biological activity, especially if these gases are found in combinations that are unlikely to be produced through abiotic processes alone. However, the interpretation of these signatures is complex, as they can also be produced by non-biological means under certain conditions. Recent findings in the field of planetary science have significantly challenged and expanded our understanding of planet formation and the diversity of planetary systems. These discoveries, made possible by advanced telescopes and space missions, have unveiled a cosmos filled with an astonishing variety of planets and planetary systems, pushing the boundaries of existing theoretical models. One of the most striking revelations has been the discovery of hot Jupiters, gas giants that orbit very close to their host stars, in environments much hotter than those in which gas giants form within our solar system. Their existence challenges traditional models of planet formation, which suggest that gas giants should form in the colder outer regions of a planetary system before possibly migrating inward. The mechanisms of this migration and the conditions under which these planets form and survive in such close proximity to their stars are active areas of research, prompting scientists to rethink theories of planetary system evolution. Another surprising discovery has been that of super-Earths and mini-Neptunes, types of planets with no direct analogue in our solar system. These planets, which range in mass between Earth and Neptune, raise questions about the processes that determine planet composition and the transition between rocky planets and gas giants. The diversity in size, density, and composition of these planets suggests a complexity in planet formation processes that was not anticipated in earlier models, which primarily focused on the solar system's architecture. The finding of planetary systems around binary and even trinary star systems further challenges our understanding. While the formation of stable planetary orbits in such dynamic environments was once thought to be improbable, numerous planets have been discovered in these complex settings. This has implications for the dynamics of planet formation and survival, indicating that planetary systems can be more resilient and versatile than previously believed. Additionally, the detection of free-floating planets, those not bound to any star and wandering through the galaxy, suggests that planet ejection from developing or mature planetary systems might be more common than anticipated. This challenges our understanding of the stability and longevity of planetary systems and raises questions about the mechanisms driving these ejections. These findings, among others, are reshaping our understanding of the diversity of planetary systems and the processes of planet formation. They highlight the unique characteristics of our solar system and its formation, while unveiling the broad range of environments in which planets can form and evolve. As a result, astronomers and planetary scientists are continually refining their theories, incorporating new observations, and developing more sophisticated models to account for the diversity and complexity of planetary systems throughout the galaxy. Dark energy, a mysterious force that is accelerating the expansion of the universe, constitutes about 68% of the universe's total energy. Its discovery in the late 1990s through observations of distant supernovae has profoundly shifted our understanding of the cosmos, presenting new questions about the universe's fate and the laws that govern it. The latest theories and experiments aimed at understanding dark energy are diverse, ranging from modifications of Einstein's theory of general relativity to innovative observational campaigns. One leading theoretical approach is the concept of quintessence, a dynamic field that changes over time and space, unlike the cosmological constant, which Einstein originally introduced to his equations of general relativity to allow for a static universe and later abandoned. Quintessence models suggest that the strength of dark energy could vary, providing a possible explanation for why the expansion of the universe is accelerating now after billions of years of deceleration following the Big Bang. Another area of exploration involves theories of modified gravity, which propose that the observed acceleration could be due to new aspects of gravity not accounted for in general relativity, especially over large scales. These theories challenge our fundamental understanding of gravity and require rigorous testing through observations. On the experimental front, several ambitious projects are underway to probe the nature of dark energy and its effects on the cosmos. The Dark Energy Survey, DES, using a powerful digital camera mounted on a telescope in Chile, has mapped millions of galaxies to study the structure of the universe over vast scales and time periods. By analyzing how clusters of galaxies have grown over time under the influence of dark energy, scientists hope to shed light on its properties. Similarly, the upcoming Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, promises to provide unprecedented insights into dark energy. By surveying the sky in detail over 10 years, LSST aims to uncover the nature of dark energy by observing billions of galaxies and tracking how the universe's expansion has evolved. Another pioneering effort is the Euclid mission, a space telescope developed by the European Space Agency, scheduled for launch in the near future. Euclid is designed to map the geometry of the dark universe by measuring the distribution of galaxies and the bending of light, gravitational lensing, caused by dark matter and dark energy, offering clues about the underlying physics driving the universe's expansion. Gravitational lensing, a phenomenon predicted by Albert Einstein's general theory of relativity, has become an invaluable tool in the study of dark matter distribution across the universe. This phenomenon occurs when the gravitational field of a massive object, such as a galaxy or cluster of galaxies, warps the fabric of space-time around it, bending the path of light from a more distant object. This effect can magnify, distort, and even produce multiple images of the background object, depending on the alignment between the observer, the foreground mass, and the background light source. Gravitational lensing observations are particularly powerful for studying dark matter because dark matter does not emit, absorb, or reflect light, making it invisible to traditional telescopic observations. However, dark matter does exert gravitational forces, influencing the motion of stars within galaxies, the gas in galaxy clusters, and the path of light through the universe. By analyzing the light from distant galaxies and quasars that has been bent by intervening dark matter, astronomers can map the distribution and concentration of dark matter, even though it cannot be seen directly. There are two primary types of gravitational lensing: strong and weak. Strong lensing occurs when the foreground object is massive enough, and the alignment is such that it creates highly distorted or multiple images of the background object. Strong lensing can create striking phenomena such as Einstein rings, where a perfectly aligned lensing object produces a circular image of the light source. By studying these rings and multiple images, astronomers can directly map the mass distribution of the lensing object, revealing the presence and structure of dark matter. Weak lensing, though subtler, is more common and occurs when the distortion of background objects is slight. This form of lensing affects the shapes of numerous distant galaxies slightly, causing a coherent distortion pattern that can be detected statistically over large areas of the sky. By measuring the shape distortions of millions of galaxies, astronomers can create detailed maps of the dark matter distribution on large scales, revealing the cosmic web of dark matter that underlies the visible universe. Gravitational lensing has provided some of the most direct evidence for dark matter, confirming its existence and providing insights into its properties. For example, observations of colliding galaxy clusters, such as the Bullet cluster, have used gravitational lensing to separately map the distribution of dark matter and ordinary matter. These observations have shown that dark matter interacts only through gravity, bypassing other forces that affect normal matter, a key piece of evidence supporting the dark matter hypothesis. The discovery of Oumuamua in October 2017 marked a milestone in astronomy and our understanding of the cosmos. As the first confirmed interstellar object to pass through our solar system, Oumuamua's appearance challenged our preconceptions and opened up new avenues for research into the composition, dynamics, and origins of objects from beyond our solar system. Oumuamua, which means scout or messenger in Hawaiian, was detected by the Pan-STARRS 1 telescope in Hawaii as it made its closest approach to the Sun. Its highly elongated shape, unusual for asteroids or comets within our solar system, and its unexpected acceleration as it passed through the solar system, sparked intense interest and speculation among scientists. The significance of Oumuamua's discovery lies in several key areas. Interstellar visitors. Oumuamua confirmed that objects from other star systems can and do enter our solar system, providing direct evidence of material exchange between stars. This has implications for our understanding of planetary system formation and evolution, suggesting that the building blocks of planets, and potentially the precursors of life, could be exchanged between distant star systems. Composition and origins. Initial observations suggested Oumuamua was an asteroid, but its lack of a cometary tail as it approached the Sun puzzled astronomers. Later studies proposed it might be a new type of object, possibly a fragment from a disintegrated comet or even a piece of interstellar debris. Understanding Oumuamua's composition and origins could provide insights into the processes at work in other planetary systems and the diversity of objects formed in these distant environments. Oumuamua exhibited non-gravitational acceleration, changes in its speed and trajectory that couldn't be explained solely by the Sun's gravity. This led to various hypotheses, including outgassing, the release of gas from its surface, which is common in comets, but had not been directly observed in Oumuamua due to the lack of a visible coma or tail. This behavior has prompted discussions about the mechanisms that could cause such acceleration in interstellar objects. The discovery of 2I/Borisov in August 2019 by amateur astronomer Gennady Borisov marks another monumental step in our exploration of the cosmos. being the second interstellar object detected passing through our solar system and the first confirmed interstellar comet. Unlike Oumuamua, whose origins and classification sparked widespread debate among scientists, Borisov was readily identified as a comet due to its distinct cometary features, including a glowing coma and a tail, which are characteristic of comets as they approach the Sun and their icy bodies begin to sublimate. Borisov offered scientists a precious opportunity to study the material composition of an object from another planetary system. Observations revealed that Borisov's composition is remarkably similar to that of comets native to our solar system, suggesting that the processes forming comets may be universal. This insight is invaluable for understanding the building blocks of planetary systems and the distribution of water and organic molecules across the cosmos, elements that are essential for life as we know it. Borisov's trajectory confirmed its interstellar origin, entering our solar system with a hyperbolic orbit that indicated it was not gravitationally bound to the Sun. Its speed and path provided data on its approach and eventual exit from our solar system, contributing to our understanding of the dynamics of interstellar objects and the gravitational interactions within our solar system. Implications for planetary system formation. The discovery of Borisov, following closely after Oumuamua, suggests that interstellar objects passing through our solar system may be more common than previously thought. This reinforces the idea that the exchange of material between planetary systems in our galaxy could play a role in their evolution and possibly in the seeding of life-giving compounds across the galaxy. The observations of Borisov have underscored the need for continued vigilance and the development of technologies to detect and study interstellar visitors. With advancements in telescope technology and observation networks, astronomers hope to discover more interstellar objects, offering further insights into their origins, trajectories, and physical properties. Each new discovery allows us to piece together the larger puzzle of our universe's history and the processes that govern the formation and evolution of planetary systems. Hoag's object is a captivating and mysterious galaxy that stands out due to its unique and striking appearance. Classified as a ring galaxy, it features a nearly perfect circular ring of young, hot blue stars encircling a brighter, more compact yellow core of older stars. This rare configuration challenges our understanding of galactic structures and formation mechanisms, making Hoag's object a subject of intense study and fascination in astronomy. Discovered in 1950 by astronomer Arthur Hoag, who initially mistook it for a planetary nebula, further investigation revealed its true galactic nature. Located approximately 600 million light-years away, Hoag's object is one of the most well-defined examples of a ring galaxy, a type of galaxy that is relatively rare in the observable universe. The origin of Hoag's object's distinctive ring structure remains a topic of debate among astronomers. One leading theory suggests that it could have formed through a particular type of galactic collision and merger. In this scenario, a smaller galaxy might have passed through the center of a larger one, triggering a wave of star formation that eventually formed the ring. Alternatively, the ring could result from the galaxy's original disk, undergoing a unique form of instability that caused it to rearrange itself into the current ring-like pattern. What makes Hoag's object even more intriguing is the presence of a second, fainter ring detected outside the main ring, suggesting that this galaxy's history and formation are even more complex than previously thought. This outer ring contains faint, older stars and hints at possible periodic episodes of star formation or multiple galactic events that contributed to the galaxy's current structure. Zombie stars represent one of the cosmos's more peculiar and intriguing phenomena, challenging traditional understandings of stellar death and survival. In the celestial context, a zombie star refers to a stellar remnant that has survived a supernova explosion, an event typically considered the death throes of a star. This survival suggests a partial or failed supernova, wherein the star is not completely destroyed but instead leaves behind a core that continues to shine, a star that has come back from the dead, so to speak. The concept of zombie stars emerged from observations of certain supernovae that did not quite match the expected outcomes. One key example involves Type Ia supernovae, thermonuclear explosions of white dwarfs in binary systems. These events are crucial for measuring cosmic distances, and have led to the discovery of the accelerating expansion of the universe. However, some observed supernovae are fainter than the standard type Ia, suggesting that the white dwarf was not completely disrupted, but rather lost a significant portion of its mass in the explosion, leaving behind a smaller, damaged remnant. The existence of zombie stars has significant implications for our understanding of stellar evolution and the diversity of supernova mechanisms. For instance, it suggests that there is a range of outcomes for the final stages of stellar evolution, influenced by factors such as the star's mass, composition, and its interaction with companion stars in binary systems. This diversity challenges simple categorizations of stellar life cycles and highlights the complex physics governing supernovae. Studying zombie stars can provide insights into the conditions required for different types of supernova explosions and the processes that lead to partial stellar destruction. This research has implications for understanding nucleosynthesis, the creation of heavy elements in supernova explosions, as zombie stars may represent environments where these processes occur differently than in complete supernova. Furthermore, the study of zombie stars contributes to refining models of type Ia supernovae, which are pivotal for cosmology. Since these supernovae serve as standard candles for measuring cosmic distances, understanding any deviations from the norm, such as those caused by zombie stars, is crucial for the accuracy of measurements that underpin our knowledge of the universe's expansion. Kaisi 8462852, also known as Tabby's star, has captured the imagination of astronomers and the public alike due to its mysterious and dramatic fluctuations in brightness. Located about 1,470 light-years from Earth in the constellation Cygnus, this star has exhibited irregular dimming events that have puzzled scientists since its discovery. Unlike anything observed in other stars, these dimming events have led to a wide range of theories and speculations regarding their cause. Tabby's star was first noticed by citizen scientists as part of the Planet Hunters project, which uses data from the Kepler Space Telescope to search for exoplanets by detecting dips in starlight caused by planets passing in front of their host stars. However, the light pattern of KIC 8462852 was unusual. Its brightness dipped by up to 22%, and the events did not exhibit the regular patterns typically associated with planetary transits. Furthermore, the depth and irregularity of the dimming could not be easily explained by known natural phenomena. Several hypotheses have been proposed to explain the behavior of Tabby's star. One suggestion involves a swarm of comets or debris orbiting the star, which could occasionally block its light as seen from Earth. This could happen if, for example, a close pass of another star disturbed a comet belt, sending a large number of comets into orbits that take them in front of KIC 8462852. However, the amount of material required to cause such significant dimming makes this scenario unlikely. Another theory posits that the dimming is caused by dust clouds resulting from the collision and breakup of asteroids or planets in the star's vicinity, creating a cloud of debris that occasionally obscures the star's light. This scenario could account for the irregularity of the dimming events, but would also imply a rare and coincidental timing for the observation of such an event. A more speculative and controversial hypothesis involves the possibility of an alien megastructure, such as a Dyson sphere, constructed around the star to capture its energy for an advanced civilization. This idea, while intriguing, is considered highly unlikely by most scientists and is taken more as a testament to the mystery surrounding Tabby's star rather than a viable explanation. Hypervelocity stars, celestial sprinters of the galaxy, are stars moving at speeds so great they're able to escape the gravitational pull of the Milky Way. These stars traverse the galaxy at velocities exceeding hundreds of kilometers per second, far surpassing the speeds of typical stars in the Milky Way, including our Sun. The discovery and study of hypervelocity stars have provided astronomers with valuable insights into the dynamic processes at work in the galaxy and the powerful forces capable of propelling these stars to such extreme velocities. The existence of hypervelocity stars was first predicted theoretically, but the first such star was not observed until 2005. Since then, the advancement of observational technologies and methods has led to the identification of several more hypervelocity stars, each offering a unique perspective on the violent phenomena capable of accelerating stars to such high speeds. The predominant theory behind the origin of hypervelocity stars involves interactions with the supermassive black hole at the center of the Milky Way. According to this theory, a binary star system, two stars orbiting each other, wanders too close to the galaxy's central black hole. The intense gravitational forces exerted by the black hole can tear the binary apart, capturing one star while violently ejecting the other at a significant fraction of the speed of light. This slingshot effect propels the star out of the galaxy, sending it on a lonely journey through intergalactic space. Another scenario that could give rise to hypervelocity stars is the collision of multiple star systems, or the explosive supernova of a star in a binary system, where the resulting forces eject one of the stars at high velocity. While less common than interactions with the supermassive black hole, these events contribute to the diversity of hypervelocity stars observed. The study of hypervelocity stars has several important implications for astrophysics. Firstly, these stars serve as indirect probes of the environment near the galaxy's central supermassive black hole, offering insights into the dynamics and interactions in one of the most extreme environments in the universe. Additionally, the trajectories and velocities of hypervelocity stars can be used to map the gravitational potential of the Milky Way, contributing to our understanding of the galaxy's mass distribution, including its dark matter halo. Luminous red novae represent a rare and intriguing class of stellar explosions, distinguished by their distinctive red color, transient nature, and luminosity, which falls between that of classical novae and supernovae. These cosmic events have captured the interest of astronomers as they probe the complex processes of stellar evolution and interaction. LRNE are believed to result from the merger of two stars, a process that sets them apart from other types of stellar explosions. The scenario typically involves a binary star system where the stars are close enough that material from one star can be transferred to its companion, eventually leading to a merger. This merger process releases a significant amount of energy, leading to the luminous outburst characteristic of LRN, and ejects material into space, forming an expanding shell of gas and dust that gives the nova its red appearance. The study of LRNE offers valuable insights into the dynamics of binary star systems and the end stages of stellar evolution. The process leading to an LRN event may begin with a common envelope phase, where one star in a binary system expands into a red giant and engulfs its companion. The friction within the envelope causes the stars to spiral closer together, eventually leading to the merger. The energy released during the merger heats the ejected material, causing it to shine brightly and produce the observed red nova event. One of the most well-studied examples of a luminous red nova is V1309 Scorpii, which erupted in 2008. Prior observations of this system provided a rare and detailed pre-merger history, showing the orbital period of the binary system decreasing as the stars spiraled closer together. This event has become a key case study for understanding the nature and mechanics of LRN. LRNE contribute to our understanding of the diversity of transient astronomical events and the fate of binary star systems. They are also significant for understanding the synthesis of certain elements, as the conditions during the merger may allow for nucleosynthesis, contributing to the chemical enrichment of the interstellar medium. Magnetars are a fascinating and extreme subset of neutron stars, distinguished by their incredibly strong magnetic fields, among the most powerful known in the universe. Neutron stars themselves are the remnants of massive stars that have undergone supernova explosions, collapsing into incredibly dense objects roughly the size of a city, but containing more mass than the Sun. What sets magnetars apart is their magnetic field's intensity, which can be over 1,000 times stronger than that of a typical neutron star, reaching up to 1015 Gauss. Earth's magnetic field, for comparison, averages about 0.5 Gauss. The origin of magnetars' intense magnetic fields is still a subject of research, but it is believed that these fields are a result of the conservation of magnetic flux during the star's collapse. As the progenitor star collapses, its magnetic field lines are compressed into a smaller volume, dramatically increasing the field's strength. Magnetars are known for their violent and energetic behavior, emitting high-energy X-rays and gamma rays. They can produce giant flares and bursts of radiation so powerful that they can affect Earth's atmosphere and even temporarily alter its magnetic field, despite being thousands of light-years away. These emissions are thought to be caused by the instability and realignment of the magnetar's magnetic field, which can release a tremendous amount of energy. The discovery of magnetars has significantly contributed to our understanding of the universe's extreme conditions. Observing magnetars allows scientists to study the physics of matter under incredible densities and magnetic fields, testing the limits of physical theories. Magnetars have been linked to various astronomical phenomena, including some types of short gamma-ray bursts and anomalous X-ray pulsars, providing insights into the diverse outcomes of stellar evolution. Studying magnetars also has implications for the study of gravitational waves and the behavior of matter at nuclear densities. The extreme conditions around magnetars could reveal new physics about the state of matter in such extreme environments, potentially offering clues about the inner workings of atoms and subatomic particles under conditions unattainable in laboratories on Earth. Wolf-Rayet stars represent one of the later stages in the life of massive stars, showcasing some of the most dramatic and violent processes in stellar evolution. These stars are named after the French astronomers Charles Wolf and Georges Rayet, who first identified their unique spectral characteristics in 1867. Characterized by their incredibly strong stellar winds and the significant loss of their outer layers, Wolf-Rayet stars exhibit broad emission lines in their spectra, indicative of the presence of heavy elements such as carbon, nitrogen, and oxygen. The significance of Wolf-Rayet stars in the cosmos cannot be overstated. They are massive stars, typically more than 20 times the mass of the Sun, that have entered a phase of their life where they are losing mass at a remarkable rate, driven by the intense radiation pressure from within. This mass loss is a crucial aspect of their evolution, stripping away the outer hydrogen layers to expose the heavier elements in the core. This process enriches the interstellar medium with heavy elements, contributing to the galactic chemical evolution and providing the raw materials for future generations of stars and planetary systems. Wolf-Rayet stars are often found in regions of active star formation and can be considered precursors to supernovae, particularly type Ib and Ic supernovae, which lack hydrogen lines in their spectra. The end of a Wolf-Rayet star's life is marked by a spectacular explosion, leaving behind either a neutron star or a black hole. In some cases, the core collapse of a Wolf-Rayet star is thought to produce long-duration gamma-ray bursts, the most energetic events in the universe, observable across vast cosmic distances. Continuing our journey to these unusual phenomena, we encounter Fermi bubbles. Fermi bubbles are enormous, balloon-shaped structures filled with high-energy particles that emanate from the Milky Way's core, extending outward for about 25,000 light-years above and below the galactic center. Discovered in 2010 through observations by NASA's Fermi Gamma-Ray Space Telescope, these mysterious bubbles glow in gamma-ray light, the highest energy form of light. The discovery of the Fermi bubbles has provided astronomers with crucial insights into the processes occurring at the Milky Way's heart and the history of our galaxy's evolution. The exact origin of the Fermi bubbles is still a subject of research and debate among astronomers. One prevailing theory suggests that they were formed by past eruptions from the supermassive black hole Sagittarius A*, located at the center of the Milky Way. These eruptions could have occurred millions of years ago when the black hole ingested a large amount of gas and dust, releasing a tremendous amount of energy that propelled particles at high speeds into space, forming the bubbles. Another hypothesis posits that the bubbles could result from intense episodes of star formation near the galactic center. In this scenario, massive stars would have exploded as supernovae, injecting energy into the surrounding space and driving the creation of the bubbles. These stellar explosions could also accelerate particles to nearly the speed of light, contributing to the gamma-ray emission observed. The study of Fermi bubbles is crucial for several reasons. Firstly, They act as a record of the Milky Way's energetic past, offering clues about the events that have shaped our galaxy's evolution. Understanding the mechanisms behind their formation and the energy sources powering them can provide insights into the behavior of supermassive black holes and the role of galactic nuclei in shaping galaxies. Furthermore, the particles within the Fermi bubbles are believed to be a source of cosmic rays, high-energy particles that travel through space at nearly the speed of light. Studying these particles can shed light on the processes that accelerate particles to such high energies, contributing to our broader understanding of cosmic rays' origins and their impact on the galaxy. Additionally, the Fermi bubbles are an example of the types of large-scale structures that can exist in galaxies, offering a comparative tool for understanding similar phenomena in other galaxies. Observations of other galaxies have revealed bubble-like features, suggesting that the processes observed in the Milky Way may be common in the universe. Moving on from Fermi bubbles, we discover wormholes. Rooted in the equations of Albert Einstein's general theory of relativity, wormholes suggest the possibility of connecting two distant points in space and time, potentially enabling travel over cosmic distances in much shorter times than light would take to travel in normal space. Theoretical physicist John Archibald Wheeler coined the term wormhole in the 1950s, but the idea itself traces back to a solution of Einstein's equations proposed by Einstein and Nathan Rosen in 1935, hence the name Einstein-Rosen bridges. These bridges were initially thought to connect two different regions of space-time, possibly even creating a bridge between two different universes. The most common depiction of a wormhole is as a tunnel with two ends, each at separate points in space-time, much like a tunnel with ends in different cities. The interior of the wormhole might be a region of space-time that allows a traveler to move from one end to the other faster than a light beam traveling outside the wormhole, though not actually exceeding the speed of light within the wormhole itself. Despite their theoretical underpinning, no empirical evidence exists to suggest that wormholes exist or could be used for space travel. One significant challenge is the stability of wormholes. Theoretical models suggest that the throat of a wormhole would naturally collapse so quickly that nothing could pass through from one end to the other. To keep a wormhole open, exotic matter with negative energy density would be required, something that has not been conclusively observed. This matter would counteract the wormhole's tendency to collapse, but whether sufficient exotic matter can exist, and whether it can be manipulated for this purpose, remains speculative. Moreover, even if wormholes could exist and be stabilized, navigating them poses additional challenges. There would be no guarantee of where or when the other end of the wormhole would open, making it a potentially risky proposition for anything other than theoretical exploration. The concept of wormholes has profound implications for our understanding of the universe and the nature of space-time. It challenges the conventional notions of distance and connectivity in the cosmos, suggesting that the fabric of the universe might be far more intricate and interconnected than previously imagined. Wormholes also raise fascinating possibilities for time travel, as they could theoretically allow for movement not just across space but through time. As we near the end of our journey through the vast expanses of astronomy and cosmology, it becomes evident how these scientific discoveries profoundly influence our philosophical understanding of existence and our place in the universe. The more we learn about the cosmos, the more our perspective on life and our role within this immense universe evolves, challenging us to rethink our notions of significance, identity, and unity. Recent discoveries, from the observation of gravitational waves to the imaging of a black hole's event horizon, not only expand our knowledge of the physical universe, but also invite deep reflections on the nature of reality itself. Gravitational waves, for instance, have confirmed a century-old prediction of Einstein's theory of general relativity, opening new avenues for understanding the universe's most cataclysmic events. This milestone underscores our interconnectedness with the cosmos, as we can now hear the ripples in the fabric of space-time created by distant astrophysical phenomena. The first image of a black hole's event horizon, a feat once thought to be impossible, has further pushed the boundaries of our imagination and scientific capability. Such an achievement not only provides direct evidence of these enigmatic objects, but also serves as a humbling reminder of the universe's vast mysteries waiting to be uncovered. It exemplifies our relentless pursuit of knowledge and the power of collective human endeavor in unraveling the cosmos's secrets. The exploration of exoplanets and the search for extraterrestrial life have significantly impacted our philosophical perspectives on existence. Discovering worlds orbiting distant stars in habitable zones where life as we know it could exist challenges our sense of uniqueness and prompts us to ponder the possibilities of life beyond Earth. This search broadens our understanding of life's potential diversity and resilience, emphasizing that we may just be one expression of life in a universe teeming with possibilities. The concept of the multiverse, suggested by certain cosmological theories, proposes that our universe might be just one of many, each with its own laws of physics. While still highly speculative, this idea has profound implications for our philosophical outlook, questioning the very nature of reality and our place within it. It challenges the notion of a singular universe and invites us to consider a much larger and even more diverse cosmic landscape than previously imagined. What fascinating mysteries do you believe exist in the universe? From the enigmatic dark matter and dark energy that seem to govern the cosmic structure and expansion, to the tantalizing prospect of parallel universes and the mysteries of black holes, where the known laws of physics converge and diverge in unpredictable ways, our quest for understanding is far from over. Each discovery peels back a layer, revealing not just answers, but a multitude of new questions, each more intriguing than the...
When you look at the night sky, you can see thousands of stars using nothing but your eyes, far from the lights of cities. In fact, there are many more stars in the sky which are too faint for us to see. Every single star that you can see is a part of our Milky Way galaxy, our heavenly home that has captured people's attention for ages. The shimmering band of stars, dust, gas, and dark matter that makes up the night sky captures our attention. These elements are all held together by gravity. As we navigate through the cosmos, an intriguing enigma emerges. What is the Milky Way truly like? What makes it up? And where does our solar system exist in the Milky Way? Astronomers have been baffled by these fundamental questions for many centuries, and finding answers was no easy task. But beyond its luminous beauty lies a tapestry of mysteries waiting to be unraveled. Join us today as we embark on an amazing adventure around the Milky Way, uncovering its mysteries, wonders, and majesty. You're probably somewhat familiar with our solar system. If nothing else, you probably already know that it contains 8 planets, in addition to the Earth, the Sun, moons, and several other celestial bodies like asteroids and Pluto. However, there is a lot more beyond the solar system of which you may not be aware. From Earth, we can see roughly 6,000 stars without the use of a telescope. Even while that seems like a large number of stars, it represents a very small portion of the total. In fact, for every star you can see, there are more than 20 million you cannot see. The majority of stars are either too dim, too far, or obstructed by clouds of cosmic dust. While the Milky Way galaxy contains all of these stars, there are other, larger galaxies as well, including the Andromeda galaxy. Every galaxy is a system made up of various stellar remnants, interstellar medium, and star systems. Astronomers believe there are 100 billion galaxies in the cosmos, yet they are not sure. Intergalactic space, which contains a thin gas, lies in between the galaxies. Given the size of our solar system, and the fact that it is only one of many in our galaxy, it is understandable why the universe is thought to be infinite. This truly helps to put into perspective how tiny both Earth and humans are in the big picture. Through the use of radio and X-ray telescopes, scientists have been able to gather information during the past century about the composition of the interstellar medium. They have shown that it is made up of extremely diffuse ionized hydrogen atoms, dust, and cosmic rays scattered throughout thick gas clouds that are thought to be the birthplace of new stars. But because of the Sun, all 8 planets, and a far-off disk of debris known as the Kuiper Belt, its precise nature just outside our solar system has remained mostly unknown. The Kuiper Belt is located between 30 and 50 astronomical units from the Sun. 1 astronomical unit is equivalent to the distance between Earth and the Sun. The heliosphere, a massive protective bubble created by the solar wind, surrounds them all. This bubble buffets against the interstellar medium like an invisible shield, keeping out most dangerous cosmic rays and other material as the Sun and its surrounding planets hurtle across the galaxy. Without the heliosphere, life would certainly have evolved differently, and maybe not at all. The area where the Sun's magnetic bubble ends and weakens is known as the interstellar space border. The heliosphere, a magnetic bubble, is full of plasma or ionized gas. The solar wind, which pulls magnetic field lines away from the Sun, blows material into the heliosphere. With its own magnetic fields and charged particles, the plasma in the interstellar medium exerts an inward push on the heliosphere's edge, creating a complex and dynamic structure there. When the solar wind encounters interstellar space, it begins to weaken and slows to approximately 62 miles per hour. It was previously traveling between 370 and 430 miles per hour. The termination shock is the point at which this happens. The heliosheath is the area in the heliosphere where the solar wind continues to slow down after the termination shock, while the heliopause is the outermost point of the heliosphere. The solar wind stops and gives way to interstellar space at the heliopause, which is located around 11 billion miles or 18 billion kilometers from the Sun.
5, 4, 3, 2, 1. MDS, we have ignition, we have a liftoff.
Since the beginning of human space exploration, only 2 probes have made it to interstellar space, or the area outside of the solar system. After launch in 1977, Voyager 1, the first spacecraft, took more than 30 years to reach the heliopause, a limit that scientists believe marks the beginning of interstellar space. It was an amazing accomplishment, sending back vital information via a medium unaffected by the Sun. As we exit the solar system, we will reach Alpha Centauri. The triple star system, which is the closest star system to Earth, located at about 4.37 light-years away in the constellation Centaurus. It is a triple star system consisting of 3 stars, Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. Alpha Centauri AB is a binary star system made up of Alpha Centauri A and B, which are sun-like stars, classified as Class G and K, respectively. These 2 main stars have an apparent magnitude of -0.27, making them appear to be a single star to the unaided eye. Only Sirius and Canopus are brighter than it, making it the brightest star in the constellation and the 3rd brightest in the night sky. Alpha Centauri B is smaller and colder than Alpha Centauri A, with 0.9 solar mass and less than 0.5 solar luminosity. while Alpha Centauri A has 1.5 times the luminosity and 1.1 times the mass of the Sun. The two have a 79-year orbital period around a shared center. The distance between A and B fluctuates from 35.6 astronomical units, or roughly the distance between Pluto and the Sun, to 11.2 AU, or roughly the distance between Saturn and the Sun, due to the eccentricity of their elliptical orbit. In the Alpha Centauri system, Proxima Centauri is the star nearest to the Sun, located approximately 4.2 light-years from Earth. Robert Innes, a Scottish astronomer, made the discovery of the star in 1915. Proxima Centauri is a red dwarf star, which is the most common kind of star. It is roughly 7 times smaller than the Sun, and a little more than half as hot at 3,100 kelvins. On the other hand, our Sun is 5,772 kelvins. As a matter of fact, this little star is just 50% larger than Jupiter. Red dwarf stars have long lives because they consume hydrogen fuel very efficiently. Proxima Centauri is expected to remain in its current state for more than 4 trillion years. Although the Alpha Centauri system can be seen in the constellation Centaurus, Proxima Centauri is usually not visible to the human eye. Proxima Centauri orbits the other 2 stars in the system, Alpha Centauri A and B. Proxima Centauri takes 550,000 years to complete an orbit of A and B. With an apparent visual magnitude of 11, Proxima Centauri is the dimmest of the 3 stars. This star emits light at a slower rate than the Sun, with a luminosity of 0.17%, that of the Sun. However, Proxima Centauri is categorized as a flare star, which is prone to massive solar flares, because its brightness can vary by more than 1 magnitude in a matter of minutes. These flares, which occur multiple times a day, have the potential to be powerful enough to make Proxima Centauri visible to the human eye. The greatest solar flare ever observed in the Milky Way galaxy was released by Proxima Centauri in 2019, glowing 14,000 times brighter in ultraviolet wavelengths than normal. Even though Proxima Centauri will live longer than the Sun, it will eventually meet the same fate. Proxima Centauri will end up as a burning white dwarf star, because it does not have the mass to turn into a neutron star or a black hole when its hydrogen supply runs out. As of 2022, astronomers have detected 3 planets orbiting Proxima Centauri: Proxima Centauri B, C, and D. These are the closest planets outside the solar system. Red dwarf stars are small and cool. Thus, planets can circle quite close to them and still be classified as being in the habitable zone. This is the range of distance from a star where a planet's water, if any, could be liquid and potentially support life. Proxima Centauri B was discovered in 2016 and estimated the planet to contain about 17% more mass than Earth, and thus likely to be a rocky planet as well. Proxima Centauri B is still within Proxima Centauri's habitable zone, despite being far closer to its star than Earth is to the Sun. It orbits Proxima Centauri every 11 Earth days at a distance of about 0.049 AU, over 20 times closer to Proxima Centauri than Earth is to the Sun. Proxima Centauri B is most likely tidally locked like our Moon, with one side always facing Earth, given that it is far closer to its star than Earth. It is therefore possible that liquid water exists on the opposite side, but its habitability is unknown due to the extreme radiation and flares from its host star. Proxima Centauri B feel the gravitational pull of their stars, much more strongly than we feel the tidal effect of our sun. Here on Earth, the moon exerts more tidal force than the sun, also because it's so much closer. And tides don't just pull on the ocean, they can also move air. It's possible that the tidal pull on the atmosphere of Proxima Centauri b is up to 500 times stronger than that of Earth's atmosphere. It's likely that Proxima Centauri b is getting close to the maximum tidal force that a planet can withstand and still retain a solid surface. However, Proxima Centauri b's climate and weather are mostly unaffected by its extremely high tides. Situated just outside of the habitable zone at around 1.5 astronomical units from the red dwarf is the mini-Neptune exoplanet Proxima Centauri c, which is around 7 times the size of Earth, and orbits its star once every 1,900 Earth days. First thought to have been discovered in 2019, the super-Earth planet, it appears to shine much brighter than expected for that size, indicating that it may be shrouded in dust clouds or circled by a ring system. The projected planet's estimated temperature by astronomers is extremely cold, probably close to minus 233 degrees Celsius. This makes it uninhabitable due to its distance from its star and large mass. The gravitational pull of Proxima Centauri c caused its parent star's velocity to wobble, which led to the star's initial detection in 2019. In 2020, pictures from the Hubble Space Telescope from 1995 were used to confirm Proxima Centauri c existence. It is therefore one of the rare exoplanets with visual confirmation. A third planet was discovered in 2022 around Proxima Centauri. The exoplanet, known as Proxima Centauri d, orbits its star at a distance of roughly 3% of Earth's distance from the Sun and contains about 25% of Earth's mass. Every 5 Earth days, Proxima Centauri d completes one orbit around its star due to its relative proximity to it. It is among the lightest exoplanets that scientists have yet observed. Furthermore, in 2021, scientists detected what may be the first indications of an exoplanet circling Alpha Centauri A, also known as Rigil Kentaurus, in the star's habitable zone called Candidate C1. It is estimated that C1 has a mass between half of Saturn and Neptune and orbits Alpha Centauri A at a distance of roughly 1.1 AU. Using direct thermal imaging, C1 was found. With an elongation of around 0.1 arcsecond, it looks to be as bright as a giant planet. This is consistent with the orbital motion of a planet in a 70-degree orbit. The fact that C1 is situated in the habitable zone of Alpha Centauri A and may be a mini-Neptune or super-Earth makes the discovery of this exoplanet much more interesting. We are almost certain that planets similar to Earth exist in Alpha Centauri. But the main question is, could humans ever actually live there? The most challenging obstacle in our quest to set up a new home in the Alpha Centauri system would undoubtedly be traveling a huge distance to reach these 3 stars. Even though Alpha Centauri is the nearest star system to Earth, it is still more than 4 light-years away. That comes to roughly 23.5 trillion miles or 37.8 trillion kilometers. We would need a far faster spacecraft or another means of transportation to cover such a great distance. NASA claims that the Space Shuttle Discovery, which was discontinued in 2011, had a top speed of about 17,500 miles per hour. Still, reaching Alpha Centauri would take more than 148,000 years, even at this steady speed. NASA estimates that even when the Orion spacecraft, the crew capsule linked to the Artemis program, is prepared to carry people. Its maximum velocity will be approximately 20,000 miles per hour. This won't significantly cut down this travel time to Proxima Centauri. That's even if either of these vehicles was designed to journey out of the solar system rather than just making relatively short trips to the Moon or Mars. As we have already discussed, the only spacecraft to make it out of the solar system thus far are Voyager 1 and 2. Even at their top speed of over 35,000 miles per hour, it will take them nearly 40,000 years to travel 2 light years to reach the indistinct boundary between Proxima Centauri and our solar system. That implies that it might take these spacecraft more than 80,000 years to reach close to the star. After all, it takes light more than 4 years to reach Alpha Centauri. A spacecraft needs to be extremely tiny and robotic in order to reach a distant star in a reasonable amount of time, like within a generation. Furthermore, it still needs an incredibly strong energy boost to get up to speed. And that is the basic concept behind the Breakthrough Starshot project. By creating a light sail-equipped nanocraft called Starship that would be sent into Earth orbit. The mothership would release the tiny probes one at a time, which would then ride the beams of a colossal ground-based laser array. The main challenge, though, is the Earth's atmosphere, which distorts laser and incoming light and makes it challenging to apply the force required to move a spacecraft forward. Much more potent lasers on the ground would be able to keep a close focus on the space mission thanks to small lasers mounted on satellites that would evaluate atmospheric impacts in real time. To send out the vessel at any given time, the required lasers need an astounding 100 gigawatts of power, which is equal to the total US electricity usage. But the lasers only need to operate for 10 minutes at full power. They plan to employ 100 million lasers to distribute the electricity across an area of 1 kilometer square. The Starshot team is determined to push the boundaries of space exploration. When the lasers are switched off, the object racing through space will be traveling at a stunning 20% of the speed of light, more than 130 million miles per hour, or 216 million kilometers per hour, with a diameter of little over 10 meters. This spacecraft could reach to Alpha Centauri in about 22 years. But it might be significantly slowed down by the sun's gravitational pull and interstellar debris. It will take 4 more years for the spacecraft's signals to reach Earth, even if they make it to Alpha Centauri. Alpha Centauri is moving toward Earth, but very slowly, and doesn't pose an immediate cause for concern. The distance between Alpha Centauri and Earth as of 2024 is approximately 3.26 light years. It will be at its closest in 29,700 AD, when it will be approximately 3 light years away. Over the course of a human lifetime, the slow change in distance will have no noticeable impact on Earth or the solar system. Space is a remarkable place. We're learning new things about it every day. Leaving Alpha Centauri behind, we travel on to the Barnard Star, the second nearest star to the Sun, at a distance of 5.95 light years. It has the name Edward Emerson Barnard, in honor of the American astronomer who made the discovery in 1916. With an estimated age of 11 to 12 billion years, or roughly twice that of the Sun, Barnard's star is an old star, and most likely a thick disk member of the Milky Way. Red dwarfs that are young or middle-aged often spin fast enough to produce powerful magnetic fields, which can result in flares that quickly double a star's brightness. but Barnard's star was too old to show this kind of behavior. However, on July 17, 1998, Diane Paulson and her colleagues at NASA's Goddard Space Flight Center revealed that a flare similar to this one had been released by Barnard's star. At the time, the star's spectra was being obtained using the 2.7-meter telescope at McDonald Observatory by William Cochran of the University of Texas at Austin. His hope had been to find alterations that would point to the existence of planets in orbit. Rather, he saw emission lines in the spectrum, which showed that the star might be flaring. 4 years later, Cochrane team's investigation revealed that the star's hot blue flare was similar to those from younger red dwarfs, even though it was quite old. The temperature of the flare was at least 8,000 Kelvin, which was more than twice as hot as the 3,100 Kelvin temperature of the star. As Barnard's star gets closer to us, its distance from us is decreasing by 0.036 light-years every century, at an incredibly fast speed of 108 kilometers per second or 67 miles per second. Its closest approach to the Sun will be at a distance of just 3.85 light-years by 11,800 AD. In terms of its proper motion, Barnard's star is also the fastest-moving star in Earth's skies. Another feature that makes Barnard's star unique is the largest proper motion of any star, which is approximately 10.4 arcseconds per year, or the equivalent of a lunar diameter every 180 years. Since of this and its relative closeness, it is an ideal target for exoplanet searches, since any systematic variations in its motion across the sky brought on by planets in orbit would be more noticeable. Finally, a planet was found around Barnard's star in 2018. The planet orbits the star at a distance of roughly 60 million kilometers or 37 million miles on a 233-day orbit, with a mass at least 3.2 times that of Earth. The planet is not in the habitable zone due to the star's low brightness, and any water on its surface would probably be frozen. As we go farther away, around 8.6 light-years away, near the constellation of Orion, we will find Sirius, also known as the Dog Star, or Sirius A, which is the brightest star in Earth's night sky. With a mass twice that of the Sun, Sirius has a diameter of 1.5 million miles or 2.4 million kilometers. The star Sirius would outshine our Sun by a factor of more than 20 if it were positioned next to it. Within the Canis Major constellation, Sirius is a binary star. The star's name comes from the Greek word Sirios, which means glowing or scorching. With a surface temperature of almost 18,000 degrees Fahrenheit, Sirius has a bluish tint and is 25 times brighter than the Sun. It is clearly visible in the winter night sky of the northern hemisphere. The ancients were familiar with Sirius due of its extreme brightness. Nevertheless, astronomers were taken aback when Sirius B, a companion star, was discovered in 1862. The star is visible to the naked eye. On the other hand, Sirius B is 10,000 times fainter than Sirius. Thanks to data from the Hubble Space Telescope, astronomers were finally able to estimate the mass of this faint object in 2005, despite the fact that it is extremely difficult to observe from Earth. Within 20 light-years of the Sun are around 131 objects, including stars, brown dwarfs, and sub-brown dwarfs. Only 22 stars are bright enough to be seen without a telescope, meaning their visible light must be at least 6.5 apparent magnitude, the lowest brightness that can be seen with the naked eye from Earth. The known 131 objects abound in 94 stellar systems. Out of these, 103 are main sequence stars, consisting of 23 typical stars with a higher mass and 80 red dwarfs. In addition, scientists have discovered 21 brown dwarfs, one sub-brown dwarf, Y08550714, which is possibly a rogue planet, and 6 white dwarfs. White dwarf are stars that have used up all of their fusible hydrogen. A red dwarf candidate, known as Schultz's star, and a companion brown dwarf, passed near the edge of the Oort cloud around 70,000 years ago. At this moment, it is approximately 22 light-years away from the Sun, and has likely triggered a comet storm that will take over 1 million years to reach the inner solar system. The Kuiper Belt object's orbits were impacted by its passage. Some other stars, such as the G-type star HD 7977, have also been researched. It had its close pass around 2.8 million years ago, and it is currently located about 247 light-years from Earth. Of course, past interactions aren't the only thing to consider about. There will be more stars in the future. In the next 15 million years, 694 stars are predicted to approach the solar system at a distance of less than 516 light-years, based on data from the Gaia telescope's second data release. 26 of them are likely to arrive within 3.3 light-years, and 7 more within 6 light-years. Due to the sheer number of stars that must be surveyed, this number is probably much higher. For example, a star that was approaching the solar system 10 million years ago would be 600 to 6,000 light-years away from the Sun today, whereas millions of stars are now closer to the Sun. Gliese 710, a star, is among the most well-known instances of a close future passage. It is an orange star, around 60% the size of the Sun, located in the Serpens constellation. This star is heading in our direction at a speed of 51,499 kilometers per hour, or almost 32,000 miles per hour. In 1.29 million years, it will pass the Sun at a distance of around 10,520 AU. It's over 100 times the distance to Pluto, which orbits the Sun at an average of 39.5 AU. But it still has the potential to disrupt the solar system. If humans are still around on Earth at that point, we don't have to worry about any disruptions to our orbit. If Gliese 710 has any effect at all, it might only have it on the outer solar system. It shouldn't have any impact on anything inside 40 astronomical units. But still, it could possibly cause disruptions to the Oort cloud because it has a very high probability of going through it. For millions of years, comet showers would result from that, heading toward the Sun. This might lead to roughly 10 comets visible to the unaided eye every year. Searches for stars that are close to the Sun could not only be an opportunity of finding ancient comets, but also of predicting an intriguing future for observers on Earth millions or even thousands of years from now. The local interstellar cloud, which is around 30 light-years large, is where the solar system and the other stars and dwarfs are now moving within or close to it. The local interstellar cloud is, in turn, contained inside the local bubble, a cavity in the interstellar medium about 1,000 light-years across, and has an odd peanut shape. Our Sun was far away when the bubble first formed 14 million years ago, but about 5 million years ago, the Sun's path made its way into the bubble. Interestingly, star formed on the surface of the bubble, but not inside it. There are 7 star-forming regions around this bubble. Because of this local bubble, life has become possible on Earth today. As we go farther away, we will reach Orion constellation, around 1344 light-years away from Earth. 1 light-year is the distance light travels in a single year, about 6 trillion miles or 10 trillion kilometers. The Orion constellation is one of the 88 modern constellations and is named after the hunter in Greek mythology. It contains over 60 stars, including Betelgeuse, a red supergiant star located at around 650 light-years away. This is one of the largest known stars, with a diameter of about 767 million miles or 1.2 billion kilometers. It's about 700 times the size of the Sun and has a mass between 10 and 20 times that of the Sun. Because Betelgeuse may have less than 300 years of fuel left in its core, there has been continuous discussion throughout the world on whether or not it would explode. The star's core will collapse into a black hole as it burns through those final drops, blasting out the star's outer layers at speeds of up to 25,000 miles per second or 40,000 kilometers per second. Astronomers refer to this blazing demise as a supernova explosion, and in Betelgeuse's case, it will be a breathtaking sight for observers on Earth. Those layers of gas and dust will shine in our sky for several weeks, comparable in brightness to the full moon, because the star is only 650 light-years away from Earth. The issue is that most astronomers do not think Betelgeuse is quite ready for a big explosion just yet. Astronomers normally expect that it will blow up in the next 100,000 years, or soon on a cosmic time frame, not a human one. The other famous stars in this constellation is in the line Orion's belt, which consists 3 stars located around the middle of the constellation Orion. These are Alnitak, Alnilam, and Mintaka, from east to west. The belt is perhaps the most recognizable feature of Orion because it is visible all around the world. These 3 supergiant stars separately are thousands or tens of thousands of times brighter and several times more massive than the Sun. Despite these stars look closer to one another in the sky, they are actually light-years apart. Orion's belt is mainly used by astronomers as a celestial landmark when searching for M42, also known as the Orion Nebula. M42 is located below the belt and is one of the most visible Messier objects for beginner astronomers, as it is easy to locate and view with a telescope or pair of binoculars. Looking at it is like looking into a celestial nursery where new stars are born. One of the largest gas and dust clouds in our Milky Way galaxy is the Orion Nebula. It is approximately 2 million years old and located about 1,300 light-years away from Earth. Because the magnificent nebula has an apparent brightness of +4, it is even visible with the human eye. On the astronomical magnitude scale, +6 is the faintest object that, in the best lighting conditions, is visible to the human eye. This massive nebula, which has a diameter of between 30 and 40 light-years, could be giving birth to 1,000 stars. Within the nebula is a young open star cluster, whose stars are still only loosely connected by gravity after having formed together in the gas cloud. It is sometimes called the Orion Nebula Star Cluster. An international group of astronomers suggested in 2012 that this cluster in the Orion Nebula might have a black hole at its heart. Through small telescopes, you can see the 4 brightest stars in the Orion Nebula, known as the trapezium. The Orion Nebula is illuminated by the light of the young, hot trapezium stars. In terms of star lives, these stars are young, having only the age of approximately 1 million years. An infrared picture of the Orion Nebula was taken by the James Webb Space Telescope last year. It shows an explosion of dust, stars and clouds in red, purple and blue against a background of dark space. Additionally, 540 planetary mass objects with masses ranging from 0.6 Jupiter masses to Jupiter itself have been discovered by James Webb within the nebula. Among these planetary mass objects, the most fascinating are the Jupiter mass binary objects, which aren't separate objects orbiting in space by themselves. Our Milky Way galaxy is a spiral galaxy. A spiral galaxy is a galaxy that looks like a flat, rotating disk with a bulge in the center and spiral arms that extend outward from the bulge. While there are many minor arms and just 2 major arms in our spiral galaxy, astronomers used to believe that there were 4 major arms. Scientists have found that just 2 arms, wrapping off the ends of a central bar of stars, dominate the Milky Way's beautiful spiral structure. These discoveries were made possible by NASA's Spitzer Space Telescope using infrared imagery. The 2 major arms of the galaxy, Scutum Centaurus and Perseus, are visible at the tips of a thick central bar, while Norma and Sagittarius, the 2 now demoted minor arms, are situated in between the major arms and are less distinct. Although the minor arms are mainly made up of gas and areas where stars are forming, the major arms have the largest densities of both young and old stars. Large telescopes are used by radio astronomers to study the motions of those hydrogen clouds that trace the arms. With a pitch angle of around 9 degrees, the Perseus arm has a spiral extension and measures over 60,000 light-years in length and 1,000 light-years in width, and has the well-known Crab Nebula in addition to double clusters. On the other hand, the Scutum Centaurus arm is around 55,000 light-years in length and 1,000 light-years in width. Our solar system lies between 2 prominent spiral arms, the Perseus arm and the Scutum Centaurus arm. However, we are not completely free floating in empty space. We are situated on the edge of the Orion Cygnus arm, sometimes referred to as the Orion arm or local arm, which is a small spiral arm. This spiral arm spans about 10,000 light-years in length and 3,500 light-years in diameter. However, a 2016 analysis indicates that its length may exceed 20,000 light-years. The Orion arm is named after the Orion constellation. The solar system is located in the local bubble on the inner edge inside the Orion arm. It is located at 26,000 light-years from the galactic center, halfway down the length of the Orion arm. You might be surprised to hear that the Sun takes 250 million years to complete 1 rotation around the Milky Way. This is referred to as a cosmic year or galactic year. Thus, during its lifetime, the Sun is estimated to have completed only 18 to 20 orbits since the beginning of mankind. The solar system orbits the Milky Way at a speed of about 220 km per second, or 0.073% the speed of light. The solar system takes around 1,400 years to travel 1 light-year at this speed, or 8 days to travel 1 astronomical unit. Following the ecliptic, the solar system is traveling toward the zodiacal constellation Scorpius. The last time the solar system was in this position in the Milky Way, there were still dinosaurs on Earth. Who knows when it will happen again? Humanity might be extinct, or it might have evolved into something else entirely. Our place in the galaxy is important because it seems that galaxies have habitable zones, just like planetary systems. because many of the Milky Way's suns orbit the galaxy along paths that take them through the deadly spiral arms. An astounding 95% of them may not be able to support habitable planets. Radiation from the crowded stars is deadly for any star that goes through one of these stellar swarms. In order to maintain its alignment with the galaxy's rotation, our solar system orbits sufficiently far from the galactic center to stay in the calmer region between the spiral arms. Within a large and intricate galaxy, the Earth and its planetary siblings are well situated in a quiet, resource-rich region. As we go closer to the center of our Milky Way galaxy, located roughly 9,500 light-years away from Earth in the Scutum constellation, we will reach UY Scuti. It's considered to be one of the largest known stars, with a radius of 1.18 billion kilometers, which is 1,700 times larger than the Sun's radius. This would give the star a diameter of over 8 astronomical units. That is equivalent to 8 times the distance between Earth and the Sun, or 150 million kilometers, or 93 million miles. Because of this hypergiant star's immense size, its outer surface would reach well beyond Jupiter's orbit, which is around 5 times further from the Sun than Earth. The gas nebula that is ejected from the star stretches 400 times the distance between Earth and the Sun, far beyond Pluto's orbit. Or look at it this way. More than 1 million Earths could fit inside the Sun, but some 5 billion suns could fit inside a sphere the size of UY Scuti. Not surprisingly, UY Scuti is classified as a hypergiant star, which is the classification which comes after supergiant and regular giant. Although it may be the largest due to its size, but it is not the heaviest or most massive star. The term mass in massive refers to the amount of matter in the star. The heaviest star is R136A1, which weighs in at about 300 times the mass of the Sun, but only about 40 times the radius of the Sun. On the other hand, UY Scuti has a size significantly larger than the Sun, although having only have a mass between 7 and 10 times that of the Sun. Similarly, being so massive doesn't mean that UY Scuti is that hot either. In fact, its surface is almost half as hot as our Sun's. Another thing that makes UY Scuti particularly interesting is the fact that it's a variable star. Over time, variations in luminosity can be seen as a result of the material's continuous fluctuation at and near the surface, due to the unstable battle between the forces of gravity and fusion. These stars are of special interest to astronomers because they can shed light on the inner workings of stars. Although UY Scuti, like many other stars, is thought to be capable of supporting a planetary system, it's possible that the innermost exoplanets have already been swallowed by the host star's expansion. Furthermore, UY Scuti is so faint that it is improbable that we will ever be able to witness those exoplanets directly. As we go to the center of our Milky Way galaxy, around 26,000 light-years away, we see a celestial enigma. Sagittarius A. This supermassive black hole is an incredible cosmic monster that is beyond understanding. Sagittarius A is no ordinary black hole. Its estimated mass is a staggering 4.3 million times that of our Sun. Imagine compressing millions of suns into a single point, a gravitational singularity where space and time warp beyond recognition. This massive monster is located at the heart of the Milky Way, our spiral galaxy. A black hole is a region of space so densely populated with mass that nothing can escape from it, not even light. A black hole is invisible to us, but telescopes can see the materials surrounding it. Black holes surrounding matter, which can consist of gas and dust, warms up and releases detectable radiation. In some cases, telescopes can observe the gravitational influence of a black hole on the motions of nearby individual stars. Observing it directly is a formidable challenge. Sagittarius A is obscured by a dense layer of dust that prevents optical observations. However, astronomers have developed smart strategies to break through this cosmic curtain. The Event Horizon Telescope, a network of radio telescopes spanning a planet, made history in April 2019, when it successfully obtained the second-ever image of a black hole. This discovery comes after the EHT collaboration released the first picture of M87, the black hole, at the center of the farther-off Messier 87 galaxy in 2019. Sagittarius A was visible in the photograph as a dim outline against the brilliant background. This turbulent region, known as the accretion disk, feeds matter to the hungry black hole, causing occasional X-ray flashes. Despite Sagittarius A being less massive and more than 1,000 times smaller than M87, the two black holes look remarkably similar. Its surrounding gas disk, which stretches out over a distance of 5 to 30 light-years, can reach temperatures of up to 18 million degrees Fahrenheit or 10 million degrees Celsius. Not only is the supermassive black hole at the center of our galaxy spinning, but it's doing so at nearly maximum speed, consuming everything in its path. Physicists used NASA's Chandra X-ray Observatory to study the X-rays and radio waves coming from material outflows in order to measure the rotating speed of the supermassive black hole in the Milky Way. A black hole's spin speed is represented by the letter A and ranges from 0 to 1, where 1 is the maximum rotational speed to a specific black hole and represents a significant portion of the speed of light. Physicists discovered that Sagittarius A rotates at a speed of 0.84 to 0.96, which is near the upper limit determined by the width of a black hole. The spin of a black hole differs from that of other celestial bodies. Black holes are truly regions of space-time, defined by an outer non-physical boundary termed the event horizon, beyond which no light can escape, unlike planets, stars, and asteroids, which are solid things with physical surfaces. This implies that as black holes spin, they literally distort space-time itself, dragging anything inside the ergosphere with them. This phenomena, known as frame dragging or the lensing-Thirring effect, which implies that knowledge of a black hole's spin is necessary to comprehend how space acts around it. Additionally, the frame dragging around black holes produces strange visual effects. The path of light gets twisted or curved as it approaches a revolving black hole due to spacetime's rotation. This causes a process known as gravitational lensing, in which the rotating black hole's gravitational pull bends the path of light. Frame dragging effects can result in the production of light rings and even the shadow of a black hole. These are examples of how light is affected by black holes' gravitational pull. The theoretical top speed of a black hole is determined by how it feeds on matter and thus how it grows. As matter falls into a black hole, it increases the black hole's spin. But there's a limit to how much angular momentum it can possess. The black hole's mass is another factor. The gravitational attraction of more massive black holes is stronger, making it harder to spin them up. This could explain why the rapidly feeding supermassive black hole at the center of galaxy M87, the first black hole ever captured on camera, is spinning at between 0.89 and 0.91, despite having the mass of 6.5 billion suns. While Sagittarius A, with its mass equivalent to about 4.5 million suns, has a spin speed between 0.84 and 0.96. But soon, something strange happened while researching this black hole. Some scientists believe that Sagittarius A may not be a black hole after all. Instead, it could be an immense concentration of dark matter. Imagine a dark pool of invisible matter forming the basic structure of our galaxy. Sagittarius A has never been directly confirmed, despite the fact that it is widely believed to be a black hole. To put it simply, it is an extremely bright radio emitter located at the Milky Way's galactic core. The astronomy community encountered a challenging problem. G2, a galaxy cloud, had moved a bit too close to Sagittarius A. The G2 gas cloud just kept drifting without undergoing any notable changes, despite the fact the supermassive black hole should have pulled it and destroyed it. Observing the interaction between the Sagittarius A and the G2 gas cloud revealed that G2 was not an ordinary gas cloud as seen by the lack of effect. They explain that at least two components had to be present to allow the cloud to pass through that close to the black hole without being devoured. One is an extended, cold and low-mass gas cloud, and the other is a very compact segment, like a dusty object that dominated the detected emission from G2 as it passed by. Astronomers, however, may be more concerned with the possibility that Sagittarius A is not actually a black hole. First, scientists created a simulation of our galaxy because they were intrigued by the idea that the Milky Way's center might actually be a mass of dark matter. Researchers found that despite the galactic center's replacement, the Milky Way galaxy still exists and operates basically in the same manner throughout the simulations. The behavior of the rotating curve in the Milky Way's outer halo was identical to that of nearby S-stars, or those connected to the radio source Sagittarius A. Taking their inquiries a step further, they proposed that darkinos, a family of particles related to fermions, may comprise the mass at the center of the Milky Way. Apart from its extreme features, such as devouring everything around it, darkinos would have the same properties as a black hole if they clumped together into a huge mass. Sagittarius A is mostly dormant and only occasionally absorbs gas or dust, but nonetheless has an estimated mass millions times that of our Sun. Although there are still a lot of unanswered questions concerning the supermassive black hole, future observations from the Event Horizon Telescope should shed light on these riddles. Stellar mass and intermediate mass black holes form when massive stars cease nuclear fusion and can no longer support themselves against complete gravitational collapse. The mechanism that forms supermassive black holes like Sagittarius A is unclear because there are no stars large enough to directly collapse into a black hole of this size. There are two possible explanations. Either smaller black holes merge in order to form larger black holes, or smaller black holes grow enormously large by consuming gas and dust from their surrounding. Sagittarius A remains an astronomical marvel, a cosmic mystery at the heart of the Milky Way. As our understanding deepens, we continue to unravel our galaxy's secrets. In 1917, American astronomer Harlow Shapley provided the first reliable measurement of the galaxy's size. He determined the size by first determining the globular cluster's spatial distribution. As had been previously believed, Shapley discovered that the galaxy is enormous, with the Sun closer to its periphery than its center, rather than a relatively compact system. Assuming that the globular clusters surround the galaxy, he calculated that the galaxy has a diameter of roughly 100,000 light-years, or 600,000 trillion miles. The Sun is located approximately 30,000 light-years from the galaxy's center. His values have held up remarkably well over the years. The Milky Way's stellar disk is roughly the size predicted by Shapley's model. Dark matter, or invisible matter, may fill an even larger volume than expected, while neutral hydrogen is somewhat more widely distributed. According to recent calculations, a dark matter area that includes a few visible stars might have a diameter of about 2 million light-years. In addition to having multiple satellite galaxies, the Milky Way is a member of the local group of galaxies, which is a subcluster of the Virgo supercluster, which is itself a component of the Laniakea supercluster. There are at least 100 to 400 billion stars in our galaxy, and at least that number of planets. The Milky Way and everything else in space are in motion. The radiation from the Big Bang, known as the cosmic microwave background, is used as a reference point for calculating the speed of objects in space. The Milky Way galaxy is thought to be traveling at a speed of roughly 600 kilometers per second, or 372 miles per second, inside the local group of galaxies. Since the oldest stars in the Milky Way are almost as old as the universe, they most likely formed shortly after the Big Bang's dark ages. The galactic nucleus is the site of a wide range of activity, apparently powered by the black hole. The region emits X-rays and infrared light, and it is possible to see fast-moving gas clouds there. Data clearly show that matter, including some gas from the Z direction, that is perpendicular to the galactic plane, is being drawn into the black hole from outside the nuclear zone. As the gas nears the black hole, the central object's strong gravitational force squeezes the gas into a rapidly rotating disk, which extends outward about 5 to 30 light-years from the black hole. Surrounding the nucleus is an extended bulge of stars that is nearly spherical in shape, and that consists primarily of population 2 stars, though they are comparatively rich in heavy elements. A star's metallicity, or the amount of elements heavier than helium in its composition, divides stars into 3 primary population groups. Population 3 are the oldest, and population 1 stars are youngest, like our Sun. The disk portion of the galaxy contains the population 1 stars. Their ages range from 0 to 10 billion years. The spiral arms include the younger ones. The orbits of population 1 stars are well organized, with roughly circular paths in the galactic disk's midplane. Young star clusters made of population 1 stars are called open clusters because the stars are loosely bound together, in contrast to the old concentrated globular clusters. Compared to population 2 stars, population 1 stars have a higher abundance of elements heavier than helium. Astronomers frequently refer to elements heavier than helium as metals. The oldest population 1 stars have somewhat eccentric orbits that can carry them up to 3,000 light-years from the disk plane, and they have a metal abundance 0.1 times that of the Sun. The population 2 stars inhabit the spheroidal component, the stellar halo and bulge. They have masses of less than or equal to 0.8 solar masses because they are old. Their ages range from 10 to 13 billion years. Their orbits are much more randomly oriented than the population 1 orbits and are highly elliptical. As a unit, the spheroidal component has little overall rotation. Population 2 stars make up globular clusters. Globular clusters were used to find the center of the galaxy because they swarm around the center like bees around a hive. On the other hand, population 3 stars are those that have not been directly observed. They are believed to have virtually no heavy elements at all. These stars are thought to be the first ones that formed in the primordial universe shortly after the Big Bang. They were extremely massive and hot, and they burned their fuel very rapidly, turning hydrogen and helium into heavier elements. When they die, they explode as supernova, scattering some of these elements into the surrounding space. These stars probably created the first heavy elements that became part of later stars, and who have played a key role in the formation of the first galaxies. Numerous globular clusters of related stars are mixed in with the stars, and both the stars and the clusters orbit the nucleus almost radially. Our galaxy is surrounded by a huge hot gas halo that is several hundreds of thousands of light years in diameter. A halo is a spherical cloud of stars surrounding a galaxy. The mass of the halo is thought to be roughly equal to the total mass of all the Milky Way's stars. Astronomers have proposed that the Milky Way's halo is composed of 2 populations of stars. The Paranal Observatory's findings indicate that the stars in the inner halo are 11.5 billion years old. The outer halo is thought to be made up of the stellar components of smaller galactic systems. The stars in the halo are older and have lower metal content in them than the majority of the stars in the Milky Way's disk. The halo also contains gas and dark matter. The halo is evidence of the 2 galaxies that collided billions of years ago, and reinforces the idea that the Milky Way has a dynamic origin story. In the Milky Way's stellar halo, astronomers have also found more than 200 far-off variable stars referred to as Lyra stars. These stars serve as important standard candles that are used to measure astronomical distances and are often found in globular clusters. The farthest star from Earth is about 1 million light-years away, which is nearly half the distance to Andromeda. About 90% of the matter in our galaxy is dark matter, or matter that is invisible to the human eye. Stars make up the remaining 10 to 15% of the visible stuff in the Milky Way, which is composed primarily of gas and dust. Simulations of the Milky Way's rotation have shown that this massive amount of dark matter produces an invisible halo. If the dark matter did not exist, then the stars within the Milky Way would orbit much slower than has been observed. The Milky Way's dusty ring can be observed in the night sky on a clear night. As we are located approximately 26,000 light-years away from the center of the Milky Way, we are unable to capture images of the disk. Any depiction of our galaxy that you have ever seen is either an artist's portrayal of it or a separate spiral galaxy. We don't have a picture of the Milky Way as a whole, since we can only capture images of it from within the galaxy. So why do we believe that it is a barred spiral galaxy? There are several clues. The first clue to the shape of the Milky Way comes from the bright band of stars that stretches across the sky. In locations with dark night skies, this band of stars can be viewed with the naked eye. That band comes from seeing the disk of stars that forms the Milky Way from inside the disk and tells us that our galaxy is basically flat. Many telescopes, both on Earth and in space, have captured photographs of the Milky Way disk by capturing a sequence of images in different directions, which is similar to creating a panoramic photo with your phone or camera. The concentration of stars in a band adds to the evidence that the Milky Way is a spiral galaxy. If we lived in an elliptical galaxy, we would see the stars of our galaxy spread out all around the sky, not in a single band. The Milky Way galaxy was believed to be only a few thousand light-years large until around a century ago, and most people believed it to be the whole universe. Although other galaxies had been found, it was believed that they were only tiny objects inside our galaxy. French astronomer Charles Messier discovered the first galaxies in the 17th century, although he had no idea what they were at that time. As a skilled comet observer, Messier saw several additional fuzzy objects in the sky that he was certain were not comets. Fearing that other comet hunters would be misidentified as well, he put together a list to help them out. On Messier's list, 110 star clusters and spiral nebulae were detected. The objects are denoted by M for Messier, followed by a number, for example, M51. However, it took astronomers nearly 300 years to figure out the fuzzy spiral nebulae. Some claimed that these nebulae were island universes, which are objects that are similar to the Milky Way galaxy, but exist outside of it. Others disagreed and thought that these spiral objects were actually Milky Way gas clouds. The dispute continued until the 1920s, when American astronomer Edwin Hubble measured the precise distance to a spiral nebula. Hubble discovered that one of the objects he was seeing was actually a Cepheid variable star in 1923, while studying the Andromeda Nebula, which is now known as the Andromeda Galaxy. First identified in the early 1900s by American astronomer Henrietta Leavitt, Cepheids are stars whose brightness changes periodically over time. Leavitt discovered a connection between a Cepheid's luminosity or brightness and its period that is now known as the period luminosity, the PL relationship. The PL relationship can be used to calculate the actual brightness of a Cepheid by calculating its period, which is obtained by measuring changes in brightness over a period of days or weeks. Hubble established that the Cepheid he was studying in M31 was located outside of our own galaxy by calculating its distance using the PL ratio. This put an end to the controversy surrounding the spiral nebulae and proved that they were in fact far-off galaxies similar to the Milky Way. Hubble continued his study of galaxy distances using Cepheids as his measuring tool before publishing his results in 1929. In his work, Hubble created a graph showing the distances from Cepheid variables and the velocities of galaxies, which is obtained from estimating the redshift of these galaxies' spectra. The majority of galaxies are moving away from us, or receding according to this graph, and their rate of motion, the recessional velocity, is inversely correlated with their distance from us. Distant galaxies recede more quickly than nearer ones. This was later known as Hubble's law. Hubble's initial estimates for the recessional velocity of galaxies was very high, because at the time no one knew that there were actually several different types of Cepheid variables, with slightly different period luminosity relationships. But as astronomy has advanced recently, the value of the graph's slope, known as Hubble's constant, has been reduced, and the results are now converging toward an accepted value of about 65 kilometers per second, or that galaxies recede by an additional 65 kilometers per second for every megaparsec they are away from us. There are trillions of galaxies in the universe, and up to a few 100 billion stars can be found in each galaxy. The same way that one studies atoms to understand the qualities of a material, one must study the building blocks of the universe to comprehend it. Understanding the formation and evolution of galaxies is essential for our understanding of the universe. Although the study of galaxy formation dates back around 50 years to the foundational work of Egan, Lyndon Bell, and Sandage, we still do not have a comprehensive understanding of how galaxies form and evolve. Many details still need to be explored. In addition to providing us with valuable answers to the questions like where do we come from and where are we going? Observation of galaxies other than our own also enables us to draw several conclusions about the evolution of the universe. But the only galaxy we have access to a vast amount of data on its stars is our own. The other galaxies are just too far away for us to observe star by star. Before we continue, one might wonder if knowledge of the Milky Way's development provides any insight into knowledge of other galaxies. The answer is yes. Approximately 50% of stars in the modern universe reside in Milky Way-like galaxies. To put it another way, the Milky Way is a fair representation of a typical galaxy in the universe. Our knowledge of the Milky Way's development will provide a strong foundation for our understanding of other galaxies. Soon after the Big Bang, which occurred 13.61 billion years ago, the Milky Way began as one or more small overdensities in the universe's mass distribution. Some of these overdensities were the seeds of globular clusters in which the oldest remaining stars in what is now the Milky Way formed. It's possible that about half of the material in the Milky Way originated in other far-off galaxies. These star groups and individual stars now make up the Milky Way's stellar halo. The Milky Way's mass reached a point where it began to rotate relatively quickly, only billions of years after the first stars were born. Because of the conservation of angular momentum, this caused the gaseous interstellar medium to compress into a disk from a roughly spheroidal shape. Therefore, later generations of stars formed in this spiral disk. Throughout its history, the Milky Way has consumed many galaxies to get to its current size and form. In the last 12 billion years, the Milky Way has swallowed up more than a dozen galaxies. According to cosmological simulations, it merged with a particularly massive galaxy known as the Kraken, approximately 11 billion years ago. Our galaxy is currently consuming the Canis Major Dwarf Galaxy by adding the smaller galaxy's stars to its own spiral. At present, the Milky Way is traveling at a speed of 250,000 miles per hour in the direction of the Andromeda Galaxy. It is expected that the two galaxies will collide in roughly 4.5 billion years. The Milky Way and Andromeda are the two largest galaxies in the local group. They will merge because before dark energy took over, they became gravitationally bound to one another. The merger is expected to change the night sky over Earth. The Milky Way is orbiting a point in space that is roughly halfway between it and the Andromeda Galaxy. Although it's difficult to believe, experts think that our solar system probably will survive such a terrible event. Since galaxies are primarily made of empty space, this collision will not have a significant impact on our solar system. Despite having 100 billion stars each, our galaxy and the Andromeda Galaxy are very far apart. Currently, Andromeda is located 2.5 million light-years away from Earth. Similar to how a ball in the air accelerates faster as it falls toward Earth, Andromeda will be drawn closer and faster by the Milky Way's increasing gravitational pull as it gets closer. In just 4 billion years, the Milky Way and Andromeda will have tugged and ripped at one another's throats. All that's left will be the spectral framework of 2 separate galaxies in the past. The carnage will go on for as long as time does not stop, until the central supermassive black holes in both galaxies are near enough to one another to collide and join. By that point, the Milky Way and Andromeda galaxies, the 2 separate spiral galaxies, will be no more. Our solar system will have a new home in an entirely different class of galaxy called an elliptical galaxy. What about life on Earth, then? Will life on Earth continue after the merger? Well, in roughly 7.5 billion years, the Sun will grow larger and swallow the Earth, turning it into a red giant. This will happen ultimately in a timeline of about 4 billion years. As solar radiation reaching the Earth increases, Earth's surface temperature will increase. We might experience a runaway greenhouse effect, much like what's happening right now on Venus. Thus, there's a good chance that life on Earth won't exist after the merger. However, perhaps by then, some people on Earth will have developed space travel abilities. It's possible that we will have abandoned Earth and our solar system. The view of Andromeda colliding with the Milky Way might still be available to us, although from a slightly different angle. As we gaze up, let's realize how short our life is. We are stardust, seeing a cosmic tale. For whatever reason, we are here now, sitting and wondering about the universe. We, the very children of the universe, born from ordinary chemicals over billions of years, now gaze wondrously into the endless black abyss to think about it.
We are surrounded by millions of stars and planets, each hiding its own secrets and amazing sights. But beyond their beauty, there's a scarier side to these celestial bodies. In the dark depths of our universe, there are planets so frightening and strange, they make us rethink what it means to be a planet. Imagine planets where the rain is made of glass, falling sideways at super-fast speeds, or worlds covered in constant darkness, where the light from their star never reaches the ground. There are giant gas planets where the air pressure would crush you long before you could even land on them, and rocky planets with seas of lava always moving under a burning sky. These aren't the peaceful blue spheres with white clouds or the red neighbors that have caught our attention for so long. These are places of extreme conditions, where nature's rules create environments so deadly they seem like they're out of our scariest dreams. Join us on this journey as we explore the most terrifying and scary planets in our universe. TRES 2b, often hailed as one of the darkest exoplanets ever discovered, serves as a fascinating subject for anyone intrigued by the mysteries of our cosmos. Located about 750 light-years away from Earth in the constellation Draco, TRES 2b was first detected in 2006 through the Transatlantic Exoplanet Survey, a project aiming to find planets outside our solar system by observing how stars dim when a planet passes in front of them, a method known as the transit method. This celestial body orbits its star every 2.5 days, a short period that hints at its close proximity to the star, approximately 3 million miles away, which is much closer than Mercury is to our Sun. What sets TRES 2b apart from other exoplanets is its astonishing lack of reflectivity. Scientists have determined that it reflects less than 1% of the light that hits it, making it darker than coal or any other planet or moon in our solar system. This characteristic is primarily due to its atmosphere, which contains light-absorbing chemicals like vaporized sodium and potassium and the absence of clouds. This absorption of light contributes to its extremely high surface temperature, soaring above 1800 degrees Fahrenheit, making it one of the hottest planets we know of. Moreover, despite its darkness, TRES 2b has a unique feature that prevents it from being completely invisible to observers. The planet possesses a faint red glow, a result of the intense heat causing it to emit light, much like the embers of a fire. This glow adds a mysterious aura to TRES 2b, enhancing its allure among astronomers and casual stargazers alike. The extreme proximity of TRES 2b to its host star results in a phenomenon known as tidal locking. This means that one side of the planet always faces the star, receiving perpetual daylight, while the other side remains in endless night. This permanent day-night divide creates a dramatic contrast in temperatures across the planet, potentially leading to fierce winds and complex weather patterns that defy our earthbound meteorological knowledge. The atmospheric conditions of TRES 2b are no less fascinating. The presence of vaporized metals such as sodium and potassium, along with the absence of reflective cloud cover, suggests an atmosphere that is both alien and hostile by earthly standards. Researchers speculate that the planet could also host exotic forms of clouds made from compounds utterly foreign to us, possibly contributing to its dark appearance. The detection of such elements and compounds in the atmosphere provides crucial clues to understanding the chemical processes that take place on TRES 2b, offering insights into the planet's formation, evolution, and current state. The study of TRES 2b also plays a pivotal role in the broader context of exoplanet research. By comparing TRES 2b with other exoplanets, scientists can explore the diversity of planetary systems in our galaxy. For instance, the extreme characteristics of TRES 2b highlight the vast range of possible planet types, from those with thick, dense atmospheres to others that are rocky, barren, or even water worlds. These comparisons are essential for developing a comprehensive understanding of planet formation and the potential for life in the universe. TRES 2b's unique features make it a prime candidate for future observations with more advanced telescopes and instruments. The James Webb Space Telescope, along with other ground-based observatories, are poised to offer unprecedented views of exoplanets like TRES 2b. These future observations will likely provide more detailed information about the planet's atmosphere, surface conditions, and perhaps even clues to its geological activity. Continuing our exploration of the cosmos, we journey to 55 Cancri E, an exoplanet that captivates the imagination with its extraordinary characteristics. Situated approximately 40 light-years away in the constellation Cancer, 55 Cancri E is a world of extremes, a so-called super-Earth that is about twice the size of our planet and 8 times its mass. This intriguing exoplanet orbits its host star, 55 Cancri A, at such a close distance that a year there lasts a mere 18 hours, a stark contrast to our 365-day orbit around the Sun. What sets 55 Cancri E apart in the pantheon of exoplanets is not just its size or its incredibly short orbital period, but its potential surface conditions, which have led to speculative titles like Diamond Planet. Scientists theorize that the intense pressure within 55 Cancri E could transform carbon into diamond, creating a world that quite literally sparkles with these precious gems. This hypothesis stems from observations and models suggesting the planet's composition is rich in carbon alongside other elements. While the romantic notion of a diamond planet captures the imagination, it's important to remember that this is a hypothesis, one of many theories that researchers are eager to test with more advanced observational tools. The temperature on 55 Cancri E is another aspect that fascinates scientists and laypeople alike. With surface temperatures soaring to over 4,000 degrees Fahrenheit, this planet is far from hospitable to life as we know it. The extreme heat, a result of its proximity to its star, ensures that any atmosphere present is unlike anything in our solar system, possibly consisting of heavy gases in a supercritical fluid state, a state that blurs the line between gases and liquids. As we delve further into the enigma that is 55 Cancri E, it's clear this planet holds a trove of secrets that challenge our understanding of planetary systems. Its close orbit around its host star, a mere 1.5 million miles away, places it in a category of exoplanets known as ultra-short period planets. This proximity leads to one of the most intriguing aspects of 55 Cancri E. The tidal forces between the planet and its star are so intense that the planet is likely tidally locked. This means one side of the planet constantly faces the star, basking in perpetual daylight, while the other side is shrouded in eternal darkness. The stark contrast between the day side and night side of 55 Cancri E has profound implications for its climate and atmospheric dynamics. Scientists speculate that the temperature difference could drive supersonic winds, transporting heat from the blistering day side to the cooler night side. This extreme weather system could result in a complex and dynamic atmosphere, unlike anything observed in our own solar system. Adding to the mystery of 55 Cancri E is the composition of its atmosphere. Early observations suggested the presence of water vapor, but more recent studies hint at a hydrogen-rich atmosphere, with layers possibly containing hydrogen cyanide, a marker of carbon-rich environments. Such findings further fuel the speculation that 55 Cancri E could indeed be a diamond planet, with a carbon-heavy interior that might turn into diamond under the planet's extreme pressure and temperature conditions. The potential for 55 Cancri E to host an atmosphere rich in carbon compounds not only intrigues scientists, but also stirs the imagination about what other kinds of worlds could exist in the vast expanses of our galaxy. The planet's study is at the frontier of exoplanet research, pushing the limits of current observational technologies and theories of planet formation and composition. Embarking further into these mysterious planets, we encounter Gliese 581c. Discovered in 2007, Gliese 581c orbits the red dwarf star Gliese 581, situated roughly 20 light-years away in the constellation Libra. This exoplanet is particularly noteworthy for its position within its star's habitable zone, the region where conditions might be right for liquid water to exist, a crucial ingredient for life as we know it. Gliese 581c is about 1.5 times the size of Earth, making it a super-Earth, and has a mass around 5.5 times that of our planet. These dimensions suggest that Gliese 581c has a significantly higher gravity than Earth, which would have profound effects on the planet's atmosphere and potentially on any water or life forms present. The planet completes an orbit around its host star in just under 13 days, a fact that points to its close proximity to Gliese 581 and raises intriguing questions about its climate and atmospheric conditions. One of the most captivating aspects of Gliese 581c is the possibility that it may harbor liquid water, a hypothesis that hinges on the planet's temperature and atmospheric pressure. If conditions are just right, Gliese 581c could have oceans, rivers, or lakes of water, environments that on Earth are teeming with life. However, scientists also caution that the planet's close orbit could mean it's tidally locked, with one side perpetually facing its star and the other in constant darkness. This could result in extreme temperature variations across the planet, with one side possibly too hot and the other too cold for liquid water to persist. As we delve deeper into the mysteries surrounding Gliese 581c, we uncover layers of complexity that challenge and expand our understanding of habitable worlds. The intriguing prospect of this planet being within its star's habitable zone does more than just spark the imagination. It drives forward the scientific quest to understand the conditions under which planets can sustain life. The study of Gliese 581c, along with its sibling planets in the Gliese 581 system, offers a rich tapestry for understanding the diversity of planetary environments. The concept of a tidally locked planet, such as Gliese 581c might be, introduces fascinating scenarios for climate and weather patterns. On such a world, the stark contrast between the perpetual day and eternal night sides could create powerful atmospheric dynamics. Scientists speculate that if the planet has an atmosphere, it might circulate heat from the day side to the night side, potentially allowing for a more even temperature distribution than one might expect. This could create a twilight zone, a region where temperatures might be conducive to liquid water and, conceivably, life. The challenges of exploring a planet like Gliese 581c are immense, given its distance from Earth and the current limits of our technology. However, projects and missions in development aim to launch telescopes that can observe exoplanets directly, analyzing their atmospheres for signs of water vapor, oxygen, methane, and other gases that might indicate the presence of biological processes. Such observations could provide indirect evidence of life, or at the very least, of environments where life as we know it could exist. Furthermore, the study of Gliese 581c contributes to our understanding of red dwarf stars and their planetary systems. Red dwarfs are the most common type of star in the Milky Way, and their long lifespans provide a stable environment for potentially habitable planets. However, their propensity for powerful flares could pose a risk to the atmospheres of closely orbiting planets, stripping away the very conditions necessary for life. Understanding how planets like Gliese 581c withstand their stellar environments is crucial for assessing the habitability of planets around red dwarfs. Nestled within the cosmic neighborhood, Proxima Centauri b presents a tantalizing glimpse into the potential for life beyond Earth. Orbiting Proxima Centauri, the closest known star to the Sun at a mere 4.24 light-years away, this exoplanet captures the imagination and curiosity of scientists and space enthusiasts alike. Discovered in 2016, Proxima Centauri b is situated in the habitable zone of its star, where temperatures could allow for liquid water to exist on its surface under the right atmospheric conditions. This intriguing world is approximately 1.3 times the mass of Earth, suggesting it is a rocky planet much like our own. The close proximity to its star means Proxima Centauri b completes an orbit in just 11.2 Earth days, presenting a scenario where the planet could be tidally locked. This would result in one side of the planet always facing the star, basking in perpetual daylight, while the other side languishes in endless night. The implications for climate, weather, and potential habitability are profound, sparking discussions and studies aimed at understanding this unique environment. Despite the excitement surrounding Proxima Centauri b, the red dwarf star it orbits is known for its temperamental nature, often emitting powerful flares. These stellar outbursts could pose significant challenges to the potential for life, possibly stripping away the atmosphere or subjecting the surface to high levels of radiation. Yet the possibility remains that, under the right conditions, Proxima Centauri b could support an atmosphere that protects it from these harsh stellar winds, preserving the potential for habitability. Given its proximity to its host star, Proxima Centauri b is subjected to intense stellar radiation, much more than Earth receives from the Sun. This factor plays a crucial role in determining the planet's atmosphere and surface conditions. If Proxima Centauri b has a strong magnetic field, similar to Earth's, it could shield the planet from some of these harmful radiations, making it a more hospitable environment than initially thought. The existence of water in any form on its surface would be a groundbreaking discovery, significantly boosting the potential for life. The intriguing aspect of Proxima Centauri b's orbit, potentially being tidally locked, raises questions about the climate dynamics on such planets. The concept of a permanent day side and a permanent night side suggests extreme weather conditions, with possible implications for atmospheric circulation patterns that could distribute heat around the planet. Scientists hypothesize that if Proxima Centauri b has an atmosphere, it might have a temperate zone at the boundary between the light and dark sides, where conditions could be conducive to liquid water and, by extension, life. The ongoing and future missions aimed at exploring Proxima Centauri b are equipped with sophisticated instruments designed to detect the faintest signals of an atmosphere and analyze its composition. Spectroscopy, a method used to identify the chemical makeup of a planet's atmosphere by studying light from the star as it passes through, could reveal the presence of molecules like oxygen, carbon dioxide, and methane, all of which could hint at biological processes. The prospect of sending a probe to Proxima Centauri b, although decades away, sparks the imagination. Such a mission would provide direct observations and data, offering insights into the planet's geology, atmospheric conditions, and potential biosignatures. Current initiatives, like the Breakthrough Starshot project, aim to develop the technology necessary to send small, light-powered spacecraft to the Alpha Centauri system, of which Proxima Centauri is a part, marking a monumental step in interstellar exploration. Venturing further into the cosmos introduces us to Pi Mensae c, a compelling exoplanet that holds its own unique place within the vast tapestry of known celestial bodies. Discovered orbiting the star Pi Mensae, located some 60 light-years away in the constellation Mensa, this planet is part of a growing list of worlds that challenge and expand our understanding of planetary systems beyond our own. Pi Mensae c is particularly notable for being a super-Earth, a type of exoplanet with a mass higher than Earth's but substantially lower than that of the ice giants Uranus and Neptune. Its discovery, announced in 2018 through data from NASA's Transiting Exoplanet Survey satellite, marked a significant achievement in the search for exoplanets. Pi Mensae c has a mass around 4.82 times that of Earth, and completes an orbit around its star every 6.27 days, indicating a close proximity to its host star, much closer than Mercury is to the Sun. What makes Pi Mensae c fascinating is not just its size or orbit, but its position within a system that also hosts a gas giant, Pi Mensae b, discovered in 2001. This setup provides a rich field for studying the dynamics of multi-planet systems, especially with such contrasting types of planets, a super-Earth and a gas giant, cohabiting around the same star. The differences in their compositions, orbits, and potential atmospheres offer a wealth of data for scientists trying to understand the variety of planetary environments that exist in our galaxy. Despite its proximity to its host star, the question of Pi Mensae c's habitability or its potential to host an atmosphere remains open. Its close orbit suggests it could be subjected to intense stellar radiation, possibly affecting any atmosphere it might have. However, the detailed study of its atmospheric composition, which could reveal the presence of gases like water vapor or carbon dioxide, has yet to be conducted. These studies are crucial for assessing not just the conditions on Pi Mensae c, but also the potential for life on planets that share its characteristics. The story of Fomalhaut b is as mysterious as it is fascinating. Initially discovered in 2008 through the keen eye of the Hubble Space Telescope, it was celebrated as one of the first exoplanets, planets outside our solar system, directly imaged, offering a glimpse into the methods of detecting and studying distant worlds. However, the planet's existence soon became a matter of debate. Unlike the rocky or gas giants found in our solar system, Fomalhaut b did not emit any infrared radiation, an oddity that puzzled scientists. Infrared radiation typically indicates a planet's heat, which can be used to infer its size and composition. The plot thickened when further observations failed to detect the planet consistently. It seemed to vanish and reappear in different datasets, behaving more like a ghostly apparition than a solid celestial body. This led to a sensational turn in 2012 when researchers proposed that Fomalhaut b might not be a planet at all. Instead, it could be a vast cloud of dust resulting from a colossal collision between two icy bodies, remnants orbiting Fomalhaut. This hypothesis painted a picture of a cosmic demolition derby, with Fomalhaut b as the fleeting evidence of a dramatic event. But the story does not end there. The debate continued to evolve with more observations and studies. Some astronomers hold on to the planet hypothesis, suggesting that Fomalhaut b might be a planet shrouded in a huge cloud of dust, perhaps from a massive ring system or the aftermath of an impact, which could explain the unusual observations. This theory keeps the door open for Fomalhaut B's planetary status, suggesting it might be a world unlike any we've encountered. The journey of discovery surrounding this distant world showcases the leaps in astronomical techniques and the persistent curiosity that drives the scientific community forward. After its initial detection, the narrative of Fomalhaut B became a catalyst for debate and innovation, encouraging astronomers to refine their methods of observing and interpreting data from the far reaches of space. Advancements in telescopic technology and imaging techniques have been at the forefront of this quest. The Hubble Space Telescope, with its unparalleled view of the universe, free from the distortions of Earth's atmosphere, played a pivotal role in the story of Fomalhaut B. Yet, the intrigue of Fomalhaut B pushed scientists to look beyond conventional methods. The application of dynamic imaging and the pursuit of infrared signatures using other space and ground-based telescopes added layers of complexity to the investigation, illustrating the multifaceted approach required to study such elusive targets. The scientific interest in Fomalhaut B also highlights a broader theme in the field of astronomy: the search for exoplanets and the conditions that might support life. Each discovery, each anomaly encountered in the vastness of space, brings us closer to understanding our place in the universe. The peculiar case of Fomalhaut B, with its disputed nature and the mysteries surrounding its existence, serves as a bridge to ponder more profound questions about planet formation, the diversity of planetary systems, and the potential for habitable worlds beyond our solar system. Moreover, Fomalhaut B's story is a testament to the dynamic nature of the universe. If indeed the result of a colossal impact, it reminds us of the constant changes occurring in cosmic scales of time and space, shaping and reshaping the architecture of galaxies. The potential for new worlds to be born from the debris of such cataclysmic events, or for existing planets to be cloaked in dust clouds, enriches our understanding of planetary evolution and survival in the harsh environment of space. Deep within the universe, there exists a planet that seems almost out of place in the cosmic narrative due to its sheer age. This character is not a mythical figure but a star, known affectionately as Methuselah, or more formally as HD 140283. Methuselah's story captivates not just because of its age, but because it challenges our understanding of the cosmos, offering a paradox that has puzzled astronomers for years. Methuselah is intriguing because its age, estimated to be around 14.5 billion years, appears to defy logic. This estimation puts it at nearly the same age as the universe itself, which, according to current cosmological models based on the Big Bang theory, is about 13.8 billion years old. The apparent conundrum of a star older than the universe prompts a deeper dive into the methods used to determine stellar ages and the uncertainties inherent in these measurements. The age of Methuselah was estimated using a technique that involves measuring its composition and its movement. Stars, much like people, change as they age, and by understanding a star's composition, particularly its metallicity, or the abundance of elements heavier than helium, astronomers can infer its age. Methuselah has an unusually low metallicity, indicating it formed when the universe was very young and contained few elements beyond hydrogen and helium. The star's speed and trajectory also offer clues to its ancient origin, suggesting it belongs to the halo of the Milky Way, a population of stars that envelops the galaxy and includes some of its oldest members. The apparent age discrepancy of Methuselah has led scientists to refine their methods and question their assumptions. It has sparked discussions about the precision of age-dating techniques, the interpretation of data, and even the models of stellar evolution. This ongoing debate exemplifies the dynamic nature of science, where anomalies challenge established theories and drive the quest for greater understanding. In addressing the Methuselah paradox, researchers have considered various factors that might affect their age estimates, such as the star's initial composition and the impact of its environment. Adjustments to the models of stellar evolution and more precise measurements of the star's properties have narrowed the age gap, suggesting Methuselah may be slightly younger than initially thought, but still remarkably ancient. WASP-12b, a distant and exotic world far beyond our solar system, presents a stark contrast to the celestial bodies we've previously explored. This intriguing planet, discovered in 2008, orbits the star WASP-12, located approximately 600 light-years away in the constellation Auriga. What makes WASP-12b stand out in the vast catalogue of exoplanets is its classification as a hot Jupiter, a type of gas giant that orbits very close to its host star, leading to extreme atmospheric conditions. With a mass almost 1.4 times that of Jupiter but an orbital period of just over a day, WASP-12b's proximity to its star results in surface temperatures soaring above 2,200 degrees Celsius. This intense heat has profound effects on the planet's atmosphere and structure, causing it to assume an elongated shape rather than a perfect sphere. Scientists have observed that the high temperatures on WASP-12b lead to the presence of heavy metals like iron and magnesium in its atmosphere, elements that in cooler gas giants would condense into clouds. Another remarkable feature of WASP-12b is its tidal interactions with its host star. The gravitational forces at play are so strong that the planet is being gradually pulled closer, leading to a scenario where WASP-12b may eventually be consumed by WASP-12. This grim fate is not immediate, but the process provides a fascinating glimpse into the life cycle of exoplanets and their stars. WASP-12b also plays a crucial role in the study of planetary atmospheres. Its detection and analysis have been made possible through transit observations, where the planet passes in front of its host star from our perspective, allowing astronomers to study the starlight that filters through the planet's atmosphere. This method has revealed much about WASP-12b's composition and behavior, offering insights into the chemistry of other hot Jupiters. WASP-12b was discovered through the Wide-Angle Search for Planets, WASP project, a ground-based effort designed to detect planets outside our solar system using the transit method. The transit method involves monitoring the brightness of stars over time and looking for periodic dimming, which indicates that a planet is passing in front of the star from the observer's perspective. This method is particularly effective for identifying planets that orbit close to their host stars, as these planets tend to transit more frequently and produce more noticeable changes in brightness. In the case of WASP-12b, astronomers observed a slight dip in the brightness of its host star, WASP-12, which occurs every 1.1 days, the period it takes for the planet to complete an orbit around its star. The regularity and depth of these dips in brightness provided clear evidence of a planet's presence and allowed scientists to calculate its size and orbital distance. Subsequent spectroscopic observations, which analyzed the star's light to detect the gravitational pull of the planet, confirmed the planet's mass and further details about its characteristics. The discovery of WASP-12b was significant because it added to the growing list of exoplanets that challenge our understanding of planet formation and behavior, particularly those in close orbits around their stars. It also underscored the efficacy of the transit method and ground-based telescopes in contributing to exoplanet science, a field that has rapidly expanded since the first exoplanets were confirmed in the 1990s. Discovered by the Kilodegree Extremely Little Telescope or KELT survey, KELT 9b orbits a star some 670 light-years away in the constellation Cygnus. This planet is not only remarkable for its sheer size, closely resembling that of Jupiter, but it's also distinguished by its extreme temperatures and the peculiar nature of its orbit around a blue A-type star, one of the hottest stars known to host a planet. KELT 9. B's discovery unveiled a world where daytime temperatures soar above 4,300 degrees Celsius, about 7,800 degrees Fahrenheit, hotter than many stars and setting the record for the hottest exoplanet discovered to date. Such blistering temperatures are attributed to the planet's close proximity to its host star, KELT 9, which it orbits every 1.5 days. This rapid orbit places KELT 9b in a category of ultra-short period planets, experiencing conditions that are beyond the extremes found in our own solar system. The intense radiation from its host star, has profound effects on the planet's atmosphere. Studies suggest that the ultraviolet light is so powerful it can split molecules apart, preventing the formation of many chemicals common in cooler planetary atmospheres and leading to a predominantly atomic composition. This has piqued the interest of astronomers, as it provides a unique laboratory for studying atmospheric chemistry under extreme conditions. Moreover, Kelt 9b's atmosphere contains ions, such as ionized iron and titanium, unusual for planetary atmospheres and indicative of the extreme heat that can ionize metals. The presence of these metals in gaseous form provides insights into the planet's atmospheric dynamics and the types of chemical reactions that can occur under such intense irradiation. As we further explore the mysterious nature of Kelt 9b, the planet's relationship with its host star takes center stage, revealing a dynamic and potentially catastrophic future. The extreme temperatures and rapid orbit of Kelt 9b are just the beginning of its story. The gravitational forces exerted by its host star, Kelt 9, are causing tidal interactions that have profound implications for the planet's structural integrity and long-term survival. These tidal forces are not only responsible for Kelt 9b's elongated shape, but also contribute to the gradual decay of its orbit. Over time, it is expected that Kelt 9b will spiral closer to its star, leading to increased heating and atmospheric loss. This process, known as orbital decay, could ultimately result in the planet being consumed by its star. Such a fate underscores the transient nature of some exoplanetary systems, offering a glimpse into their life cycle and evolution. The study of Kelt 9b also sheds light on the mechanisms of atmospheric escape. The intense heat and radiation from Kelt 9 are powerful enough to strip away the planet's atmosphere, atom by atom, into space. This atmospheric escape is observable as a tail of gas being blown off the planet, akin to a comet's tail, providing direct evidence of the harsh conditions that prevail. Furthermore, the peculiarities of Kelt 9b extend to its night side, which remains a subject of intrigue. Despite the extreme temperatures on its day side, the night side of the planet experiences significantly cooler, though still extremely high, temperatures. This discrepancy poses questions about the efficiency of heat distribution across the planet's atmosphere and the potential for complex atmospheric dynamics involving winds and jet streams. The exploration of Kelt 9b has broad implications for our understanding of exoplanetary atmospheres, particularly those orbiting close to their stars. It challenges astronomers to develop models that can accurately predict the behavior of planets under such extreme conditions, contributing to our broader understanding of planetary science. Continuing our journey in space, we encounter Kepler 10b, identified by the Kepler Space Telescope, which was tasked with discovering Earth-like planets in habitable zones. Kepler 10b orbits its star some 560 light-years away in the constellation Draco. This exoplanet holds the distinction of being one of the first rocky planets confirmed outside our solar system, providing a glimpse into the diverse planetary compositions that exist beyond our familiar celestial neighborhood. Kepler 10b is a world of extremes, with a mass 3.3 times that of Earth, yet it orbits its star at a distance more than 20 times closer than Mercury is to our Sun. This close proximity results in a year on Kepler 10b lasting just 0.84 Earth days, and contributes to surface temperatures that can exceed 1,300 degrees Celsius, about 2,372 degrees Fahrenheit. Far too hot to support life as we know it. The planet's surface is thought to be molten in some areas, with possibly oceans of lava, a testament to the intense heat generated by its star. The discovery of Kepler 10b was significant for several reasons. It was the first planet found by the Kepler mission to have both its size and mass measured, allowing scientists to calculate its density and confirm its rocky nature. This achievement marked a milestone in exoplanet research, offering evidence that rocky planets not only exist outside our solar system, but can also be detected and studied with the technology at our disposal. Building upon the discovery of Kepler 10b, the exploration of this intriguing exoplanet opens doors to deeper questions about the nature of planets beyond our solar system. The methods used to uncover Kepler-10b's secrets, particularly the transit method, where the planet's passage in front of its star leads to a slight dimming of the star's light observed by telescopes, underscore the sophistication of current astronomical techniques. This process not only revealed Kepler-10b's presence, but also provided insights into its composition and physical characteristics, highlighting the potential for further discoveries. Kepler-10b's extreme proximity to its host star raises fascinating questions about its formation and history. How did it end up in such a close orbit? Theories suggest that it might have migrated inward from a more distant orbit over millions of years, a journey that could have dramatically altered its composition and surface features. This scenario prompts a re-evaluation of our understanding of planetary system dynamics and the forces that shape them over time. Furthermore, the study of Kepler-10b has implications for the search for life beyond Earth. While this planet itself is inhospitable to life as we know it, due to its scorching temperatures, its detection demonstrates the capability to find and analyze Earth-sized and potentially habitable planets in other solar systems. This effort is part of a broader quest to identify worlds where conditions might be right for life. Now let's take a step back and explore some of the more familiar planets. Venus, our celestial neighbor, presents a fascinating contrast to Earth, offering a unique perspective on planetary science and the conditions necessary for life. Known as the second planet from the Sun, Venus orbits within our solar system's inner circle, positioned closer to the Sun than Earth. This proximity to our star contributes to Venus's status as the hottest planet in our solar system, with surface temperatures averaging around 465 degrees Celsius, 869 degrees Fahrenheit. Such extreme conditions are primarily due to its dense atmosphere, composed mostly of carbon dioxide, with clouds of sulfuric acid creating a runaway greenhouse effect that traps heat. Despite being similar in size and composition to Earth, earning it the nickname Earth's twin, Venus's surface and atmospheric conditions are vastly different. Its rotation is notably slow, taking about 243 Earth days to complete a single rotation on its axis, which is longer than its orbital period around the Sun of about 225 Earth days. Intriguingly, Venus rotates in the opposite direction to most planets in our solar system, including Earth, meaning the Sun rises in the west and sets in the east on Venus. The exploration of Venus has been a challenging endeavor due to its harsh environment, with numerous missions attempting to study the planet up close. Soviet Venera probes in the 1970s and 1980s provided the first detailed images of its surface, revealing a world covered with volcanic landscapes, vast plains, and high mountain ranges. Recent studies suggest Venus is still geologically active, with potential signs of recent volcanic activity. Venus also exhibits a phenomenon known as ashen light, an apparent faint illumination of its dark side when viewed from Earth, which has been a subject of speculation and study among astronomers for centuries. Additionally, the planet's thick clouds reflect sunlight efficiently, making Venus the third brightest object in the sky visible from Earth, after the Sun and the Moon. Neptune stands as a sentinel in the outer reaches of our solar system, the eighth planet from the Sun, and the most distant among the known planets, following the reclassification of Pluto as a dwarf planet. Discovered in 1846, its existence was predicted mathematically before it was visually confirmed, a testament to the power of Newtonian mechanics and a milestone in the history of astronomy. Neptune is 4 times wider than Earth, with a diameter of about 49,244 kilometers, 30,598 miles, making it the smallest of the gas giants in our solar system, yet it packs a dense atmosphere composed primarily of hydrogen and helium, with traces of methane giving it a striking blue hue. Orbiting the Sun at an average distance of 4.5 billion kilometers, about 2.8 billion miles, Neptune takes approximately 165 Earth years to complete a single orbit, which means it has only completed one orbit since its discovery. Despite its distance from the Sun, Neptune's atmosphere is surprisingly active, with dynamic weather systems and the fastest winds in the solar system, reaching speeds of up to 2,100 kilometers per hour, about 1,300 miles per hour. This activity is thought to be driven by the planet's internal heat, rather than solar energy, which is minimal at such a great distance. Neptune's magnetic field is also a subject of interest, as it is tilted significantly relative to its rotation axis and offset from the planet's center, similar to the magnetic field of Uranus. This unusual magnetic orientation may be the result of the planet's internal structure and heat distribution, offering clues about the processes occurring within its deep interior. The planet is encircled by a faint system of rings and 14 known moons, with Triton being the largest and most notable. Triton orbits Neptune in a retrograde direction, meaning it moves in the opposite direction of the planet's rotation, suggesting that it may have been captured by Neptune's gravity and is not a native moon. Triton is geologically active, with cryovolcanoes that eject nitrogen gas and dust particles from beneath its surface, creating a thin atmosphere that, like Neptune's, is mostly nitrogen. The exploration of Neptune has been limited, with the Voyager 2 spacecraft providing the bulk of our current knowledge during its flyby in 1989. The data collected by Voyager 2 revealed Neptune as a world of immense beauty and complexity, with swirling clouds, high-altitude ice crystals, and dark spots indicative of storm systems. These observations have laid the groundwork for future missions that may further unravel the mysteries of this distant planet, deepening our understanding of the outer solar system and the forces that shape it. Uranus, the seventh planet from the Sun, offers a fascinating study in contrasts and surprises within our solar system. Discovered in 1781 by William Herschel, its discovery expanded the known boundaries of our solar system for the first time in modern history. Unlike the more familiar rocky planets of the inner solar system, or the gas giants like Jupiter and Saturn, Uranus is often categorized as an ice giant. This classification comes from its unique composition, primarily of water, ammonia, and methane ices, beneath a thick atmosphere of hydrogen and helium. One of the most striking features of Uranus is its dramatic tilt. The planet rotates on its side, with an axial tilt of about 98 degrees, meaning it essentially rolls around the Sun on its orbit. This peculiar orientation leads to extreme seasonal variations, with each pole getting around 42 years of continuous sunlight, followed by 42 years of darkness. This tilt is believed to be the result of a massive collision with an Earth-sized object long ago, which drastically altered the planet's orientation. Uranus is encircled by a complex system of rings, less prominent than Saturn's but equally intriguing. These thin, dark rings were only discovered in 1977, highlighting how much remains to be learned about this distant planet. Additionally, Uranus is accompanied by 27 known moons, each named after characters from the works of William Shakespeare and Alexander Pope, adding a cultural layer to the scientific exploration. Despite its distance and the challenges it presents for observation, Uranus has been visited once by a spacecraft Voyager 2 in 1986. This flyby provided a wealth of data, revealing many of the planet's secrets and leaving many questions unanswered. The pale cyan of Uranus, due to the methane in its atmosphere which absorbs red light and reflects blue, and its calm appearance belie a complex atmospheric system with the fastest winds in the solar system, reaching speeds of up to 900 kilometers per hour. Pluto, once the ninth planet from the Sun in our solar system, has captivated the curiosity and imagination of astronomers and the public alike since its discovery in 1930 by Clyde Tombaugh. Located in the Kuiper Belt, a region filled with icy bodies and remnants from the solar system's formation, Pluto is a dwarf planet, a category that it helped define when the International Astronomical Union, IAU, refined the criteria for planethood in 2006. Despite its reclassification, Pluto continues to be a subject of significant scientific interest and exploration, embodying the mysteries that lie at the edge of our solar system. With a diameter of about 2,377 kilometers, 1,477 miles, Pluto is smaller than Earth's moon. Its orbit is highly elliptical, taking it on a 248 Earth-year journey around the Sun, during which it can come closer to the Sun than Neptune for a period before moving back to its more distant position. This unique orbit contributes to Pluto's complex and variable environment. Pluto's surface is surprisingly diverse, with vast plains, towering mountains, and deep valleys. One of the most striking features is a heart-shaped glacier named Sputnik Planitia, composed of nitrogen ice, which hints at a geologically active world beneath its icy exterior. The presence of mountains made of water ice, which behaves like rock due to the extremely low temperatures, suggests geological processes that have yet to be fully understood. The dwarf planet's atmosphere is thin and composed mostly of nitrogen, with traces of methane and carbon monoxide. As Pluto moves away from the Sun, its atmosphere freezes and falls to the surface as snow, a seasonal change that provides insight into the dynamics of planetary atmospheres under extreme conditions. Pluto's 5 known moons, Charon, Styx, Nix, Kerberos, and Hydra, add another layer of intrigue to its story. Charon, the largest of these moons, is so sizable in relation to Pluto that they are often considered a double dwarf planet system. The gravitational dance between Pluto and Charon presents a fascinating dynamic, with both bodies orbiting a point in space between them, rather than Pluto being the sole center of orbit. The exploration of Pluto, particularly by the New Horizons spacecraft in 2015, has opened a new chapter in our understanding of the outer solar system. New Horizons flyby provided unprecedented detail about Pluto's surface, atmosphere, and moons, shedding light on a world that is far more complex and dynamic than previously imagined. Jupiter's moon Io stands as a celestial body of extreme contrasts and profound fascination within our solar system. Discovered in 1610 by Galileo Galilei, alongside 3 other moons orbiting Jupiter, Io marks itself as the innermost of the Galilean moons and is heralded for its dramatic geological activity. This moon, slightly larger than Earth's own moon, is characterized by over 400 active volcanoes on its surface, making it the most volcanically active body in our solar system. The source of this intense volcanic activity lies in the powerful gravitational tug-of-war between Jupiter and the other Galilean moons, Europa and Ganymede, which causes immense tidal heating within Io's interior, flexing and heating its interior to keep its mantle and core in a molten state. Io's surface is a tapestry of sulfur and sulfur dioxide frost, giving it a colorful appearance with yellow, red, white, black, and green hues, unlike any other celestial body we know. This vivid landscape is constantly being reshaped by volcanic eruptions that can eject plumes of material up to 500 kilometers, about 310 miles, into space, creating extensive basins and depositing large amounts of sulfur in various forms. Despite its hostile environment, Io plays a crucial role in our understanding of geological processes beyond Earth. It challenges scientists to reconsider notions of planetary and moon formation, the conditions necessary for volcanic activity, and the potential for life in extreme environments. The study of Io has also provided insights into the magnetic and gravitational interactions within the Jupiter system, particularly how Io contributes to Jupiter's magnetic environment by generating an electric current known as the Io flux tube, which produces intense auroras on Jupiter. The exploration of Io has been primarily through flyby missions, most notably by the Voyager spacecraft in the late 1970s and the Galileo orbiter in the 1990s and early 2000s. These missions have offered glimpses into Io's complex and dynamic environment, revealing a world where the ground is literally never still. Continuing our exploration of Io, Jupiter's fascinating moon, we delve deeper into the implications of its unique geologic and volcanic features. The immense volcanic activity on Io is not just a spectacle of nature's power, but also a window into the internal dynamics of celestial bodies. The heat generated by tidal forces within Io's interior leads to frequent and massive volcanic eruptions, shaping a landscape that is constantly being renewed and reformed. This process offers scientists a live laboratory to study how volcanic activity can affect a body's surface, atmosphere, and even its potential habitability. One of the most striking discoveries about Io is the presence of lava lakes and vast flows of molten rock that cover large swathes of its surface. These features indicate that Io's mantle must be incredibly hot, with some estimates suggesting temperatures exceeding 1,200 degrees Celsius, about 2,192 degrees Fahrenheit, in certain areas. The composition of these lavas, rich in silicates and sulfur compounds, differs from the typical basaltic flows found on Earth, providing clues about the Moon's formation and the elemental makeup of the outer solar system. Io's influence extends beyond its own orbit, impacting Jupiter's magnetosphere. The Moon ejects about 1 ton of material into space every second through its volcanic plumes, contributing to a torus of plasma that encircles Jupiter. This interaction not only fuels Jupiter's auroras, but also creates a complex electromagnetic environment that challenges our understanding of planetary magnetospheres. The study of Io has broader implications for the search for life beyond Earth. While Io itself is too hostile for life as we know it, its volcanic activity underscores the diverse conditions under which moons and planets can exist. Understanding Io helps refine our models of celestial dynamics and habitability, informing the search for life-supporting environments in other star systems. Future missions to the Jupiter system, such as the European Space Agency's Jupiter Icy Moons Explorer, scheduled for launch in the 2020s, and NASA's Europa Clipper, aim to further explore Io and its fellow Galilean moons. These missions will provide new insights into Io's volcanic activity, its interaction with Jupiter's magnetic field, and the Moon's role in the larger Jovian system. Io remains a symbol of the dynamic and active processes that can exist on moons throughout the universe, challenging our perceptions of where and how dynamic geological activity can occur. Its study enriches our understanding of the solar system, offering lessons on the forces that shape celestial bodies and the potential for discovering even more worlds of wonder beyond our own. Saturn's moon Titan stands as one of the most intriguing and distinctive bodies in our solar system, capturing the fascination of scientists and space enthusiasts alike. As the largest moon of Saturn and the second largest in the solar system, Titan is unique in having a dense atmosphere, thicker than that of Earth, composed mainly of nitrogen with traces of methane and hydrogen. This thick atmosphere obscures the moon's surface from view in visible light, requiring radar and infrared instruments to peer through the haze. What sets Titan apart from all other moons in our solar system is its complex weather system, including rain, rivers, lakes, and seas, though not of water, but of liquid methane and ethane. This discovery has led to Titan being one of the most Earth-like worlds we know of, albeit with a frigid surface temperature averaging around -179 degrees Celsius, -290 degrees Fahrenheit. Despite these chilly conditions, Titan's atmosphere and surface processes mirror those of Earth's own hydrological cycle, with evaporation, cloud formation, and precipitation shaping the landscape. Titan's surface is varied and includes vast dunes of hydrocarbon sands, mountain ranges, and a multitude of liquid hydrocarbon lakes in the polar regions, making it an object of intense scientific study. The presence of liquid bodies on Titan makes it a prime candidate in the search for extraterrestrial life, particularly in exploring the prebiotic chemistry that could lead to life. The Cassini-Huygens mission, a collaboration between NASA, ESA, European Space Agency, and ESI, Italian Space Agency, has been instrumental in unveiling Titan's secrets. When the Huygens probe descended onto Titan's surface in 2005, it provided humanity's first close-up view of this alien landscape, revealing a complex world with features reminiscent of Earth, such as river channels and stones smoothed by liquid erosion. This exploration of Titan has opened up new questions about the moon's past and present, including the sources of its methane, the mechanisms driving its climate and geological processes, and the potential for hosting simple forms of life in its vast liquid reservoirs. Delving deeper into the mysteries of Titan, Saturn's largest moon, we find a world that continues to captivate with its potential for scientific discovery. Beyond its Earth-like weather systems and hydrocarbon lakes, Titan holds clues to the solar system's history and the complex chemistry that could lead to life. One of the most intriguing aspects of Titan is its subsurface ocean, believed to lie beneath the icy crust. This hidden ocean, possibly composed of water mixed with salts and ammonia, represents a key interest for astrobiologists searching for extraterrestrial life. The interaction between the liquid water ocean and the rocky mantle beneath could create conditions suitable for chemical reactions foundational to life as we know it. The study of Titan is not just about understanding another world in our solar system. It's also about gaining insights into Earth's past and the potential for life elsewhere in the universe. Titan's thick atmosphere, rich in organic molecules, acts as a window into the chemical processes that might occur on exoplanets with similar conditions. The complex organic chemistry occurring in Titan's atmosphere and on its surface, driven by sunlight and possibly by cryovolcanism, creates a vast array of compounds that could be precursors to more complex molecules associated with life. Future missions to Titan, such as NASA's Dragonfly mission slated for launch in the 2030s, aim to explore its chemistry and habitability further. Dragonfly is a drone-like rotorcraft designed to fly through Titan's dense atmosphere, covering much greater distances than a traditional lander or rover could. Its goals include studying prebiotic chemistry and habitability at various locations, analyzing the moon's surface and subsurface properties, and investigating its atmospheric and surface processes. By directly sampling Titan's environment and conducting detailed analyses, Dragonfly seeks to unlock the secrets of this enigmatic moon, potentially reshaping our understanding of life's origins and existence beyond Earth. Oumuamua, a fascinating object that captured the world's attention when it was discovered on October 19, 2017, by astronomers using the Pan-STARRS 1 telescope in Hawaii. Its name, Oumuamua, comes from the Hawaiian term for scout, or messenger from afar arriving first, reflecting its status as the first known interstellar object to pass through our solar system. What sets Oumuamua apart from other celestial bodies observed by scientists is its highly elongated shape. Unlike any comet or asteroid seen in our solar system, and its surprising acceleration as it traveled away from the Sun, behavior not typically expected from a natural celestial object without any visible signs of outgassing or a tail. Measuring roughly 800 meters long and only about 80 meters wide, Oumuamua's cigar-like shape is unprecedented. Observations and analyses suggest it is a dark red color, indicative of a surface rich in organic molecules that may have been irradiated by cosmic rays for millions, if not billions, of years. Its exact origin remains a mystery, but it's believed to have been ejected from another stellar system before making its solitary journey through the cosmos and eventually passing by Earth. The trajectory and speed of Oumuamua, combined with its non-gravitational acceleration as it moved away from the Sun, sparked intense debate and speculation among astronomers. Some theories suggest that its acceleration could be attributed to outgassing, a process common in comets where ice turns into gas and drives the comet forward. However, the lack of a visible comet-like tail or coma around Oumuamua challenged this explanation, leading to a variety of alternative theories, including the less conventional suggestion that Oumuamua might be an artificial object. The intrigue surrounding Oumuamua deepened as further analysis of its properties and behavior continued to challenge conventional understanding of comets and asteroids. One of the most perplexing aspects of Oumuamua was its rotation. Observations indicated that it was tumbling rather than smoothly rotating, and its brightness varied dramatically, suggesting that it was highly elongated and possibly flat, rather than cigar-shaped as initially thought. This unusual rotation and shape hinted at a violent past, perhaps involving a collision that sent it hurtling out of its original stellar system and into interstellar space. Another point of intense debate among scientists is the origin of Oumuamua. While it's clear that it came from outside our solar system, pinpointing its exact home has proven to be challenging. Some theories propose that Oumuamua could be a fragment from a larger object that was torn apart during a close encounter with a star or planet, while others suggest it might be a remnant of a planetary building block that never formed into a full-fledged planet. The diversity of theories reflects the limited data available and the novelty of studying such an object, underscoring the need for continued observation and research on interstellar visitors. Oumuamua's brief visit also highlighted the limitations and capabilities of current astronomical technologies and the importance of being prepared for future encounters with interstellar objects. Since its departure, there has been a concerted effort within the scientific community to enhance observation techniques and develop strategies for rapidly responding to similar phenomena. This includes proposals for missions that could intercept or rendezvous with incoming interstellar objects, providing unprecedented opportunities for in-situ study and potentially answering long-standing questions about the composition and nature of material from other star systems. In reflecting on the Oumuamua encounter, it's clear that this mysterious visitor has had a lasting impact on astronomy and our understanding of the cosmos. It has sparked conversations about the need for international cooperation in monitoring the skies for future interstellar objects and the potential for groundbreaking discoveries that such objects hold. As technology advances and our ability to detect and study these visitors from afar improves, we stand on the brink of a new frontier in our quest to understand the universe and our place within it. Eris, nestled far beyond the familiar planets of our solar system, invites intrigue and mystery as one of the most distant known dwarf planets. Discovered in 2005, Eris significantly contributed to the redefinition of what constitutes a planet, leading to the demotion of Pluto to the status of a dwarf planet. Located in the scattered disk, a remote area of the solar system, Eris orbits the Sun at a distance so vast that it completes a single orbit approximately every 558 years. This celestial body is named after the Greek goddess of discord and strife, a fitting title considering the astronomical debate its discovery sparked. Eris measures about 2,326 kilometers in diameter, making it slightly smaller than Pluto, but remarkably dense, suggesting it is primarily composed of rock and ice. This composition hints at the conditions and materials present in the outer solar system during its formation. One of the most fascinating aspects of Eris is its surface, which is exceptionally reflective, suggesting it is covered in a thin layer of frozen methane. Observations indicate that Eris's surface undergoes changes in brightness as it moves away from the Sun, which could be due to the sublimation of surface ice into gas, altering its reflectivity. Eris has one known moon, Dysnomia, named after the daughter of the Greek goddess Eris, representing lawlessness. The discovery of Dysnomia played a crucial role in determining Eris's mass, which is found to be approximately 27% greater than that of Pluto. This measurement was instrumental in understanding more about the dwarf planet's characteristics, including its density and composition. The story of Eris is not just about a distant dwarf planet. It is a narrative that reshaped our understanding of the solar system. Its discovery prompted the International Astronomical Union to redefine the criteria for planethood in 2006, which now requires a celestial body to orbit the Sun, be spherical in shape, and have cleared its orbit of other debris. Eris's presence in the Kuiper Belt, a region teeming with icy bodies, challenged the notion of what it means to dominate an orbit, contributing to the creation of the dwarf planet category. Diving deeper into the exploration of Eris, we delve into the scientific endeavors and future prospects surrounding this distant world. The intrigue surrounding Eris extends beyond its pivotal role in the reclassification of Pluto. It represents a frontier of discovery in the outer reaches of our solar system, where the conditions are starkly different from those of the inner planets. One of the most compelling aspects of Eris is its atmosphere. Observations suggest that Eris possesses a tenuous atmosphere of nitrogen and methane, similar to that of Pluto. This atmosphere is thought to expand when Eris approaches closer to the Sun along its elliptical orbit and freeze onto the surface as it moves away. This dynamic process offers valuable insights into atmospheric physics in extremely cold environments, far from the warmth of the Sun. Eris's orbit, taking it as far as 97 astronomical units, AU, from the Sun, 1 AU is the average distance from the Earth to the Sun, places it in a region of space that is difficult to study. Despite the challenges, the New Horizons mission to Pluto and the Kuiper Belt has sparked interest in missions that could explore Eris and other distant objects. Such a mission would not only shed light on Eris itself, but also on the nature of the scattered disk, a less understood region of the solar system that is home to many other icy bodies. The study of Eris and its comparison with other dwarf planets like Pluto and Haumea is crucial for understanding the diversity of objects in our solar system. Each of these bodies has unique characteristics, from their geological features to their atmospheres and moons, offering clues about the processes that dominate in these distant reaches. For instance, the similarities and differences between the atmospheres of Eris and Pluto can help scientists understand how atmospheric conditions evolve in response to their orbits and distances from the Sun. Looking to the future, Eris holds the potential to answer key questions about the solar system's formation and evolution. Its composition, particularly the ratio of rock to ice, can provide insights into the materials present in the outer solar system during its early history. Additionally, studying Eris's surface features, such as craters and possible cryovolcanoes, could reveal the impact history and internal processes of this remote dwarf planet. Advancements in telescope technology and the possibility of dedicated missions to the Kuiper Belt and beyond mean that our understanding of Eris is poised to grow. The James Webb Space Telescope, with its unprecedented sensitivity and resolution, is expected to offer new views of Eris, potentially uncovering features that have remained elusive. Sedna, an enigmatic object within our solar system, offers a fascinating glimpse into the vast and largely unexplored region beyond Neptune. Discovered in 2003, Sedna's orbit is one of the most distant and eccentric, taking it from about 76 astronomical units, AU, at its closest approach to the Sun, to an astonishing 936 AU at its farthest, a journey that takes approximately 11,400 Earth years to complete. This extraordinary orbit challenges our understanding of the solar system's formation and the forces shaping its outer boundaries. With a diameter estimated to be about 1,000 kilometers, Sedna is smaller than Pluto, classifying it as a dwarf planet, though it has yet to be officially designated as such by the International Astronomical Union. Its surface is one of the reddest in the solar system, suggesting the presence of organic molecules or tholins, which are complex compounds that form when ultraviolet sunlight irradiates simple organic compounds such as methane and ethane. The discovery of Sedna was significant because it resides in a region of space that was previously believed to be largely empty. Its presence, along with that of other distant objects discovered since, suggests the existence of a vast and previously unknown population of similar bodies in the outer solar system, sometimes referred to as the inner Oort cloud, or sednoids. These objects could be remnants from the early solar system, providing critical clues about its formation and the distribution of small bodies beyond Neptune. One of the most intriguing aspects of Sedna's discovery is the insight it offers into the gravitational influences at the edge of our solar system. The peculiar orbit of Sedna, which does not bring it close enough to be significantly affected by Neptune or the other giant planets, suggests that either it was perturbed by a yet undiscovered massive object far beyond Neptune, or it was captured from another star during the Sun's early history in a dense star cluster. One of the most tantalizing theories that Sedna's discovery has fueled is the possibility of a yet undiscovered ninth planet, sometimes referred to as Planet 9. This hypothetical planet is theorized to be influencing the orbits of Sedna and other distant objects through its gravitational pull. If it exists, Planet 9 could be several times the mass of Earth, lurking unseen in the dark regions far beyond Neptune. The search for this elusive planet involves complex simulations and observations, aiming to explain the anomalies in the orbits of Sedna and similar objects. Sedna's long journey around the Sun also offers a unique opportunity to study the Sun's influence over vast distances. As Sedna moves closer to the Sun in its eccentric orbit, it could potentially develop a very faint coma or atmosphere, much like comets do when they approach the Sun. Observing these phenomena could provide insights into the composition of Sedna and the mechanisms by which bodies in the solar system interact with solar radiation and the solar wind, even at extreme distances. Moreover, Sedna's existence challenges and refines our models of the solar system's early dynamics. It supports the hypothesis that the Sun was once part of a dense star cluster where close encounters with other stars could have dramatically affected the orbits of the outer solar system's objects. Alternatively, Sedna's peculiar orbit could be the result of interactions with unseen celestial bodies, or even a passing star, suggesting a more chaotic early solar system than previously thought. The exploration of Sedna and the quest to understand its origins and properties highlight the dynamic and ever-evolving nature of our solar system. Each discovery brings with it new puzzles and propels our scientific capabilities and curiosities further into the cosmos. Future missions, possibly involving flybys or even orbiters, could one day unravel the mysteries of Sedna. Kepler 1625b is an exoplanet that has captured the attention of astronomers and the public alike due to its intriguing characteristics and the possibility that it hosts a moon, akin to a giant version of our own Earth-Moon system. Discovered by the Kepler Space Telescope, which was launched by NASA to search for Earth-like planets orbiting other stars, Kepler 1625b resides in the constellation Cygnus, approximately 4,000 light-years from Earth. The planet orbits its host star, Kepler 1625, a star similar to our Sun but larger and older, every 287 days, a period that places it in or near the habitable zone of its star, where liquid water could potentially exist. Kepler 1625b is a gas giant, several times the size of Jupiter, making it a type of planet known as a hot Jupiter, although its specific conditions and temperature depend heavily on its atmosphere and distance from its star. The most striking aspect of Kepler 1625b's discovery was the potential detection of a moon orbiting the planet, which would be the first moon outside our solar system ever identified, colloquially known as an exomoon. This possible exomoon, unofficially named Kepler 1625bi, is estimated to be the size of Neptune, making it an unprecedented find, as moons of this size are not found in our solar system, and it challenges existing theories of moon formation. The detection of the exomoon is based on transit observations, where the planet and its moon pass in front of their host star, causing a temporary dimming of the star's light that can be measured from Earth. The data suggests that the moon's gravitational pull influences Kepler 1625b's orbit around its star, leading to variations in the timing and duration of the transits. These observations have sparked considerable interest and debate in the scientific community, with further analysis and additional observations needed to confirm the existence of the moon and understand its characteristics. The intrigue surrounding Kepler 1625b and its potential exomoon extends into the realm of what these celestial bodies can teach us about the cosmos. The study of such an unusual moon, especially one that rivals Neptune in size, could revolutionize our understanding of moon formation theories and the dynamics of planetary systems far beyond our own. The very notion that moons could be as large as planets introduces a fascinating complexity into the architecture of solar systems, suggesting a diversity in celestial formations that was previously unimagined. Further investigations into Kepler 1625b and its potential exomoon are crucial for astronomers seeking to unravel the mysteries of exoplanetary systems. Observations and models suggest that the formation of such a large moon might involve processes distinct from those that gave rise to the moons in our solar system. For instance, it could have formed from a disk of gas and dust surrounding Kepler 1625b in its early stages. Or it might even be a captured rogue planet, ensnared by Kepler 1625b's gravitational pull. The presence of this exomoon could also have significant implications for the environment of Kepler 1625b itself. If confirmed, it would provide a rare opportunity to study the interactions between a planet and its moon in a system very different from our own. For example, the gravitational forces between the planet and the moon could affect their rotational dynamics, leading to tidal heating, which might influence the internal geology and atmospheric conditions of the moon. Moreover, the potential habitability of such an exomoon sparks curiosity and speculation. While Kepler 1625b, a gas giant, is unlikely to be habitable, its moon, if it has a rocky composition and an atmosphere, could present conditions conducive to life, at least theoretically. The prospect of an exomoon with an environment that could support life adds an exciting dimension to the search for extraterrestrial life, expanding the focus from planets to their moons. The quest to confirm the existence of the exomoon and understand its nature involves sophisticated observational techniques and future space missions. Telescopes such as the Hubble Space Telescope and the upcoming James Webb Space Telescope play pivotal roles in this endeavor, offering the high-resolution imaging and spectroscopy needed to detect and characterize distant exoplanets and their moons. These observations, combined with advanced computer modeling, will help scientists piece together the story of Kepler 1625b and its companion, shedding light on the formation and evolution of complex planetary systems. Kelt 11b is a fascinating exoplanet discovered by astronomers using the Kilodegree Extremely Little Telescope survey, which specializes in finding exoplanets around bright stars. Located approximately 320 light-years away from Earth in the constellation Sextans, Kelt 11b orbits the star Kelt 11, a bright, evolved star that is nearing the end of its life cycle. This proximity to its host star provides a unique opportunity for scientists to study the exoplanet's atmospheric composition in detail. Kelt 11b is classified as a hot Jupiter, a type of gas giant exoplanet that is similar in characteristics to Jupiter but orbits very close to its star, resulting in much higher surface temperatures. However, Kelt 11b stands out among hot Jupiters due to its extremely low density. It is one of the least dense exoplanets ever discovered, with a density so low that it is nearly as inflatable as a balloon. This low density suggests that the planet has a very extended atmosphere, making it an excellent target for atmospheric studies. The planet's close orbit around its host star, completing a full revolution in just under 5 days, subjects it to intense stellar radiation. This proximity not only contributes to its high temperature, but also likely affects its atmospheric dynamics, potentially leading to atmospheric escape, where the outer layers of the atmosphere are blown away by stellar wind and radiation. Kelt 11b's large radius, nearly 40% larger than Jupiter's despite its lower mass, and its extended atmosphere provide a rare opportunity to analyze the chemical makeup of an exoplanet's atmosphere. The atmosphere's extended nature allows for the detection of various molecules through the process of transmission spectroscopy, where scientists observe the starlight that passes through the planet's atmosphere during transits. This method can reveal the presence of water vapor, carbon monoxide, and other important compounds, offering insights into the planet's formation and evolution. The intrigue surrounding Kelt 11b extends into the implications of its findings for the broader field of exoplanet research. The exceptional characteristics of Kelt 11b, particularly its low density and extended atmosphere, serve as a paradigm for understanding the physics and chemistry of hot Jupiters. These insights are pivotal in piecing together the evolutionary puzzle of gas giants under intense stellar irradiation, offering clues about their atmospheric retention, heat distribution, and potential for atmospheric escape over time. One of the most compelling aspects of studying Kelt 11b is what it can teach us about the life cycle of planetary atmospheres. The extended atmosphere of Kelt 11b, exposed to extreme conditions, may undergo processes that are not observed in the atmospheres of more dense and compact planets. For instance, the phenomenon of atmospheric escape where lighter molecules are stripped away from the planet by the star's radiation, is likely occurring at a significant rate on Kelt 11b. Understanding this process gives scientists valuable insights into how planets lose their atmospheres and the timescales over which this transformation can happen, which has implications for the habitability of planets over their lifetimes. The study of Kelt 11b's atmosphere through transmission spectroscopy opens a window into the chemical and thermal structures of hot Jupiter atmospheres. The detection of specific molecules, their distribution, and how they interact with incoming stellar radiation can inform models of atmospheric dynamics and chemistry. These models, in turn, help scientists predict the conditions on similar planets yet to be observed in detail, broadening our understanding of planetary atmospheres across the galaxy. The research into Kelt 11b and its atmospheric properties also underscores the importance of future telescopic missions and the development of new observational technologies. Instruments, such as the James Webb Space Telescope and the upcoming extremely large telescopes on the ground, are poised to provide even more detailed observations of Kelt 11b and other exoplanets. These advanced tools will enable the detection of fainter signals and the identification of more complex molecules in exoplanet atmospheres, further enriching our understanding of their composition and behavior. The HR 8799 system is an extraordinary and pioneering discovery in the field of astronomy, offering a fascinating glimpse into a planetary system that mirrors a young version of our own solar system. Located about 129 light-years away in the constellation Pegasus, this system is centered around HR 8799, a young main-sequence star that is slightly more massive and brighter than our Sun. The HR 8799 system is particularly renowned for being one of the first where multiple exoplanets were directly imaged, marking a significant milestone in the study of planetary systems beyond our own. Discovered incrementally between 2008 and 2010, the HR 8799 system consists of 4 massive exoplanets, known as HR 8799 E, D, C, and B, moving in orbits far from their parent star. These planets are gas giants, with masses ranging from about 7 to 10 times that of Jupiter, making them some of the largest exoplanets discovered to date. Their orbits range from relatively close to the star to more extended orbits, with the outermost planet, HR 8799b, orbiting at a distance comparable to Pluto's orbit in our solar system. One of the most striking features of the HR 8799 system is the direct imaging of its planets. Unlike the majority of exoplanets detected through indirect methods like the transit or radial velocity techniques, the planets of HR 8799 were observed directly using powerful telescopes equipped with adaptive optics systems. These systems correct the blurring effect of the Earth's atmosphere, allowing for clearer images of celestial objects. The direct imaging of these exoplanets has provided astronomers with invaluable data regarding their atmospheres, compositions, and orbital dynamics. The planets of the HR 8799 system are young, with estimated ages of around 30 million years. This youthfulness means they are still glowing with residual heat from their formation, making them easier to observe with infrared telescopes. Observations have revealed that these planets have complex atmospheres with clouds and possibly even weather systems, similar to what is found in the gas giants of our solar system. Moreover, the HR 8799 system is surrounded by a vast debris disk, composed of dust and ice, which is thought to be the remnants of the process that formed the planets, and possibly hints at the presence of additional smaller bodies within the system. Continuing the exploration of the HR 8799 system, we delve deeper into the scientific significance and the future prospects of studying such a uniquely detailed planetary system. The HR 8799 system's direct imaging provides an unprecedented opportunity to study the atmospheric composition, orbital mechanics, and even the climate of exoplanets in great detail, offering a wealth of information about how planetary systems develop and evolve over time. The atmospheres of the HR 8799 planets are of particular interest to astronomers. Spectroscopic analysis, which examines the spectrum of light emitted or absorbed by the planets, can reveal the presence of various gases and potentially provide clues about atmospheric dynamics and weather patterns. For instance, the detection of water vapor, methane, and carbon monoxide in these planets' atmospheres would not only confirm theories about the chemical makeup of gas giants, but also offer insights into the processes that dominate their weather and climate systems. The HR 8799 system's debris disk plays a crucial role in understanding the formation and evolution of planetary systems. By studying the distribution and composition of the debris disk, scientists can infer the presence of other, smaller bodies within the system, such as asteroids or comets, which may impact the development of the system's planets. The disk also provides clues about the late stages of planetary formation, offering a glimpse into the processes that may have occurred in the early solar system. The future study of the HR 8799 system will benefit significantly from advancements in telescope technology and observation techniques. Projects like the James Webb Space Telescope, JWST, and ground-based telescopes equipped with next-generation adaptive optics will be able to capture even more detailed images and spectra of the HR 8799 planets. These observations will enhance our understanding of the planet's atmospheres, including their compositions, temperature profiles, and potential weather phenomena. The study of the HR 8799 system has implications for the search for life beyond Earth. While the gas giants themselves are unlikely to host life as we know it, their detailed study can inform our understanding of the habitability of other planetary systems. By learning how gas giants and their moons form and evolve, scientists can better assess the potential for habitable environments elsewhere in the galaxy. As we near the end of this documentary, we are reminded that the universe is filled with mysteries waiting to be unraveled and wonders yet to be discovered. The quest to understand the cosmos and our place within it has never been more alive. With each passing day, new technologies and methodologies are being developed, opening up new possibilities for discovery and exploration. What lies beyond the next horizon? Only time and our relentless pursuit of the unknown will tell. But one thing is certain, the journey is far from over, and the best
The Great Rift Valley. Evocative words that immediately suggest origins. There are many reasons I love visiting Ethiopia. I love the people. I love the food. I love the high-altitude freshness of Addis. I love the mountains and valleys and high plains. I even loved visiting Erta Ale, the legendary shield volcano at the Afar triple junction known as the Gateway to Hell, although I probably won't do it again. But I also love an idea. It's impossible to visit this ancient country and not catch a glimpse in your peripheral vision of a chain of ghosts stretching back 10,000 generations, because it is firmly embedded in popular culture that we came from here. Every one of us is related to someone who lived in Ethiopia hundreds of thousands of years ago. It is the Garden of Eden, the place where humanity began. What popular culture has yet to assimilate, however, is the fortuitous and precarious nature of the ascent of man. When I was growing up, I remember talk of the missing link, that elusive fossil that would tie us definitively to our ape-like ancestors. When I started school, DNA sequencing was not yet invented, and Lucy hadn't been unearthed. Today, we have a significantly more complete view of how Australopithecines like Lucy are related to modern humans, and whilst the details are still debated and new evidence is continually updating the standard model of hominin evolution, it's now possible to tell the broad sweep of the story in some detail. The members of our human evolutionary family are referred to as hominins. The split between hominins and the ancestor of the chimpanzee occurred at some point before 5 million years ago in Africa, and by 4 million years ago, Australopithecus afarensis, Lucy, was present. Their brain size was approximately 500 cc, around the same as a chimpanzee, and less than 1/3 that of a modern human. Around 1.8 million years ago, there was a step change in both brain size and the number of hominin species in the East African Rift. Several species of our genus Homo appeared, including Homo habilis and Homo erectus. They lived for a time alongside other species, including several Australopithecines and a genus known as Paranthropus. There are anthropologists who prefer to classify Paranthropus as a different species of Australopithecus. I make this point not to be confusing, but to highlight an important fact. The study of hominin evolution is a difficult area, and it's not surprising that there are ongoing debates about the classification of 2-million-year-old fossils and DNA sequences. What's important for our story, however, and what nobody disputes, is that there seems to have been a jump in both brain size and the number of species of hominins in the Rift Valley region around 1.8 million years ago. By around 1.4 million years ago, only one of these species had survived, Homo erectus, with a brain size of 1000 cc. The next milestone is the appearance of Homo heidelbergensis around 800,000 years ago. Homo heidelbergensis is generally accepted to be the ancestor of Homo sapiens and the Neanderthals who lived alongside us in Europe until around 45,000 years ago, and possibly later. Homo heidelbergensis represented another jump in brain size, up to around 1400 cc, which is close to that of modern humans. In the late 1960s and early 1970s, 2 hominin skulls were found near the Omo River in Ethiopia. Known as Omo I and Omo II, argon dating of the volcanic sediments around the level they were found dates them at 195,000 plus or minus 5,000 years old. These are the earliest fossilized remains to have been identified as Homo sapiens. The interesting question is what caused these rapid increases in brain size, driving hominin intelligence from the chimpanzee-like capabilities of Australopithecus to modern humans in only a few million years. Again, this is a very active area of research, and there are differences of opinion amongst experts. This is the nature of science at the frontier of knowledge, and this is what makes science exciting and successful. The model we are focusing on is the most widely accepted theory of human evolution. It is known as the recent single origin hypothesis, or more colloquially, the out of Africa model, and the dates and locations we've described so far might be referred to as textbook. There is broad consensus, therefore, about the when and the where, but not why, and it is to why that we now turn. There's a trend towards larger brain size over the 4 million years since the emergence of Australopithecus, but the trend is not gradual. There's a large jump around 1.8 million years ago with the emergence of Homo erectus, and another jump just under 1 million years ago with Homo heidelbergensis. The final jump occurs when Homo sapiens emerges 200,000 years ago. The time period around 1.8 million years ago also corresponds to a leap in the number of hominin species present in the Rift Valley. There were at least 5 or 6 species living side by side, suggesting that something interesting occurred around this time, which may have been responsible for, or was a contributing factor to, the observed increase in brain size, particularly in Homo erectus. The large number of deep water lakes appearing temporarily in the Rift Valley around 1.8 million years ago indicates that at this time the climate, and in particular the level of rainfall, was varying quickly and violently. Similar climate variation occurs around 1 million years ago and 200,000 years ago, and this appears to be correlated with increase in hominin brain size. The theory is that rapidly changing climatic conditions in the Rift Valley at these specific times played an important role in driving the increases in brain size. The selection pressures that may have led to these increases are unclear. Selection for adaptability was probably an important factor, but social factors such as the ability to live in large groups and intraspecies competition as a result of the larger number of species living side by side, particularly around 1.8 million years ago, must also have played a role. Having said that, it does appear that climate variation in the Rift Valley 1.8 million, 1 million and 200,000 years ago could have been a contributing factor to the development of our intelligence. This is known as the pulse climate variability hypothesis. We can now bring all these threads together to reveal a surprising and, for me, dizzying hypothesis, which, if correct, sheds new light on the immensely contingent nature of the existence of our modern civilization, or, in simpler language, why we are bloody lucky to be here. The three dates, 1.8 million, 1 million, and 200,000 years ago, correspond to the times when the Earth's orbit was at its most elliptical. As described earlier, the mechanism by which climate changes due to precession at these times is well understood. The pulse climate variability hypothesis asserts that the unique geology and position of the Great Rift Valley amplified these changes, and that early hominins responded by increasing their brain size. If this is correct, our brains evolved as a response to changes in the Earth's orbit, driven by the precise arrangement of the orbits of the other planets around the Sun, and precession, driven primarily by the gravitational interaction between the Moon and Earth's axial tilt, both of which date back to a collision early in the history of the solar system. And all this is plainly blind luck. Without an inconceivably unlikely set of coincidences, and the way these conspired together to change the climate in one system of valleys in wonderful Ethiopia, we wouldn't exist. If this is correct, then what a response. I held a brain for the cameras at St. Paul's Teaching Hospital in Addis. It is the most complex single object in the known universe, a most intricate example of emergent complexity, assembled over 4 billion years by natural selection, operating within the constraints placed upon it by the laws of physics and the particular biochemistry of life on Earth. The brain contains around 85 billion individual neurons, which is of the same order as the number of stars in an average galaxy. But that doesn't begin to describe its complexity. Each neuron is thought to make between 10,000 and 100,000 connections to other neurons, making the brain a computer way beyond anything our current technology can simulate. When we do manage to simulate one, I have no doubt that sentience will emerge. Consciousness is not magic. It is an emergent property consistent with the known laws of nature. But that doesn't lessen the wonder one iota. Out of this evolutionary marvel, we emerge. Thoughts, feelings, hopes, and dreams exist on Earth because of electrical activity inside a 1.5 kilogram blob of stuff, which hasn't changed much since the earliest modern humans began the long journey out of Africa. If you could travel back in time and bring a newborn baby from 200,000 years ago into the 21st century, allowing it to grow up in our modern society with a modern education, it could achieve anything a modern child could. It could even become an astronaut. Which sets up one more question. If the hardware was present 200,000 years ago, then what changed to lift us from the Great Rift Valley into space? An unprecedented duel with nature. The best thing we can do now is just to listen and hope, said Cliff Mitchellmore, broadcasting from the BBC studios 24 minutes from the expected splashdown of Apollo 13. On the 17th of April 1970, I was too young to watch the live broadcast, but I've seen the recording many times since. Grainy pictures from the deck of the USS Iwo Jima, its flight deck crammed with nervous sailors off the coast of Samoa. Patrick Moore and Geoffrey Pardo, grim-faced in the studios, and James Burke famously with fingers crossed behind his back. Apollo Control, Houston, we've just had loss of signal from Honeysuckle. Honeysuckle Creek Tracking Station in Canberra, Australia, was the last ground station to contact Apollo 13 before it entered the Earth's atmosphere on its way home. Signal loss during re-entry is routine high drama on all space missions. The ionization of the atmosphere caused by the frictional heating of the spacecraft blocks radio signals, typically resulting in radio silence for 4 minutes. On Apollo 13, 6 minutes passed in silence. The brilliance of the BBC's quartet of commentators was in the silence they allowed on the airwaves. The only sound was the static of the NASA feed, a moment of genuine tension. No need for vacuous media babble. Nobody could bring themselves to speak.